Hi, my name is Renske from Team 4481 in the Netherlands, and we'll be hosting the stream for the European time slot. Jonathan will be telling us something about how you can go 5 weeks with a budget on 1,000 euros. So let's get on it. Here you go, Jonathan. The screen is all yours.
Thank you very much. So this evening, I'm going to be talking about building on a budget, and it's all about how you can be competitive with limited time and limited resources in terms of budget, be that money, be that materials, or anything else. So I wanted to start off by imagining a scenario, and I think this is a scenario that's not too far divorced from the reality that many teams might be facing in the coming year. So imagine that it's January 2021, it's not too far away, and kickoff is happening. You learn about what changes are being made to the game. Your team is all ready to compete, build an awesome robot or modify an existing one, and you're really ready to do something great this year. And then you're informed that you only have $1,000 and you only have 5 weeks of access to your workshop, and that because of COVID restrictions and the need for social distancing, you only have 10 people in your workshop at once. So what do you do? Well, essentially, you have to improvise. Now, you may ask, well, why should you listen to me about that? So I come from a team which had to deal with this on a regular basis. So we're a 10-man team from Australia. We had, because of Australian school restrictions, even before the pandemic, we essentially had a 3-week build season. From when the bag still existed, we had 3 weeks from kickoff. Sorry, we had 3 weeks from the first time we were able to get into our shop to bag day, just because the first 3 weeks of the season were during the school holidays, and there was no good way of accessing the workshop and the robot during that time. And we had a very limited budget. And myself personally, I was first a student captain, and then as soon as I finished school, I went back to act as a mentor. Now, in that time, since I've graduated, I've worked on 2 startups with some friends. So through all of this, working efficiently and making the most out of limited resources and limited time has been my experience. So who is this talk for? Obviously, not every single team is limited in resources, or at least not severely limited in resources. But really, with the pandemic and the impact that has had on how teams work and what things teams have access to, it really is relevant to more and more people. So this includes teams who have smaller budgets due to the pandemic, be that a loss of sponsorship, be that budget cuts to your schools, and people who have limited access to their workshop, be this from school restrictions, government restrictions, the need for social distancing, or just good hygienic practice. And in case your team isn't impacted by any of this, if you're looking to improve your productivity and try and get more done in the same amount of time, then this talk is also for you. Now, what this talk will cover is broken down into 3 sections. The first is how to organize your team, how to design your robot from a high-level perspective, and finally, how to design and manufacture your robot so that you can maximize all of these things. Now, it's important to note that all 3 of these things intersect. They're not 3 discrete, easily broken up parts. And so you want to be creative in how you find a solution to all of these things. Now, what this talk won't cover is many of the finer details, because this is often covered by many other teams. So things about strategy, CAD design, the use of CNCs, and we've had many good talks just in this event alone on those subjects. So make sure that you scour YouTube and relevant forums for information about those things. I won't cover them here. Make sure that you research well, because there really is a wealth of information about all of these things. The other thing that we won't touch on in this talk is how to implement all of these things for your team, how to turn these ideas and principles into ways that will work for your team. Each team is different, and it will work better if you think about how to adjust the parameters I talk about in this presentation to suit your needs. So let's now look at the first part of the three, and that's how you organize your team. Now, much of this will be done by your team leadership and be that mentors or student leaders, preferably together. And so the first thing that we realized when I first returned to my team to mentor, this was in late 2018, early 2019, we realized that we had to break our time down. We can't just say, okay, we got 3 weeks to build the robot. We had to divide our time down into soft time and into hard time. So what is soft time and what is hard time? Soft time is time when your team can discuss things or just work on things in general. Now, specifically, it means time that you don't have access to your robot. But this is time that you can use to meet together, to design, to research, and to plan. And the thing about soft time is most teams have a lot of it. And in fact, most individuals have a lot of soft time. So whether you're working in, whether it's FRC or any other project that you do, you should realize that there's lots of time when you say you can get on a Zoom call, you can discuss over Slack, Discord, whatever application your team uses. And you should be using this time that you have a lot of, to increase the efficiency of hard time, which generally is more limited. So hard time is defined as time when you have access to your shop and to your robot. So that's time when that really you are more limited with. And you need to treat this as your most precious resource. It's more precious than Falcon 500s. Because no matter how much funding you get, you can't overcome it. Now, the number 1 rule with hard time is you never use this time to do things that you can do in soft time. How effectively you use your hard time will determine how good your robot is, essentially, because that's the time when you have access to your robot. So the takeaway from this slide and what you'll need to remember to make the rest of my explanation make sense is soft time is time that you can be doing, that you can use to do things away from the robot. Hard time is the time that you have to work on the robot. So the first thing to do to make sure that you're making the most effective use of your, of your hard time is you need to know what you're working with. So do this before the season starts. Now, as of today, the 19th of December, we have about 15 days, 2 weeks before season gets underway. So how do you do this? One, you need to know the regulations you're working with, especially in terms of COVID, and what your team's circumstances are. So how many days you can meet, where can you meet, be that at your school, at somebody's home, at your team's facilities, wherever they may be. Now, how many people can be there at once, and when can people make it, and who can use what tools? Plan this out on a Gantt chart. See if there are any days where, say if your team has rules about who can use which tools, are there certain days when there is an important tool or machine that no one can use, right? These are all things you need to plan around, and you almost have to micromanage this in your soft time. So time that you're spending away from your shop and from your robot. Now, you do a simple calculation, and you need to calculate the number of man hours that your team has. So this is the number of people that you can have in your shop at that particular time, multiplied by the number of hours that they're going to be there for. And if you don't like the word man hours, you can call it woman hours, people hours, whatever you like. But essentially, say I can get 6 people to fit into our shop to maintain social distancing and comply with regulations, and that day we are working a 6-hour day, then I have a total of 36 man hours to work with. Now we get into how to actually make the most of that hard time with everything that we've considered so far in mind: the number of man hours, how many people you can have there, and who can use and who can do what. Now, what we've generally found is that if you go for shorter and more focused days, then it works better. So one thing that we have to work with on our team is, because we build while school is in session, we can't be there during the day. We can't do a 9 o'clock to a 4 o'clock. We have to wait until school finishes at 3 p.m. And so what we do is, after school finishes at 3 in the afternoon, we say we will build as hard as we can. We're going to do nothing but build for 2 hours, because that's when school closes and that's when we all need to be out of there. And we find that when we do get some chances to build either on a weekend or in the holidays, we're not nearly as efficient. People get tired in the afternoons after a full day of work. And lunch breaks, snack breaks, all of those things are awful ways of using your hard time. Now, the second thing is, we found that CAD is incredibly important to integrate into your workflow, because once you have a detailed drawing made up and you know exactly what you need to do, then it becomes so much easier to make the most of your hard time. You don't need to spend that time worrying about, oh, is this part too short? Is that part going to fit? It's all planned out. Mistakes are the biggest delay, or the second biggest delay, I should say. We'll talk about what the biggest delay is in I think one of the next few slides. So avoid mistakes by using CAD. You don't want to build halfway, then realize something is broken, or something is not done properly, and then go back. Now, the next thing is these next 2 points go hand in hand. You want to have someone who is effectively, who directs the building process and directs your manpower, so to speak, or woman power, or people power, or whatever you like to call it, to wherever in the building process you want to direct that to. So Generally, this is either a student leader or a mentor who will keep tabs on how different things are progressing in the shop, and go, we need an extra pair of hands over there, and direct people over there. Now, this person should make up a agenda for each day. What they're going to do, figure out how long that's going to take, and assign people to each roles. Not just say where, oh, today we're going to build an intake. You want to say person X, person Y are going to be on this task. Now, be reasonable as to what you think can be done in one day. If you allocate too much, it only hurts your productivity by diverting resources where they shouldn't be going. So for example, if I say, I'm going to have the drive face built in 3 hours, well, now you're going to plan tasks that, assuming you can't get a drive face built in 3 hours, now you're going to plan tasks that rely on having a drive face built after those 3 hours. And if you don't get your drive face done, then all of those tasks are going to have to be pushed back. And that means people are not doing what they should optimally be doing. And of course, it goes without saying, be flexible, be ready to reallocate resources, be that machinery, be that people, or anything like that. And one last thing that's not entirely necessary, but we found quite helpful, is to hold online briefings the night before. We say, all right, if we're going to be doing a full day's building on say Saturday, Friday night, everyone jumps onto a Zoom call. We call for 15 minutes. We say, tomorrow we're doing X, Y, and Z. On school days, because we build after school at lunchtimes, we try to get everyone in and say, okay, this afternoon, we're going to be doing this. Everyone get to know what things you're going to be doing. So after lunch, you go to class. As soon as class finishes, come back, and don't wait to be told what to do. You should already know what you're doing. Finish class, drop your bags, get onto the machine, or get onto the mechanism that you're meant to be working on. Okay, so this is more or less our robot development process. Now, this is quite an optimistic process. In reality, we don't get to fabrication until maybe end of week 3, start of week 4. So this is a little optimistic. So for the first 2 weeks, we have 0 access to our workshop, not at all. So we use that time as soft time. In the past, when we've been able to hold physical meetings, we've gone to libraries, public libraries, or we've met online sometimes, and you use that time to go through strategy and go through design. Now, if you're very, very limited on time, like we are, you can often find a way of skipping the prototyping phase. Watch what other teams are doing, and especially now with No Bag and with the Open Alliance teams, it's very, very easy to figure out what works, what doesn't, so you don't necessarily need to try it out yourself. And this has been instrumental to how we build robots, because we no longer have to prototype. And I would suggest that if you are a team that's particularly limited on resources, you want to stick with building what you know works. Because sure, it might feel really good to get something innovative working, but if you're going for maximum student satisfaction, maximum results as well, you're always going to be better served by employing something that's tried and tested. Now, next stage is fabrication. Fabrication has to be done in hard time, although at the end of this presentation, I'll talk about one of the ways that you can get around this. You want your team to be well drilled in how to make parts effectively. Now, I'll also talk about this in the latter part, the manufacturing part. Now, weeks 4 to 5, you want to assemble, and you want to try and do that distributed. Not everyone crowded around the same robot. Not that that would be very good in the present circumstances if you want to avoid people getting sick. And so you want to have them spread out into multiple different processes, into multiple different subsystems. Now, finally, you want to get testing in, testing practice, don't skip this. Now, formalizing processes, as I said before, the #1 enemy of productivity is mistakes. If you drill something wrong, if you assemble something wrong, if you accidentally break something, or you design something wrong, this is going to massively, massively hurt your time. More than once, things have been going completely fine in a season for us until someone drilled one hole that was a few centimeters off because he had read something wrong. And that happened, we would try to put it on, we'd realize during assembly that this hole was incorrectly drilled. That part would have to be remade. You'd have to wait for the person with the drawings to turn up, or you'd have to try and retrieve the drawings from somewhere. You would have to find all sorts of ways. So now you're delaying your assembly. And what we found is that we needed a formal review, approval, and revisions process. So that means every single drawing, every single design is double checked before that's allowed to go to manufacturing process. Also, always use engineering drawings, even if you don't use CAD, which I highly recommend. At least draw out, even using your hands, at least draw out roughly the dimensions, so that people know what they're actually making. Don't manufacture off the top of your head. That's something that I learned as a student after many failed mechanisms, because I tried to just grab a piece of aluminium and draw it. Also consider using a production line process. Now, on our team, we spread people over separate rooms where separate machines are made. And so everyone has a job that they do over and over again. So we have a drawing, and each part has a corresponding drawing. So the first people cut the raw stock, the raw aluminium, to how long it needs to be according to the drawing. They send those parts with the drawing through to the next people who mark it out for where holes and other features are needed. Then people drill the holes. Other people may make special features, and this is just passed down the production line with the drawing. And then finally, of course, people brush, file, deburr to make sure that things look nice and that they're safe. Okay, you want to station people by their tasks. You want people performing the same tasks over and over again. It may get a bit boring, but that's where the short day comes in. So if you're only doing this for 2 days, 2 hours, at a time, the boredom isn't too bad. And it's also a good way of overcoming COVID restrictions, like I talked about before. If there's a rule saying you can only have 3 or 4 people in a room, that's fine. You can just have 3 or 4 people cutting, 3 or 4 people marking, 3 or 4 people drilling. Now, it is the job of the production manager to identify potential bottlenecks, to monitor the process, and to divert resources where they're needed. So, for example, if marking, the people who mark out the features on the actual piece of tube, if they're getting bogged down, the production manager might want to get one of the people from a different station to help them out. Now, this is the thing that I alluded to earlier. The biggest reason that productivity suffers: safety. If there is not a culture of safety, if people have accidents, that is going to cause big issues. Okay, because if someone gets injured, more than just not wanting to get injured in the first place, you're now going to have to stop everything. You're going to have to make sure the person is okay. If you work in a school, there might be additional procedures. Teachers might not be very happy, and the whole thing is just a huge delay. It's human nature to want to cut corners. Our team did not. This is something that our team has not done well in the past. So someone who's learned from experience of people getting hurt, this is the biggest delay, and it's more than any sort of corner cutting, any sort of time that corner cutting can save you. And of course, safety culture starts from the top down. Team leadership needs to establish a safety culture. If team leadership is always in a rush, if team leadership always wants to cut corners, that is not going to help you. Not at all. Okay, so that was the first part, and now we're going to talk about robot architecture. If you don't take anything else away from the first part, team organization, if you don't take anything else away, I should say, remember to distinguish between hard time and soft time, especially now that we can't be in person all the time. Know when you can plan things out and when you can work on the physical robot. Do everything you can to make your hard time as efficient as possible. Okay, so what do we mean by robot architecture? Now, this is the big picture design of your robot. We're not talking about specifically what sort of mechanisms, or rather how your mechanisms themselves work. We're not talking about what type of claw, what type of intake. We're just saying what mechanisms you want on your robot. I want an intake. I want a lift. I want, you can have all sorts of other things. I want a shooter. And whereabouts they go, how they interact with each other. So for example, you might want to say, I want an arm with an intake on it, picks up a game piece and then turns around and feeds it back into the shooter, which might not be particularly efficient. Or you say, I want to blend these things together. I want to put these here, things like that. Now, in my experience from Australia, many Australian robots are far more complex than they need to be. They don't achieve much. They play the game decently, average, but they have an incredible amount of parts that are really, really not necessary. Okay. A question that I pose to my team every single year is can you get away with building a robot that's nothing more than an intake that's on the end of an arm? And if you look at the history of FRC, you'll find that there are a lot of robots that are able to do very well doing just this. So let's have a look at one specific example of two robots that really are on polarizing ends of that spectrum of simplicity. Although I'll concede that the robot that represents the lower end of that is not perhaps the most extreme manifestation of a minimalist philosophy. So on the left here we have Team 604, on the right we have Team 254, both very teams that are famous for different things, perhaps one more so than the other. So if we look at Team 604 on the left, their robot is quite simple. It's nothing more than an intake on the end of an arm. The intake is simply a row of wheels powered by a PG. It also has a mechanism to capture the disk in 2019. I believe, although I'm not entirely sure, that it does somewhat center the disk. In addition to that, it's able to climb using nothing more than a simple arm. Now, this robot in total, outside the drivetrain, has maybe 3 motors, at least only 3 controls. And so, very simple. Robot on the right, many of you in FRC will be familiar with this robot. 254's 2019 robot, incredibly technically impressive machine. I'm not at all saying that it's poor in the comparisons that I'm going to be making following this, but as you can see, extraordinarily complex, very, very capable. Now, the question is, how did these teams do in competition? Now, as you can see, I've pulled up 2 regionals where both of these teams were present. Now, 254 in the first regional was ranked narrowly behind 604, and in the second regional was ahead, but not by particularly much. Now, the question is, what point am I trying to make? Well, what I'm saying is that at least in qualifications, now we saw that once playoffs happened, things turned a little different. But at least in qualifications, one can be very competitive with nothing more than an intake and an arm, with a simple robot and a practiced driver, one which is designed well. And why? Why was it designed well? Well, this team saw a strategy where they can store many points with only a simple robot. Now, this may not happen every single year. For this year's game 2020, I myself am personally of the opinion that a simple robot, it's difficult to do a simple robot that can store well if we're just talking about a robot that picks up the balls and dumps it right out. Of course, I might be seeing something, I might not be seeing something that other teams are seeing. And of course, if your team sees a way of doing well, being very competitive with nothing but a low robot, all the power to you. In addition to that, of course, your team's goals will be different. So if your team just wants to be reasonably competitive, compete in the midfield, a well-practiced driver on a low robot, like the 2018 Everybot, can be extremely effective. Okay, so why was this? So this robot found a game and a strategy that worked very well. The team also worked on implementing the simplest architecture that they could possibly imagine. No frills, no unnecessary parts whatsoever. They use COT parts, simple, straightforward structures. They save resources and spent that on practice and refinement. Okay, now a few lessons from my own team's experience. Number 1 mistake is overcommitment. Everyone thinks that they can build more than they actually can. They try to, the old saying of aim for the moon, you'll land among the stars, does not apply particularly well to many engineering fields. In fact, if you think about the actual moon mission, had they actually aimed for the moon when they just wanted to get into orbit, that mission would not have ended particularly well. And the same thing happens in FRC. The number 1 commitment I see from all teams is trying to build more than they're actually capable of. A less functional robot with a better driver will, in 90% of cases, win out against a robot with more functions, but a less practiced drive team at intermediate levels of competition. If your goal is to win Einstein, then of course you'll have to add more and more function. But this talk is more about making the most of limited resources than competing at the highest levels. There are people who are much more qualified than myself to talk about those things. Now, one thing to realize is more functionality does not always mean faster robot. So one thing that this is particularly true in is using a turret versus not using a turret. So obviously a turret will mean that you can aim faster, but say if you spend an extra week or so tuning the turret, making it work, half the time or maybe even more than half the time, that week would be better spent practicing with your driver, getting him or her familiar with how to aim manually, or point the robot in the right direction manually, and then using vision or whatever other method to aim. Similar thing with lift and arm. Lifts will give you more predictable motion, but arms are simpler. One final thing. Avoid mechanisms which pass end pieces from one to the other at all costs. Now, this is, I see this a lot with high resource teams. Obviously, they have the time to make this work, and they have other priorities for which they would use this method to optimize. Now, with most of the mid to lower resource teams, this is usually not worth it. You're much better off with less functionality, but a simpler, more reliable setup. Okay. Additional resources on robot architecture. These two teams and their respective presenters give excellent presentations that we've learned a lot about, and I'd highly recommend that you Google these presentations. They're freely available on YouTube, and you can. This will really help you rethink how you design your robot from a big picture level, and make your robots easier to build from the very start. Okay, so the final part of our presentation tonight will be looking at mechanical design. So that's to say how you can actually design the intricacies of your robot to make it easier to manufacture and easier to build. Now, there are 4 S's to remember, 4 S's. They're listed here. And we've learned from all of these things from the mistakes that we've made as a team, from all of the robots that haven't done well. First thing is simplicity. Now, this is a word that gets thrown out a lot, and in a way, it's difficult to define what exactly simplicity is. That's one of the reasons why so few people actually are able to offer a concrete definition. Now, there's a few different ways that we can measure simplicity, and sometimes they are competing, sometimes they are contradictory, and I'll try and highlight where that occurs. So the first thing to consider is the number of components or the number of subsystems. Say if your robot is going to have an intake, something that centers the intake, something that conveys the intake to the shooter, something that, and outside the shooter, you have a turret, you have an aiming mechanism that adjusts the angle of the shooter hood. That's a good way of measuring if your robot is complex. Now, the second way so that is functional complexity. That is complexity in what your robot has to do to actually get an accurate shot or to perform a specific task well. The second type of complexity is structural complexity. So one of the things that I see a lot of people do is they say, okay, in order to reduce functional complexity, I'm going to try and fit everything into one mechanism. And now you've got all sorts of oblique angles. Things are not at right angles. You need 3-dimensional joints, and you need things at funny angles just to make everything fit together. You haven't actually saved yourself very much in terms of complexity. And if anything, you've made the manufacturing process harder. Now, that may be for many people preferable to making the assembly, to making the integration process harder. And I would say that oftentimes it is worth a small increase in structural complexity, but make sure that you're not neglecting that and you're factoring that into your considerations, your trade-off considerations. Pay attention to number of fasteners and number of joints. That's a good way of figuring out whether you're being complex or whether your robot is simple. Now, final thing is use COTS components. The COTS revolution in recent years has massively lowered the bar to competitiveness. So being able to compete in the mid to higher range, being able to make playoffs on a regular basis. And not to mention, if you are limited on resources, try and recycle each previous year's parts as much as possible. Recycle your VPs, recycle everything, and make sure that you try and keep it in reasonable condition so that it can be used over and over again. The next S is serviceability. Now, always consider how you're going to fit something or get to a part to adjust something if it needs adjusting or if it needs repairing. And the number one thing is access holes. So if you're doing things by hand, if you don't have access to CNC resources, and you need to think about how things bolt together, make sure that you're able to drill access holes. So that's holes where you can stick your tools through and you can turn things. And you don't, the last thing you want is you want two people who are bent over in funny positions around the robot, one holding a hammer while the other one is holding, sorry, not a hammer. One is holding a spanner, or I think in some parts of the world you call it a wrench, while the other guy, and this has actually happened on my team, uses a pair of pliers to insert an Allen key into the head of a bolt, and then uses the same pair of pliers, because that Allen key is now in such an inaccessible position, uses the pliers to turn the Allen key while the second person holds the spanner. That's something that you want to avoid at all costs, because that's going to massively slow down your manufacturing process. Now, one thing you can always consider investing in is some really good tools. Standardized Allen keys, so everyone has one when they can have one. Train someone on the design team to think about manufacturing. Their job can be just to look at the CAD of the robot, make sure that this robot is manufacturable and reasonably easy to manufacture as well. In addition to that, consider using blind fasteners. Blind rivets are fantastic for tube because you don't have to reach through the other side to try and fasten it. So that's something to consider. If you have a good rivet gun, there's the hand rivet guns that you squeeze. Those can often be quite tiring to use. Look for scissor type rivet guns where there's a handle on the end and you're able to push the rivet in. Likewise, consider, if you have more resources, a pneumatic riveter. You just put the rivets in, go ping, 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 and the rivets just go right in. Now, poor access can also lead to accidents and mishaps, and that's a major slowdown. So this is an example of what not to do. Here is our electronics board that's actually under the lifting and the lifter and a conveyor belt that we have on our robot. And the lifter isn't actually even on the robot. The lifter is meant to go directly over the electronics board, which, to put it simply, would not have gone well. And so that's something to consider. Whenever something went wrong on this robot, our electronics board was double-sided. And so to fit something, we would have to prop the robot up on two chairs, and someone would actually have to slide underneath the robot while it's on those two chairs to try and fix anything. More often than not, I was the one who went under the robot because I didn't want it falling onto any students, and the robot has fallen on me at least once at comp. And obviously, if someone gets hurt while trying to get into an awkward position to access something, that's going to be a massive, massive slowdown. In addition to, obviously, you don't want anyone getting hurt. Now, the next S is separability. this is one place where we did well this year, and that is you want your subsystems to be modular. Now, I alluded to earlier that in the assembly process, you want your mechanisms to be nice and distributed. And so you don't want everyone to have to pack into one room, crowd around one robot and try and fix things. In the past, we found that this is very bad for productivity because people start getting into a tangle with each other. At one time, I remember distinctly at comp, a lot of things broke after a bad mishap, a collision with another robot, and we had about 10 guys crowded around the robot, each one trying to, with their arms stuck out, trying to reach an Allen key in to hold something or trying to put something in. And it was so crowded that it was just a sea of arms and Allen keys and wrenches, and you simply couldn't see anything. That's why after that season, we implemented a rule where every single mechanism must be removable under a minute and is attached by no more than 4 bolts. So on this mechanism we see on the right here, that is our shooter. And so we had 4 bolts, 1 in each corner. And if it needed repairs, we would simply undo the 4 bolts, the whole thing would lift out of our robot and we can repair it. Now, obviously during manufacturing, this was very good because this could be assembled in a separate room to what everyone else was doing. And especially now in the age of a pandemic, you don't want everyone stuck together in one room. Now, the next thing is standardization. I believe this is the final thing. You want to use standardized components. So on this piece on the right here, this is one of the rails for our shooter. You'll find that everything is in even increments. You don't have now in Australia, we use millimeters. In more backward parts of the world, you may use inches. We tend to have things in multiples of 25 millimeters. And that means that we're able to have a jig or have a guide where we know that we can drill every 25 millimeters. We don't usually have things that are odd numbers of millimeters unless we are trying to accommodate for our good friends in the US who insist on working with 25.4 millimeter increments, also known as inches. So likewise, have all of your hole positions be standardized and use similar, or rather I should say, use the same dimensions for holes so that you can have one set of bolts, one set of tools. One thing that you can use is something called a jig. So that's a drilling guide. So you can get such a thing from the likes of Thrifty Bot or I believe Aussie boards. So that's the thing you see on the bottom that clamps onto your tube. It gives you a guide of where to drill. The other thing that we do is we use a drill press in a centralized process, so that you can set up a guide on the drill press, and that the one on the right, on the top right, is the exact one that we use. Down the bottom of that drill press, you see there's a little guide fixed to the base plate. We fix that to be the right length to drill the center of the tube. And so we slide our piece of metal along that. And so we're no longer aligning in 2 dimensions, we're now only aligning in 1 dimension. And that increases our accuracy a lot as well. Depending on your team's resources, you may either want to have a decentralized hand drilling process using a jig or a centralized process using a drill press. If you have a lot of people and a lot of hand drills, obviously go for a distributed process. But if you have 1 or 2 people who are very good on a drill press, you might consider going centralized. Finally, if you're on a budget, you want to buy more, not less. This means that, and plus you can accumulate parts. This means that you will be able to save money in the long run by having to do less. Now, you should also shop around to make sure you get a good deal. Andymark and Vex are great suppliers, but there's lots of other smaller suppliers like the ones I mentioned before, who do really good prices for things. Now, if you're very pressed for time, you can try outsourcing manufacturing to a local CNC shop. Now, we're going to be doing that this year, just to get more custom components. Generally, CNC services aren't too expensive, and if you design yourself well, you can actually make it cheaper because you can now afford to buy less expensive COTS parts. So instead of buying a Versaplanetary, a VP, you can now simply buy a belt and a pulley. So it also will help you manufacture by having fewer parts and less complex parts. Okay, so where does this lead us? Using all of the techniques that I talked about, this robot on the right here was built in 60 man-hours. So 2 days. We got all of the parts that you see on the right, plus maybe one more of what you see here, because the climber isn't actually attached in this photo. So this is about half of all of the parts we made. We got the entire thing done in 60 man-hours, or 2 days. So that's 2 days working 3 hours each. So 2 3-hour days, we managed to get all of this done. So just imagine over a season. So this is in total 6 hours for the team. We got this done in 6 hours. Imagine how much you can get done in a season. All right, that brings us conveniently to the end of our presentation. I'm open to take questions should you have any.
Yes, I maybe do have a question. I was wondering, do you have examples of how your team fills in the soft time for example, electronics and software during the first weeks of production until they're ready to test?
Yeah, that's right. So soft time, we generally follow a structure for soft time. So at the initial parts of the design stages, we tend to meet as a team. We want to discuss team goals. We want to make sure that everyone is on board. Everyone knows exactly what we are doing by making sure that the whole team is involved. Now, after we set goals and we do our robot architecture, so our big picture design, once that's done, we then split off. So software goes off and does their own thing. I'm not a software mentor, so I can't say specifically what they do, but my understanding is it's not something to do with computers. So I would imagine that they're writing up the code, they're looking through code from previous examples, possibly documentation from the suppliers for the parts that we use, and in general getting things ready so that as soon as the physical part is built, they can deploy the code and they can test. Now, on the mechanical side, as soon as the overall thing, big picture design is done, we will split off into our various sub teams. We'll go through look at past robots, because we don't really have much of a chance to prototype. So we'll go through what has worked in the past, what hasn't, look through examples, and CAD. And CAD is what's going to take up the majority of our time. We will CAD the first time, it'll go to a mentor or a senior student to review. It'll go back to the student doing the CAD, And this happens over and over again until we're ready, we're happy with the final product. When that happens, we work out how we're going to manufacture. We plan out our manufacturing. So before every day when we build, our production manager will say, okay, person A will be doing these jobs, person B will be doing those jobs, person C, and so on and so on. So, and we will make sure that everyone knows exactly what job they're doing before the build session. So as soon as the door to our workshop opens, everyone can jump onto exactly what they're doing.
Okay, thank you. Then I was maybe wondering, do you have any ways of making your electrical parts of your robot more structured, or yeah, do you have any ways of preparing for the modular design of the robot, and especially with electronics in mind?
That's a very good question, and I think that's one place where in the past we haven't done so well, but in recent years we've started to make inroads. One of the biggest things that we found was so important for elect is quick disconnect connectors. So those are the things like the power poles, and you can get power poles from AndyMark. Those things have made it so easy for us to attach and detach the elect board quickly. In addition to that, pardon me, in addition to that, moving to a CAN architecture as opposed to a purely PWM one like we've done before, CAN is much easier to disconnect from the rest of the robot, we found. And so that's something that's really helped us as well. Now, for the physical structure of the elect board itself, one technique that we've used is we have done a metal and aluminium elect board using Talon SRXs and Talon SRs, where we will CNC the elect board, we'll outsource that, and instead of using, say, double-sided tape or some other sort of adhesive or even cable ties, what we will do is we'll get a long screw, and the screw will go through the holes that are provided to you in the Talon SRX and the Victor SPX, and we will actually tap the aluminium of the elect board. So we'll use either an M3 or the Imperial equivalent, I believe it's a number 6. And we will tap the elect board, and we will blind fasten the motor controls to the elect board. So that if we have to swap out a motor controller, be that for damage or because we want to modify the function of the robot, you use an Allen key, you unscrew 2 screws, the motor controller comes out, and we can swap like that, and you can use the quick disconnect connectors.
Okay, thank you for answering the question, and thank you for your presentation. I think Renske, we can go to the next one.
Thank you.
Yes. We'll move on to the next one. Thank you.
Thank you.
Hi. So the next topic we're going to talk about is science fairs with Oliver Nichols from Team 3132. So the stream is all yours, Oliver.
Thank you. Just need to start my PowerPoint. Let's get this going. PowerPoint, this one. Sure. There we go. Can you guys see that all good?
Yep, we can see it.
Yes, we can.
Excellent. Thank you. Hello. My name's Oliver Nichols, and I'm from Thunder Down Under, Team 3132 in Sydney, Australia. And I'll be talking to you guys about my experience with science fairs or science and engineering competitions, whatever you guys want to call them, and how that has played between FRC and sort of the external competitions that I've been involved in, and where that's taken me and where that can potentially take you. So my inspiration to get into STEM originally, which obviously you're all interested in STEM being here, was a telescope. And you might have thought of a telescope looking like this. Some of you might have thought of one looking like this. All of these telescopes definitely inspired me, and this picture here is the Square Kilometre Array, part of the largest telescope in the world, a conglomerate of dishes in the outback of Western Australia. And being able to experience these and to be involved vicariously through my father is something that's definitely inspired me in getting out in the school holidays and trying to experience STEM as much as I could growing up. You all have, I had the fantastic opportunity of being involved in FIRST, as I'm sure you all have. And I am on 3132 now. I was also in 2014 and had the great opportunity to build skills and experience, which I took back to the team at my school, the Barker Redbacks 4613, and helped found that team as a founding student. I was involved for 5 years in all manner of mechanical and electrical, both as a sub-team lead and then as a team captain, building robots every year and developing so many skills that you'd be here all week if you tried to list them. Both teams provided me an excellent opportunity to learn from more experienced students, but also to give back and teach the new students that were coming through, and that's definitely played into who I am now and being a mentor and all that kind of thing. And I encourage you to, both as a sort of a senior student, to teach younger students, and also to always be looking to learn new skills and new areas. But you've got a passion for STEM, you're doing FRC. In some parts of the world, that's only for half the year. What do you do with the rest of it? Well, there's a whole bunch of science and engineering fairs around. Here are some of the ones listed sort of that are accessible in Australia. There's others that are state and national fairs in your countries, for example, Google Science Fair and other things. We'll come back to a lot of these, but I know you're all a big fan of Water Game, and so I just point out the Stockholm Junior Water Prize, which gives you an opportunity to do some water-based projects and potentially win some money or some recognition for that effort. Starting in year 9, sort of as a beginning of robotics, I started also working on projects for external competitions, science fairs. The state level science fair in New South Wales is called the Young Scientist Awards, and I entered my year 9 science project, essentially a model of a pulsar, and that, as you can see here, was a little model of a pulsar. You can see the robotics component sneaking in there, an anti-mark motor. So all the skills are starting to overlap, but also creating the opportunity for you to do more advanced projects than the classic timing, how long it takes a seed to grow kind of science projects. I had the fantastic opportunity to go to the national kind of finalist camp, which really inspired me to say to myself, wouldn't it be epic to come back in a few years' time in my senior year, year 12, and win an award. So I didn't win anything at the science camp at the national camp in year 9, but winning an award definitely provided some of that determination. So the hope to win an award provided some determination that we'll get into later. Year 11, so like second to last year of high school, for one of my subjects, we had it's called a mini major in preparation for our final year project, the major work. and that was a robotic dog ball launcher. Realistically, it was just to develop skills and prove that I knew how to use these technologies to myself and to my teachers. You'll see even more FRC related components here. You got the battery and a 888 and all the Andersons and the bag motors and things going on there. So it's definitely starting to all come together here, and we'll go into more about how the two worlds play into each other as we go along. Just a quick note on major works for me, just to kind of give it perspective and that. For our senior year in New South Wales in Australia, we have to do 6 subjects, and the major work is half of one subject. So what I'm about to walk you through is basically a 1/12 of my final mark, and you'll definitely see that it requires a disproportionate amount of effort to the marks returned to take your projects to the next level. But of course, that's what you really need to do, and it's not about the marks when you're doing a project like this. It goes beyond just that. So my Year 12 major work in a subject called Design and Technology was an autonomous window cleaning robot. And I'll walk you through the process and how I sort of designed that, hopefully to give you some hints and some ideas on where you can do with your own sort of projects. My teacher showed me this in Year 11 or so, and I think it's a fantastic way of understanding how you should go about developing a solution when you are trying to do a project in FRC maybe, but more so in broader science or engineering projects. Developing or identifying the problem and then expanding that, the avenues you have, and then focusing that back down into a problem definition, a brief, we'll get into that in a sec, and then expanding it back out again, double diamond style, to all the potential solutions, doing feedback, doing testing and evaluating, and then finally narrowing that down to a single solution. And you'll see that is what happens through my process. So obviously you need to follow the local rubric for whichever competition you're targeting or whichever one you want to enter. For me, being this is a school-based project, that was the first and foremost rubric that I was following, was the school's rubric. So, if you're targeting ISEF, which we'll come to later, if you haven't come across that before, it's the International Science and Engineering Fair, in my opinion, the epitome of high school level science and engineering fairs. You could be targeting that and then just make sure you align with your local fair so that you can qualify to get to ISEF. The first step is to identify the problem. And a great way to approach that is to think to yourself, what do I have that I can't have because it doesn't exist? Or what does society need that it doesn't have, again, because it doesn't exist? And in my case, I focused in on safety because I knew that in general, science fairs really favor sort of safety-based things that have a really meaningful impact to society. And so I identified that window cleaning is pretty dangerous. It actually started with a glass awning that at school where one of the cleaners slipped and fell and broke a bone, and that kind of really kicked off that process of how can we clean glass safer. And then obviously for cleaning angled glass, why don't we clean sides of buildings? There's heaps more of them, and that kind of process there. And developing that genuine need as an engineering project or reaching the edge of knowledge as a science project is super important and is quite possibly the most important part of the project. It doesn't matter how great what you come up with is. If it's not really needed, or if it already exists, then it's kind of, you're just copying someone else, or at least replicating someone else's work without knowing it. So researching what already exists is super important. Getting feedback from other users, super important. So going through here, you can see I've got my design brief up the top, and that was kind of channeling that all the research I did into solving the major problem identified and creating a succinct, approachable direction for me to proceed, with the project, because if you don't kind of develop all of that together, you can just get very lost and very overwhelmed. And that also comes hand in hand with the scope here. You'll see that there's a whole bunch of stuff that I identified that could be really helpful or really important in cleaning windows, but to be honest, I, as an individual doing a single project, couldn't develop that in the time I had. And building from these, identifying your criteria to actually figure out what needs to happen is the first step before you get into kind of any sort of design. Breaking it down into the functions and then understanding why it's important and testing it. To be honest, this is a little bit of fitting the criteria, but at least thinking to yourself these questions and understanding, how important is each of these things? How much do you value it? And that'll feed into the risk identification we'll talk about later. So furthering on degree of difference, it's super important to research the other options that are out there to help you both teach yourself, or at least identify yourself, what you're going to do that's unique and novel, but also to be able to communicate that to the judges or to your peers that might think, oh, well, that's sort of been done before. And as you see, there's a whole bunch of window cleaning solutions here, but not all of them are, well, none of them are widely commercially used, and there must be a reason for that, bar people cleaning it. And so diving into that and also kind of evaluating what people are doing is a super important way to narrow down the things that you need to work on in your project that's different to others. Also looking at patents is something that I strongly suggest. You can discover all sorts of interesting novel solutions and also things that are not yet commercialized by doing research in patents. There's great tools in Google patent search and also in the World Patent Search and your local area. For me, the Australian patent search system is a really helpful tool. Be warned though, it can get pretty overwhelming and you might end up finding some completely ridiculous translation from, for example, Chinese. I know that I found one that was really funny. It kept referring to its robot as Spider-Man. So you're reading the patent and you're like, why is there a Spider-Man on the building? Until you realize that it's actually the robot. So you never know what you're going to find with those ones. So risks to the project. And I realized that in science and in school, we love to be like, oh, how are you making sure you don't cut your hands? How are you making sure you keep your safety glasses on and all that? But there's two kinds of risks. There's the risk to yourself, and there's also the risk to the project. The risk that the project will fail and won't be able to succeed. And so I got sort of 3 steps in my process that I use, and I recommend you guys use this both in science projects and also engineering projects and also in FRC, and I'll explain how that can relate in a sec. But identifying the task and then applying kind of a risk to that. So how difficult do you think that's going to be? And also applying not a risk, that's the outcome of the matrix. That's the next step. Yeah, applying the difficulty and then the likelihood of needing it, or the importance, and that the importance comes from your criteria to evaluate success previously identified there. And feeding those two axes into a matrix, you get out a number. And by applying that to the processes that you identify in the task, you're able to plan your project to actually tackle these steps one at a time, which is going to enable you to make sure that if something's going to go wrong, it's going to go wrong early, which gives you time to recover. For example, it's kind of a natural tendency to leave the hardest things to the end, but that's really risky because if you can't make that work, then it's not going to be useful. I had concerns that I wouldn't be able to dry the windows efficiently after I was cleaning it, so I didn't leave streaks on the windows. And it's not necessarily particularly difficult, but if the simple solutions didn't work, it could become very difficult very quickly. So that was something I targeted really early on before, for example, I figured out how I was going to autonomously move around the window, because if you can't dry the window after you've cleaned it, it doesn't matter how well you move, it's just not going to work. And even FRC, you can apply this as well to processes in your mechanisms. For example, if you're making an intake, you might sort of narrow the questions you have to ask down to, like, well, how well does it pull the ball in? How well do I avoid jams? Is it effective while I'm moving? these sort of questions here that you can test, and putting those tests into some sort of spreadsheet, or those questions into spreadsheet, and assigning a test and identifying actually how you're going to evaluate that, and then figuring out which one's the most risky and starting there, helps you develop your robot in such a way that you're not going to get to after having this beautifully CAD'd and CNC'd intake that just doesn't work. You'll have already ironed out all those issues nice and early on, and that's one of the biggest pointers that I try and get across to the students on my team. And to be honest, it's a team. It's a team effort to be able to do that, and we all have to keep working at it. So now we've got a plan for the project. What are we going to do? What's the design process? So this is just a quick snapshot of the evolution of my project. You can see how it's sort of quite an a iterative process. And as you see on this slide, the very first one was wash, and that was the thing I identified as the most risky. And that was the first thing I tested. And you can see very quickly, I moved from a roller system to a disk system, and then from a single disk to a triple disk, and sort of get into some of those differences at the end if that's interesting. But by testing that up front is super handy. I'll point out here some of the powers of FRC components. We've got a versaplanetary in here that let me change the speed of the different components in the system and things like that. That was very helpful to be able to adjust and to refine in what was, to be honest, a single day. I could completely rule out one solution. And same with the hex shaft and all the components that fit really nicely together. It's much more difficult if you need to make a keyway and then get the right size shaft and all that kind of stuff. Having the standardized, and that's what the previous guy talked about, having standardized components, super handy, and something that you definitely take for granted in FRC, and I'll talk about it at the end. But when you move into the real world or the big wide world, it's kind of frustrating when everything's a bit different. Sketches are the place to start. They're absolutely fantastic. And you'll see here, I've got some sketches from my window cleaner and some sketches from the 2014 robot, the big exercise ball year. And, you can definitely see similarities here going through the mechanisms, just sketching out how I might build them, where things might be laid out, identifying key dimensions so I can start to manufacture things. And a lot of these ones were pre-CAD, particularly up to wheel spacing. That was pre-CAD. So being able to figure all this stuff out lets you get ahead in your design and not get bogged down with the super nitty-gritty CAD figuring out where bolt heads are going to go. But if you sketch it out, you can pretty quickly figure out, the bolt might not be able to come out through the spacer, and that's going to cause you grief when you have to assemble it or disassemble it later. So I strongly encourage you to sketch when you can, rather than CAD, particularly some of the simpler aspects, because it's just going to overwhelm you trying to CAD early on if you don't have a competent team of CADers, which a lot of teams don't have. Something that I found really useful with this concept of packaging was I laid out each of the levels of the robot that I had in my mind in a 2D sketches so I could see how things interacted. Packaging in FRC is a classic, being how do you fit your shooter, your intake, the other manipulator and a climber all inside the frame perimeter. Things tend to overlap in 3D space. So if you looked top down, you wouldn't notice, or you'd only see all these intersections, and side on, you wouldn't notice how a move could intersect in the depth plane. So making these 2D sketches is heaps faster than CADing in 3D, and also just lets you kind of play around with things and see how it's going to interact and pass through. And that's something that really helped me figure out what was going to happen. And as you can see, that relates straight into the wooden prototype on the right there, and that evolution of CAD, which related back to my process of building, which we'll come to in a second. Yeah. So again, you can see the iterations here, starting in wood and then developing, getting more metal, and then to a final metal product. You'll also see an evolution in the wiring. going from some pretty wild PWM splitters, which, side note, really suck. I recommend you don't use them unless you absolutely have to, right through to fully solid system with, you know, some good fun riveting involved. And that's something, kind of this evolution is something that at least my team is often afraid of doing. We don't like to build an intake or build a solution that might not work. So again, I encourage you to not be scared of testing things out and trying something out. As long as you obviously have a thought through plan, and this should be addressing questions and risks identified previously, but this lets you target and pivot and identify what's going to happen. Yeah, not get stuck in a rut, for example. Yeah, some more examples of where FRC kind of came into my project. You'll see here there's some Omni wheels there, which let me move both left and right on the glass, as well as up and down, which is something that, well, literally no other wheel can do without sliding and scuffing. So that was a pretty awesome find in terms of the FRC exposure to different industrial solutions. I got some ultrasonic sensors there, which you might have used. These are pretty classic ones that, if you make sure you have really great connections, work pretty well. Some polycord there, and some hex shaft and collar clamps and laser cut acrylic, all things that you'll find on many robots. And Anderson connectors, which actually turns out are super ubiquitous across industry, and definitely highly recommend using those, as mentioned previously, for quick connect and disconnect and things like that. Other concepts that you might, we got a 775 there, and on the bottom you can't see it, but there's a bag motor and a planetary gearbox. Other things that both I used from FRC and then fed back into FRC as I kind of built on my skills is wire management and an understanding of electronic interference and things like that. And that's definitely something that rewarded me for getting on top of it early, because not paying attention there can cause you all sorts of grief debugging. You know, why are my motors jittering and things? Well, turns out that running two PWM cables right next to your power cable is going to cause you grief, for example. Another one that I think is super helpful is being able to, sort of modularity, but not really. It's more the ability to access and swap out any component at any time. And the classic example of that is in a FRC gearbox, where you might put a bolt in and then put the next plate on top of the previous bolt, where, if you haven't thought about that ahead of time and left a port maybe to get that bolt out, you can really cause yourself grief if something happens in that end stage where you have covered that up successively over the course of the development. So I got a little video here which shows some of my testing, and I'll pause it and play it as we go through and talk you through some of what was going on. So yeah, you can see the motor there. Pretty classic way of testing. Really quick, just stick a piece of wood on a planetary gearbox and off you go. For example here, one of the things I realized really quickly with this great big disc was, well, how do you clean up in the corners? That's kind of not going to work. A round disc, a square corner, what's going to happen there? And that was part of the reason why I transitioned to using three discs in a bit of a zigzag shape, because actually they allow you to get much closer into the corner, smaller radius, that kind of thing, to the point where I decided in my value from my criteria that is an acceptable amount of window not to clean just in that very corner, which is typically out of the view of someone. You don't usually stand there and look out a window in the very corners. That's a bit unusual to do. So yeah, being able to harness some standard equipment and things to test what was going on. You can see here where we're proving out some of the technologies. I'm not sure how much thrust is going to be. they might have spec on the internet, they might not, but you're never quite sure how all the different interactions are going to play out. So both measuring as much as you can, and then understanding what you're measuring is super important. So here we're measuring the current, so I know that I can only apply a certain amount of current before my battery is going to be a problem. And also then measuring the thrust. Recording that on the camera meant that I was able to figure out what combination of propellers and shapes of the wood. You can see at the top in that T kind of piece there, a little bit of filing there to make it a bit more rounded, a bit more aerodynamic. We weren't sure how much of effect that was going to have. Turns out it was pretty minimal, but yeah. Some lovely shaky footage here. You can see that it's driving pretty well. In that previous clip there, it was driving pretty well. It got a long way along the glass there with the anti-mark wheels. But as you'll see here, as soon as we wet the glass, well, damn, that doesn't work at all. So that was definitely a bit of a wake-up moment there, and really drives home the point about you got to test all of your expected kind of edge cases, for example, because really, testing the wheels on the dry glass would have led me on a totally wrong tangent of trying to do something with like a pendulum and a single contact point in the top. But that's not going to work at all. That's not what we wanted to happen. It's this side. Where are we up to? Here. So yeah, transition to moving, sliding across the top. And you can see how we're changing it. We're pivoting our approach, or I'm pivoting my approach slightly, so it's not completely redesigning, it's just slightly adjusting, and that's the benefit of de-risking the project as you go. You can pivot without the huge risks. We might come back to the video at the end if there's still time. Yeah, so with that project, I then again entered into my state science competition. The fella with the exciting shirt there is Dr. Kyle. He is a very well-known science communicator in Australia, and I was fortunate enough to get to have a chat with him. And I also was again had the opportunity to go to the national level finalist camp for science and engineering, and was fortunate to win there. Definitely was something I targeted, and that's kind of the level I was targeting. I knew what I needed to do to get to the top of the national competition, and so I put the effort in to get there and worked really hard to be there. And had the opportunity to chat with the Larry Marshall, the CEO of CSIRO. It's sort of our version of NASA, but a bit smaller, a bit less well known, but still a pretty major figure in the world of Australian science and engineering. Yeah, so in winning the state and the national competitions, I got the opportunity to go to ISEF. The year I went, it was the Intel ISEF, International Science and Engineering Fair. And you can see it's a pretty huge hall. This is probably half of one of two halls, with so many students all demonstrating their fantastic projects. Very similar kind of feeling to Champs, to Worlds with FRC, where there's just so much excitement for STEM and for engineering. It's definitely comparable, and for those of you who have been to Champs and Worlds, you'll know how infectious that is and how kind of exciting it is to be there. And if you haven't been, I encourage you to try and get to Champs. To be honest, even if your team doesn't make it, it's pretty exhilarating, and there's some pretty awesome networking to be done to meet new people and to make new friends and all that, but also just to see some top tier robots if you're in that sort of area. But yeah, in ISEF, there is so many posters that one of the things that I'll come to in a sec is sort of how do you make yourself stand out? And you'll see in this picture, most people have a bit of a trifold with a desk and maybe their device sitting on the table next to a laptop or something. So, this is my booth here, and I took it a little bit differently. I created my own essentially table to demonstrate my robot, and created a poster which I felt was as engaging as it could be. And that really helped me stand out and helped me draw a bit of attention to my stand. Unfortunately, due to the way the rules are worded at ISF, I wasn't able to turn my robot on, but having it there was a really awesome opportunity for the judges to be able to look around and to point and to really get into the nuts and bolts. And speaking of judges, some kind of advice, some commentary, one of the biggest things that I was fortunate to be able to do was it was truly my own project. And so I knew all the things there were to know about it, but also I knew what I didn't know. I knew where my edge of knowledge was. I knew my black spots, for example, for expression. And that's something that the judges are looking for and really appreciate in being able to say, I don't know. And the classic example of that is I was asked about the software, and at the time I had never programmed anything. I basically looked over the shoulder of the person who I had helped me program my robot, but also being able to say to the judge, who, as it happened, this judge that came and talked to me about it worked on the Curiosity rover. They really was hoping to find out more about the software, but by being able to say, look, honestly, I didn't really do it. This is not my scope. It's not my kind of target. They had, they accepted that and they took that, and I think they appreciated that honesty of what's going on. And that's something that I encourage you, and maybe isn't so common for US competitions, but to be willing to say, look, I actually don't know. And going back to that, way back to the comment about scope, by having that really nicely defined and laid out, you can safely say, this wasn't part of what I was trying to achieve. And that's really a point in competitions where you can't be marked or judged on something that wasn't within what you were trying to achieve, or you less likely. One of the weirdest questions I got were actually about the frame, and again comes back to the judges wanting to know kind of what you did versus maybe what your professor or your teacher or your parent did. They were asking about the frame and how I constructed it. They could see that the construction method was similar to the robot. So instead of focusing on the robot, they focused on the frame, which I built that, so I was able to talk to it. But yeah, if you're not confident on your content, then that could throw you off. And that's kind of the key point in this is you are the expert on your project. You did the project. So, be as confident as you can and get people to ask you questions, be it parents, be it friends, be it even random classmates in lower years. One of the most challenging questions I had from anyone in the whole time, doing this project was a year 7 student. When I was in year 12, a year 7 student, first year of high school, asked me, what about the window cleaners you're going to put out of work? And that really made me stop and think about what was happening and kind of understand how to address that problem. And I don't remember if a judge asked me that later, but questions like that from completely outside perspectives really help you understand what you know and cement some of the great things that you'll learn doing projects. So I was fortunate enough to win 2 special awards at ISF. The second place NASA award, which is pretty wild, not being a US person, and also an IEEE award. I was further, completely unexpectedly, I went to ISF just to enjoy it. I didn't go with a goal of winning, as I was talking about before. In the national competition where I had a goal, ISF was so far above what I had dreamed of that I didn't even consider it, any sort of goal there. And I was fortunate enough to be one of the 2 first band, top band winners from my category. And then, to top that off, was a best in category for robots and intelligent systems. Something I didn't know at the time was that all best in category winners then go on to win a separate grand award. And they were calling out all these grand awards, and at the time I didn't know this, but I was the only grand award winner who hadn't been called out. And turns out I actually won the Gordon E. Moore Award, the top award at ISEF, and that's created some pretty wild opportunities. Not discounting the pretty serious prize money that was involved, but also media opportunities to network, and business inquiries, and all sorts of other things like that. I have gone through the patent process, decided not to fully patent my project, but went through the patent process and learned an awful lot doing that. Now I'm at uni at University of New South Wales, UNSW, studying mechatronic engineering. I'm in my third year of 4, and I'm now actually working at a really small startup who are developing, a robot window cleaner for high-rise buildings. So it's pretty incredible how that all crosses over. So just some other successes I want to talk about from people who I know really well. McKinley Butson on the left there with her smart armor, copper scale armor that protects the breast that's not having radiotherapy during radiotherapy, so that you don't accidentally kind of create cancers on the other side there. She won a pretty major prize at ISEF and has actually taken that on and is commercializing that, and is working with hospitals to develop that and prove that out. And she has a whole bunch of other really fantastic inventions that she's had there. And the other kind of standout for me is Lucy Lake on the right-hand side. She developed like a whale-inspired oar that reduces significantly the amount of drag the oar has to improve rowing times. And she was actually approached by the people who make the oars for the Australian Olympic rowing team, and they were in discussions, or are in discussions, about how they can incorporate some of her designs into their oars. So I hope my story has inspired you, has sort of given you another perspective, and helps you see things that you can potentially do different or better in both FRC and in extracurricular science and engineering competitions, and to think beyond just what you might be doing at school or what might be your state science fair, and really strive high and aim for the top level, because the skills you developed in FRC, they will take you so far, and it's really exciting. I might just click back to the video earlier and play the second half of that, because it shows my window cleaner in action. And then, if there's any questions, I'll come to that. Just lovely PWM signals that are super noisy. So testing things out and identifying what's going on. So here's the robot doing a bit of a dance. So you can see how I separated the left and right motion from the up and down motion, and then again from the kind of in and out of the building using different systems. I used a stepper motor at the top there to have control over the location of the belt-driven slider in the track, and that let me have some feedback on where the robot was in the in the window frame. And that's kind of the key of the ultrasonic sensors there, was to be able to identify where I was in the frame. Yeah. So that kind of wraps up what I've got. Are there any questions that anyone's posted or anything like that?
Yeah, we have a question in the chat. Question is, how did the ISEF judging process compare to the FRC judging process?
Yeah, that's a fantastic question. And I meant to touch on that, but totally forgot. It's remarkably similar skills and similar kind of involvement. I was never hugely involved in the FRC judging process, but from when I was in the pits, I was often like robot pit crew. So I'd hear the judges and I might talk to them about the robot, but I wasn't a chairman's presenter or anything like that. But knowing your content and having that question and answer rather than a prepared speech process was something that was really, pretty different from what you might do at school, where you're normally getting up in front of the class with a prepared speech and you kind of get your 5 minutes to talk. The judges interrupt you, probably within a minute of starting, and they're asking you questions to really flesh out what you've presented to them, because they've already read your poster, they've already read your kind of other materials that you might provide, your folio or like journal paper or something like that you might have. So yeah, it's pretty widespread what they might ask, particularly depending on your your project. But yeah, definitely the skills in FRC and that confidence you might build being a presenter or feed into both being able to answer questions at ISEF, but also interview questions at job placements and things like that. They're all skills that are super intertwined and very helpful throughout life.
So how did FSC actually contribute to what you're doing now?
Yeah. So the skills I developed in FRC with electronics and with mechanics and design definitely influenced my trajectory through both school and then university and the internship that I'm doing now. So some of the kind of interesting points in that journey are definitely around mechanical side of things. I always been very involved in the mechanical process at robots, and so having those skills in design and in fabrication, then being able to use that both to demonstrate those skills in an individual project, to then being able to take that to employers and to university and be like, look, I've actually done this before. You can trust me. That's something that the employers really value, and having FRC is awesome on a resume, but having it in an individual project is awesomer, for lack of a better expression. Yeah, does that answer that question?
Yeah, I think so. We've got some more questions in the chat.
Awesome.
Do you think this award is a gateway to great universities/colleges?
Absolutely. In the US, ISEF can change your college trajectory. There's a heap of scholarships available, similar to how there's a lot in FRC. There's a whole bunch of scholarships available. There's a lot of scholarships as prizes at ISEF, but also for the grand awards. So for the top prize I won, that money is intended to be used for education, and is enough money to pay for a pretty top tier university in the US. I was actually, because of the way Australian school timings work out, we start in sort of January. We start our year of school. So I had already started university by the time ISEF came around for the project I'd done the previous year, and so I wasn't changing universities, but that is definitely, it definitely creates opportunities and can get you in the door. Like, I got a whole bunch of letters and messages from people trying to encourage me to come to the university in the US from some top schools. And so, yeah, if if you're someone who is looking to go to a top school, then doing these individual projects can both literally create opportunities from scholarships and from networked, well, not recruiters. I can't remember the name of the kind of enrollments people that you guys have, but but also just by having that extra skill to be able to demonstrate on a resume or on a portfolio application or whatever the process you guys apply through is.
Okay. Then we have another question in the chat. You mentioned earlier that in industry there's a lot of options for parts. How does this differ from FRC?
Yeah, that's something that has really been something I've hugely learned recently in my role at the moment, building another window cleaning robot. It's a very small startup with myself, another undergraduate person, and my boss being a business and marketing and other areas, but not engineering per se. Getting out and sort of identifying, the classic example is bearings. In FRC, you go to the bearing cupboard or the bearing box you might have, and you look and you see you got a hex bearing, you got maybe a 3/8 hex as well as a 1/2 inch hex, maybe a round for thunder hex, and that's about it. If you're really lucky, you might have some specialty bearing you've bought for a custom gearbox or something. But in industry, you go online and you're looking for what bearing you need for your application, and you drop down the website list, and there's 11,000 different bearings. So from personal experience, I can say it took me about a week to go from being like, oh yes, bearings are simple, there's 3 options, to actually learning all the different things about bearings to be able to choose a bearing. And that's just something that I think, and maybe it's just like everyone in engineering kind of has to have that, oh wow, there's lots of options moment. But that's something that really surprised me and led me to learn a whole bunch of new information, new skills I didn't already have. And that kind of difference extends to connectors, extends to wiring, extends to software languages. Everything, there's just so much choice. And that can be a liberating thing when you're like, oh damn it, I wish I could use, before Falcons were a thing, wish I could use a brushless motor. But it can also be scary when you realize how expensive some options are, or just, you're paralyzed by choice.
Yeah. Then there's another question.
Mm-hmm.
How has your FRC/ESEF experience impacted your university experience?
Yeah. It's definitely something that has fed into the bigger kind of building projects, like group projects at uni, where many people are coming from school having they've done excellently at maths and excellently at science, physics maybe, but they haven't really had an opportunity to do a project or to do some other kind of self-led or physically building something kind of sort of projects and education. And that's definitely led me to become team mum, some might say, project manager in the team at the various university group projects, and also in individual projects, being able to kind of break down a criteria and tackle that in first year rather than having to learn that on the fly was something that was really helpful. And one thing I will add kind of more broadly is that the way FRC approaches the rules, in that half the time the rules are there to be not just worked within, but sort of worked around sometimes, is a handy skill to apply in uni and in the workplace and things, where maybe not in the workplace, but in uni for sure, where you're trying to work within the boundaries, but also see beyond those obvious boundaries and try and come up with novel solutions.
Yes, thank you. Then I have one more question. What advice do you have for students in FRC, and more specifically, what advice would you give viewers right now if they want to start doing what you're doing?
Yeah. So like, I'll talk to that kind of in 2 different tangents. In terms of starting out, you're clearly here interested in STEM, involved in FRC to some extent, and you want to strike out and do an individual project. This year is a bit different, and I'm not 100% sure how the innovation kind of projects work. I'm not particularly involved in that, but some of those could be something you could start with to investigate as a small part of your team, developing a solution to whatever problem that they present. I haven't really looked into that, but beyond the FRC related ones, as an individual or as a small team of 2 or 3, identifying a problem that you see around you, be that like a problem that technology can solve or a science-based problem, and researching that and being passionate about that to try and actually come up with a solution for that problem, and then develop and build that solution and enter into your local science competition multiple times. You're never going to win. Oh, I won't say that. You're very unlikely to win the first time. Most people who end up going to ICEF go and do well go multiple times. I definitely was a fluke personally. Most of the other people on the stage who won things had multiple years of ribbons on their jackets, and so yeah, taking that kind of that idea you have or that injury. I remember seeing a project that I judged this year as a guest judge at my state competition. Someone's mum had chemo, and they weren't impressed with the way the cold caps work, so they tried to develop a new solution to that. And to be honest, in my opinion, came up with a really awesome solution, and I'm pretty sure they were rewarded for that awesome solution. So yeah, looking in your life and more broadly to society, trying to come up with solutions there. Also, if your question was more related to getting into mechatronics and robotics in industry, one of the biggest things that I found is going to a job interview or to an employer with some examples of work you've done individually and in the team is put you a huge leg above someone, even who comes with a maybe 10. Is your mark out of 100? Let's call it out of 100. If your mark's out of 100 for uni, then if someone comes in and you've got an 80 and they have a 90, if you can say, yeah, look, here's a video of my awesome robot that I made in high school and my awesome project I've done also in high school or after high school, they're going to look on that really favorably and potentially, discount some of those or give you additional points in their mind that might put you on par or even ahead of some of those people who might have higher marks just from being super brainy.
Yeah. Okay. Then there is one more question that actually popped up. Out of so many projects, out of so many projects on the science fair, what do you think led the judges to choose your project as a winning project?
That's a really tough question. I know that I put a lot of effort into drawing their attention both to the things that I thought I had done really well with my stand and with my poster. That was focusing their attention onto the things that I thought I had done really well and finding a real solution and actually working on that as an individual and acknowledging the assistance I received. I think that was taken really favorably. I know that there's a lot of judges that really try and try and dig down into what you did as the individual and what you received help with, because it's hard to separate as a high school student. It's hard to separate maybe what you did yourself versus what you got help from a parent or a teacher. But at ICEF, their role there as judges is to identify who's done the best job, but also who actually did the job. And so being confident and having done that myself, I think that really helped. And I know that one judge I spoke to was really impressed with the risk process I used, and I think that showed how I had actually thought through the process and really followed a good, robust engineering process rather than just throwing myself at the problem, if that makes sense.
Yeah. Okay. think that's all the questions we have. We have 4 minutes left. So what would be your next step? What do you like do any more side projects? Like, is this no, wait, let me just reformat that. Let me just see here. Yeah, is there we got some yeah, I think that's all the questions we have. Yeah, no, I was looking for something in the chat, but it's yeah.
Well, you sort of mentioned you got a couple minutes, and you were asking sort of where to from here for me.
Yeah.
I am now working at a startup, and something I haven't had the opportunity to experience, but would love to, and inevitably will, is working in understanding how the world of a startup is different to the world of a established, research and development department in a big company, or working in a bigger team with more robust systems, developing solutions that go to market a bit sooner. That's something I haven't had experience with, and I would like to. Also, in the super near future, pretty sure you guys would do theses at university. For engineering in Australia, you have to do a thesis. So that's in the next year for me. And I encourage you also to investigate things that might not be obviously your passion. This year I did a subject on nuclear engineering and a subject on cybersecurity. And despite not being my passion of robots, I found them unbelievably interesting and kind of changed my perspective on how I do things. So yeah, just try things out that sound interesting, and it's definitely something I could encourage.
Okay, thank you for your presentation.
No worries. Thank you.
Yeah, that's all the questions we have, and I think we're going to move on to the next presentation. So thank you again. Yes. Well, so next is James, who can be affiliated with the Blue Flamingos, with mechanical mechanisms for moving matter, if that works. So, hi, James. Did you... Hello, James? James is connecting with audio. Let's wait 1 second. There he is.
Hello.
Hello, James. So, we're ready for your presentation.
Understood.
Yeah, whenever you're ready.
Yep, I'll share my screen if I may.
Yes.
Is it visible?
Yep, it is.
Cool, all good to go.
Sorry?
All good to go?
Yeah, whenever you're ready.
Yeah, nice. So, hello everyone. This presentation is about simple mechanical mechanisms that one can use in all robotics applications or any mechanical application for moving an indexer, for performing any sort of task. It's a lot of the basic principles behind what ends up making up pretty much every single mechanical solution for all purposes. So yeah, that's what this presentation is about. So starting with linear motion. So this is moving along a single axis. Don't get much more simple than that. So there are quite a few reasons why one would choose to move in this way, whether it's for whatever specific task, specifically, practically as well. A mechanism that only moves in one axis can generally be made quite durably, because you only have to deal with that one axis in regards to resistance to impact or load. And so you can have often a large contact area on that physical mechanism. If you want to stow a mechanism, this is a great way to extend it or retract it in a simple manner. And also because of the fact that it's only going in one direction, it's able to accelerate and decelerate quite reliably and faster because the forces are easier to predict and easier to handle. We'll also comment this presentation is framed specifically around, because it's applicable for everything, but it was initially intended for FRC applications. So a lot of FRC machines will be visible here. This is for those machines for the first robotics competition, as they demonstrate a lot of these principles quite well. So yeah, in the corner here, we have Team 971, an American team. Their front intake, which collects balls, is at a slight angle and extends downward because you have to start within a perimeter. And it's a great example of that. It has a large contact area in which when it extends, the two sliding parts still have a large 2 points with a large distance between them to prevent any flex or movement. It's a great example of a use of a linear mechanism. So the simplest way to move in a single direction would be using a spring or elastic band or something similar. And obviously you can create this energy by extending or whatever it is to put that energy into that system. But it's about the controlled release, importantly. This can be through a latching mechanism, or if you have a gear, for example, that is on a cam that pulls back a spring. If it is missing some teeth, when it gets to that point, it will spin back real fast and release all that energy in one go. That can be used for a timing shooting or something like that. There's numerous ways in which this can be done. I won't focus too much on that here, but that's definitely a way things can be done. By far the mechanically simplest way to move on a linear axis is through a pneumatic system. So this is where you have a cylinder with a rod and piston, of which you can pressurize or depressurize internally to a different pressure to the atmosphere surrounding it. This creates a force pushing on the piston in one way or another. If you have pressure going into the cylinder in relation to the atmosphere, it will generally extend out as that internal volume wishes to expand. Generally, you only have two positions you can go to with pneumatics. It will either be fully extended or fully retracted. Some cylinders do exist which permit multiple stages of movement, but they're quite expensive and they're generally very specific and you can often work around them. They're very mechanically reliable due to their simplicity. The only thing that can really wear out are the seals, and those can be made quite well using bronze or brass or something similar. And you can have magnets embedded within the piston head itself in order to tell its position. And so, yeah, they're very common, they're very simple. The complexity comes in powering these pneumatic systems. Yeah, that's what we're going to talk about a bit now. After this, a cam mechanism is the oldest way of converting a rotary motion into a linear motion. And so when you have an electric solution and you don't wish to have the complexity of pneumatics in the back end to power the pneumatics, you need a compressor, some form of solenoid in order to control the direction of flow, storage, and all that. So electric motor is it moves a lot of that complexity to the motor side, but the overall complexity is reduced. If that makes any sense, which I don't think it does. So you end up with having to turn a rotary motor motion into a linear motion, which is what we're going for here. A cam is, again, by far the oldest. And you can see in the bottom left graphic, one setup which that may be, with the red dot in all of these images is what moves linearly. The one thing which may be the advantage of this system if you want for that specific application, but in this case we consider it a disadvantage, as the cam rotates, that bar straightens or goes higher or lower, which changes the speed of linear actuation for a fixed rotary motion. It can be used to an advantage when it's perfectly straight. You have a theoretically infinite mechanical advantage. As soon as it moves, obviously that reduces exponentially. But that can be used for whatever application, but they're generally not as common due to that very predictable, but perhaps unwanted change in speed. On the right, we have a chain and sprocket, which can be a belt and pulley. It can just be two wheels and elastic bands. There's many ways which this can be done. So you can see the red element is what moves across. And generally, will pretty much always have to have some sort of fully wrapping round belt or chain. There's not many other ways to do it there. It's very strong because you can make it very simple with just 2 pivoting points. And it's got that really controlled motion. You can have it very precise. You can have it, if you build it well, you can have it output a lot of force. And if you make it with belts and the like, it can be very light. But generally it's more complex and difficult to construct because you have to have a point of rotation further than the end of the linear motion. And so it's not really great for extending very far because you have to have already, reached that location effectively to move, the red dot to there. Similar to the chain and sprocket, a rack and pinion can be used. If you're done properly, it's very strong, very durable, and can be super precise. The only disadvantage of this is obviously you have to have a gear and then a rack cut very specifically. It's quite a complex shape in those teeth. But obviously the gear is the rotating part and the rack is the linearly moving part. Again, you've got a nice smooth motion. It can be fast, it can be slow, it can be outputting a lot of power depending on the size of the gear, because that's effectively the lever advantage you have against that rack. Expensive and hard to manufacture, but if done well, is probably one of the most reliable and strong method out of these to get a linear motion. But you have to also mount the rack very well, so yeah, very complex. Screws on the right one can be seen. I often use in machinery because the screw, depending on how it's cut, can act as a very high gear ratio to get a very precise and small amount of movement for a single rotation. So they're used in machinery for, say you've got a lathe for moving the gantry across in a very precise manner, as I said before, or getting a high amount of power out of it because of that high gear ratio. The threads can be quite fragile though, they're expensive to cut. And because when you turn that thread, you're trying to fight the thread's motion in order to permit the bit that sits on the thread, I forgot what that's called, from moving. And so if you're going to make it rotate, you can either use bushings, but if you can use bearings, they have to be thrust bearings, which can be expensive again. Often this comes down to expense. But yeah, they're pretty compact too. But again, you have to have already reached that location in which you want to move something to. With a rack, you can sort of just suspend the end and have it stick out. All things to consider depending on the application. Now we're talking to more practical methods. If you specifically wanted to move something in a straight line, a linear actuator is a very reliable and strong way. You can buy them for pretty cheap. That can lift over 100 kilos. Got 2 mounting points. It all depends on what you end up buying, but it's an electric solution as well. It's all single compact. Often they're used for robotics because of that electric control, which is, if you're making a machine, you're generally going to have an electric system there. They can have built-in limit switches to sense when they have reached the end. Generally pretty good all-around way. But an even cheaper way though is to use drawer slides. So the same ones you have in your sliding drawer on your desk or the like. They can pick up ones that can hold 45 kilos, can be picked up from, in Australia we've got Bunnings for about $5, $10, and can extend to double or more of their initial length. But they're generally only really strong in one plane. If you were to load them sort of straight on, they have quite a large loading capacity, but if you were to rotate them, they'd flex quite a lot. I don't know if that sort of idea can be seen from the image, but you can see the rails are only on the top and bottom. If you were to rotate it 90 degrees, it would pop out quite easily. Talking about expense, the most compact and strong way for the weight of doing this is to have a tube inside of a tube, because of the way the circles will mesh with each other and with a very even distribution of load. If you were to make this yourself, you'd have to be pretty good at machining stuff, or you can either purchase it, but then you'd be making a pretty expensive purchase. You pretty much have no movement other than the intended linear axis, and it's all evenly strong, if that's the correct wording, because it is a circle. And an example seen in the bottom far left, on the left and right of the pneumatic cylinder, you can see a tube in a tube sort of start like how it would be positioned. And to the right of that is team 6986, I believe, or 6986. They had in 2019 on their FRC machine a carbon fiber tube elevator, which was very strong and very light, but obviously quite expensive to manufacture. So that's sort of you can't really go much further in regards to the material use there. It's very impressive to see that done. Again, more down to practical stuff. Bearing blocks can be made to ride on any rectangular shape. Thus, it's pretty cheap because you can buy rectangular extrusion and the like. Yeah, pretty much anywhere you go. I don't know what hardware stores around various people. Therefore, it can be made with hand tools. The bearing blocks are really, really good at taking loads in the direction they're designed to, but it can just pop out in one direction unless you capture them, and then it becomes more expensive to make. In reality, you sort of got this four-sided square, well, you got this square at the bottom. It's either light, low cost, has a high extension ratio, which is what we were talking about before, where you can only can't extend further than you've already gone, or you can extend twice or more that, or you can have it strong. You only get 3 of those. There's pretty much no scenario in which one gets all 4. You can have it weighted towards one or the other, but that's what one's always competing with, the strength of it, how far it goes, and the low cost, the low weight. So for example, of the draw slides, they're pretty strong, they're pretty cheap, they double their extension, but they're pretty heavy, they're made of steel. That box, that nice carbon fiber tube, it's really light, it extends to over double. It's nice and strong, but it's really expensive to make. So just what someone got to pick out what their sacrifice in that mechanism will be. Cool. Next section will be rotary motion. If anyone has some questions on that last bit, this would be the time to take them.
I don't think there are any questions yet, so
All good? Yep, happy to continue.
Yeah, we'll do maybe
question at the end.
Questions start rolling in during the presentation, so maybe we can go to them at the end.
Yep, sorry, understood. If that's how it's been done, that's no issue.
No problem over that. That's okay. You can continue.
Coolio. We'll move on with the next one. So next is rotary motion. As we talked a little bit about it before. This is when you have a fixed point and you are moving in a fixed distance around that point. That's pretty much it. All mechanisms are made up of some combination of linear, single axial motion, and rotary motion. And therefore, if you've mastered both of those concepts, you can pretty much do everything. Reasons why one wish to rotate rotarily. It's very simple. In the real world, you can have a bearing or a bushing or none at all. Yeah, that's better. It's simple. There's not much to it. It's quite versatile. Levers, gears, they all function on this principle of rotary motion and the ways in which they relate to each other. Gearboxes permit a very large amount of power output for the weight compared to using another pneumatic solution, all made because of the ability for something to rotate around a point. Again, it's sort of in relation to the first point of the linear solutions, is that if you wish to stow something and you can't just move it along that single plane and you want to rotate it, that may be the reason for that. The simplest way to do rotary motion, because it's just output directly, is using a motor. Your motor outputs a torque. Gears, sprockets, pulleys, all of these transmit torque. Torque is rotary motion in this sense, or the ability to move something rotarily. And again, gearboxes permit the variance of torque and rotational speed. It's generally a trade-off for one or the other, depending on how you've set that gear ratio. And if you can have a rack and pinion mechanism, as described before, rather than the rack being perfectly flat, it can be curved. In effect, it's a section of a gear. These effectively provide a rotary motion around that singular point. But yeah, not as many use cases for that, but yeah, it's just a section of a gear at the end of the day. In the right, we see quite an old machine from FRC, and here there is a multi-axis arm that is stowed here. So it is unable to be stowed to reach as far as it does. They couldn't stow it in a straight line, so they've got an ability to fold in 3 points, it looks like, with a wrist for the intake. Very obviously beautiful mechanism in that sense, but one can also see the belts and pulleys, or the chain or the wire sort of thing, and the pulleys that enables it to transmit the power further up the arm without having the heavy mass further up there. Yeah, beautiful machine as it is. Here are two more machines that use rotary motion in its various forms as discussed. On the left, we've got on the upper right of that machine a gearbox that is used powered by a motor. It reduces the rotational speed in exchange for torque. This is actually used to extend the arm of this machine, which moves in a linear fashion. All these photos, I'll say, is a property of Team Spectrum. These are taken from their website. So if you're looking for more information on those, that's the place to go. Back to that left image, it also rotates, powered by another gearbox, which is visible on the front of the machine. Wheels are the simplest and oldest form of rotary motion, used for basically everything. Yeah, very nice machine there too. And on the right, you can sort of see here, this image is here to demonstrate that curved rack idea mentioned before. You can see a silver curved piece of metal. This enabled the rack to be curved in. As it extended out, it would move in a certain way to raise the machine up, and also permits stowing in that special orientation to have the lowest form factor possible. You can power a rotary thing with your pneumatics, sort of in the reverse of the ways that things were discussed before. You're again exchanging the simplicity of a pneumatic cylinder for the complication of mechanical complications of getting rotary motion out of that. It's got the 2-position control, which can be very good if you just want 2 positions. It will always go to that, and unless it's physically stopped, and return from it. So you don't need encoders or any electrical solution to control this. In FRC, many intakes are out or in, for example. And so if you only want out and in and never looking for anything in between, it's a great way to do that. Cam in reverse is a great way to do it, in which one lever of that cam extends or retracts. As you see at the point of the moving component, that's where the rotary motion will be. And you can use a rack and pinion in reverse. It's seen on the front side of this FRC machine. This one's by Team 118. It's very effective at doing that. You get a constant torque, while on the cam mechanism you have a varying torque. This again deploys the intake to a 2-position control. You've got the same disadvantages though, because you're using a rack and pinion, but it's very compact and quite light if done correctly. Winches are very ubiquitous. They're used in many things, and have been used for a very long time. It's using some flexible coil rope in order to put tension on that, and that can be used for whatever you really need to in a linear manner, often in some form of elevator, and 3 forms of that are viewable below. The winch coil can be seen on the left. In the center is a very complex rigging for a multi-stage elevator, which is mostly just for interest. On the right, it can be seen in a more viewable manner. It's very cheap and very simple, and if done correctly, quite light, while you're moving a heavy mechanism a long distance. I'm using electric power, so you'll need to have a motor and some sort of gearbox in order to power this. There's not much reason to use a pneumatic solution. I'm sure someone could reason one. You can have a double wound spool that can pull both up and down, but that's more into elevator theory and the like. If someone needs that, they can definitely look into it. So 4 bars. This is sort of moving into slightly more complex uses of the rotary motion. You have 4 linkages, 2 of them are parallel and 2 of them are parallel to each other that way. These will, if they're all joined equidistantly at 4 points, it will keep those in parallel as they rotate. Often this can be fairly heavy and require a lot of power to move. But it means you can, if you're looking to keep two parts parallel as it rotates, it's the best way to do it. It's mechanically the simplest. There's something called a 6-bar, which can be looked up, often used in the VEX competitions to gain extra height, but not used very often in FRC or other applications besides that. On the right, there's a little animation of this 4-bar concept. On the left can be seen a 4-bar used slightly differently, where a winch pulls down the rear of that linkage sticking out the back, which pushed up that front linkage and enabled to the arm to swing up and down in parallel with that pulled on bar and extend out quite far as that entire mechanism retracts inside of the blue bumpers when stowed. An acceleration link is sort of compounding this, but using different size levers rather than having them all the same size in parallel. It's just 2 levers sort of coupled together. Enables a very large amount of movement for a very large input force, obviously, that is in relation to that movement. Not used super often, but definitely possible. One thing which I don't see used very often, but absolutely could be, is called a 4-bar mechanism, but it's used for the purpose of acceleration. Furthering on this concept before of using 4 bars with different sizes and the like in order to gain different effects. This one is in a different style to the last one, where this motion enables the end of the lever to flick up in some manner rather than just accelerate. Using different bars, different arcs can be achieved. In the middle here is a super heavyweight combat robot weighing in at 150 kilos. It last fought, I believe, in 2007. But visible right in the middle of the image, one can see the 4-bar mechanism with a cylinder inside used to flip up opponents. We'll see pretty much right now how that is done. Cool. So the purpose of that was so one can visibly see the way in which the 4-bar mechanism is able to accelerate at that tip and have a sort of arcing motion that isn't really possible with any other mechanism. This is sort of a bit of an abstract use of levers, but definitely is very useful to know how to do. Also note the hammer of the other machine. Underneath that hood is powered by a rack and pinion with a very small pinion to enable it to reach a very large rotary velocity for a given linear motion, which is also powered by a pneumatic cylinder. So being able to apply these concepts as well into moving things, we have intakes. All machines that manipulate an object will have some form of intake, and there's many different types of objects, and here will be a couple of ways in which to manipulate those with the concepts we've just discussed. So balls are very common. They're very easy, difficult to grab a hold of because of that round shape, but they're easy to roll. Therefore, 2 reasonable methods knowing this is to have a powered roller on one side that rotates and a friction plane on the other to roll the ball. It generally has to be compliant because otherwise, if you have it spaced perfectly, you'll in theory only be contacted with it for a very short amount of time. So in order to combat this without that compliance, is to have 2 powered rollers either side to grab the ball. A couple of ways of doing this are visible at the bottom. The machine in the middle and the left of the same machine. You can see in that center photo on the left of that machine, there is a orange roller. The ground is the friction plane in this sense, and that roller spins to pull the ball in. It is compliant and bounces up, which falls into, which is visible better on the left, a dual roller system to grab it and hold on to it a lot better. And on the right, you've got a vertical dual roller system using belts doesn't have to just be a wheel. It can absolutely be belts or something similar in order to lengthen that contact. Yeah, 2 ways of doing that. Cubes can't be rolled. Like, you kind of can, but not reasonably. So you have to slide them. Unlike balls, though, they're easy to grip, and thus claws are a much better option. You can use a claw on a ball, but it's not really used very much, and there's much better ways of doing things. To pick up cubes, you can use a double roller like before. This is quite good to easily pick up the cube as it doesn't care for orientation, and also launch the cube if that's your intention. But you generally have to be pretty compliant, as the cube, depending on its orientation, will have different total dimensions in that plane in which the 2 rollers would be grabbing it. Claws are naturally compliant as they close. They can't self-center easily. So if that's not required, then claws are great. They're very simple. And they can't just launch a cube if that's the intention to. Because if you're going to collect an object, for example, or manipulate it in some way, you'll have to release it at the end. Single top rollers can be successful. Team Upper Creek Robotics in the 2018 FRC competition did this to collect cubes from the ground, as it just slid the cube as discussed before. But yeah, it's fairly difficult to do, and they spend a lot of time making sure that mechanism works. To manipulate discs, these can be rolled or they can be slid, depending on the orientation. So therefore, you can combine all of these methods. You can have a top roller and a friction plane to slide the disc along a flat surface. Yeah, so you can also do this sort of if it is vertical, but that's sort of the point afterward, in which you have one roller on a side and a friction plane on the other in order to roll it. So you can pretty much, yeah, you can do that in 2 different ways. It's really just the orientation of the disc at the end of the day. Or you can have 2 rollers, one either side, to slide it linearly, top and bottom side. You can either act as a cube or you can act as a ball, depending on what orientation you want that disc to come in and what the dimensions of that disc are. Maybe better to do it one way or another. On the left, we can see some rollers. These would extend down onto the ground and slide a disc. I was able to center them and pull them in. So that's the case in which you're moving a disc from that top lane. And on the right, you can see a friction plane surface around the edge and a center wheel that would roll that disc around that curve there. This enabled to have a very long contact with the disc. And so these are pretty much just 2 methods of doing really the same thing at the end of the day. It's just the method by which you actually apply it. So a bit less common, but definitely just as capable, is a spaghetti intake. These sort of have, some form of floppy noodle, whether it's rubber or something similar, that uses, so the noodles are compliant, and they sort of just apply forces to the object and just nudge it in the direction that you want. The faster you, and this is done generally by taking these compliant objects and rotating them to sort of thwack the object as much as possible. The advantage of this, though not particularly controlled, not particularly powerful, is that it does not care about the dimensions of the object or the size, as long as it's within the size of the intake. Because of that low power, though, it's not very good on heavy objects or those that have a lot of friction with the ground, because it doesn't apply much force to the object. But if you're trying to collect multiple different sizes and shapes of the object, or you're unable to predict that, then this could be an effective way of doing it. The machine on the middle and left, it's a bit hard to see. They've got large black floppy pieces of silicon rubber. These would spin horizontally to nudge balls towards the center of the machine to collect them. And on the right, we have a vertical spaghetti intake that was able to collect both a cube and a ball in this specific case. So yeah, again, they're not very common, and those floppy components do eventually wear out, but definitely a good way to do it. So in summary of this short component, there are many mechanisms that you can do to perform a single task. It's down to the team to implement it, or the individual to implement it particularly well. If you're going to design anything mechanically in any way, it's really important to have it as simple as possible, whether that be electrically or mechanically, and sort of decide where that complexity is going to be. If you're able to combine functionality of a mechanism, whether that's to use, as we saw before, a top roller to pull in the object from the ground, and then 2 horizontal ones to hold onto it, or something similar to that. It's great. That's a good way to use 2 different simple mechanisms rather than having one complicated one. Testing, prototyping, and developing it, and exploring different ways of using that mechanism. Seen on the right here, it was a challenge in the 2019 FRC to have a robot reach a higher platform. The machine on the right was a ramp, so the idea is the machine would just drive up it. For some reason, it was unable to do the center platform, so they shifted over, and another machine jumped the gap and landed on the lower level. Not the intended use, definitely interesting. I find it quite amusing. Yeah, an alternative use of a very simple mechanism that was able to, in this case, fold out using a rotary system. So that's the end of this prepared presentation. This is probably, from my understanding, the time in which questions can be asked and answered.
Yes, I don't think we have any questions yet.
Yep.
So, is there? Is there more on the presentation?
No, that's it for the presentation. I was asked to cut it down from last time, and that made it a bit too short than it should be.
Okay, no, that's fine. What's your favorite game piece?
For the FRC games?
For the FRC games, yes.
Right. So I've been involved in the past 2. You've had a small ball, a big ball, or a disc. When you have there's more ways in which one can manipulate round ball objects. So I'd say that's probably been my favorite one, because of the complexity of machines that you end up with and all the different ways in which a single task is achieved. So yeah, I'd take the ball.
So, from all the games you've played in FRC, what mechanism really stands out like your favorite? Do you have something that you're really proud of?
Or for my team?
For your team or any team that you might have seen?
Yeah, I'll actually, while we're here, I'll break the illusion and I'll pull up the longer presentation, because there is an element of that in which can be used to demonstrate this quite well. So that the team that I actually brought up a few times in this presentation that just did was the team with the orange machine. It's literally just called Team Orange. Their machines, I think, are a great example of combining the simple mechanisms to achieve a task in a very impressive, and it looks very complicated, but at the end of the day, it really is quite simple. They have the horizontal roller on the top and the friction plane in order to roll a ball object, as well as collect it with the horizontal rollers. We have 2 videos here which I think will demonstrate that quite well. This is what I cut out of the last presentation, but I think it can be viewed here well. They also have their intake is deployed in a 4-bar fashion using a rotary mechanism, but it is powered by pneumatics for that 2-position sort of accuracy that they get. Very simple. And what will be seen in the next video is that arm as well is able to extend. I think it'll be at the end of this one. But yeah, you can see here the wide intake is able to collect balls from the ground, but the positional accuracy comes from that horizontal roller there. And here you can see the arm extends. So yeah, all very simple mechanisms at the end of the day, but combined to create a very fluid moving machine. Given that we actually have the time, not quite as ordered as before, I think I'll go back through the longer presentation and find the more interesting aspects to demonstrate.
Yeah, that would be fun.
I'll go through the case studies that we were looking at before. So here's another one, Crescent Robotics, from the 2018 game. Hang on, can I go into full screen here? There we go. So this is the game of cubes. So a completely different challenge in relation to these boards, which you saw before. The intake has two rollers that are the rollers themselves are completely fixed. They are unable to move, but the wheels themselves were squishy and enable the cube to center itself when in contact with these wheels. Very simple, durable, great example of a simple mechanism done well. The arm on the machine was a single hinge at the back, which rotated up and down, and enabled for lots of adjustability to launch cubes. Again, simple, durable, and effective. The climber was much more, in construction, quite complex. Uses square tubes rather than round tubes in order to extend multiple times its initial length, almost 4 times its initial length. It's got a large extension ratio, it's durable, it's fairly light, but as we saw before, the cost of that is the monetary cost or maybe time cost in text to machine this. So you can see here, example of how that was done. Or turn off the music so there's no copyright claiming or the like. So it can be seen folding up and down there where let's see if I can go back to there, freeze it for a moment. So briefly folding up, these two gray roller wheels are large pneumatic tires. They're able to compress quite a lot and they fold up and down in a small rotary mechanism and can be seen again. The cube is collected, pivots up, and then it is launched using the rollers spinning backwards in a pneumatic cylinder. And in a more complex manner can be seen here, is the climbing mechanism, which is able to retract and extend to many times its original length. Again, the cost of the machining capabilities of the team that would have to make this. One more example, an Australian team, the Drop Bears, back in 2017, you had to place a gear-like piece of plastic onto a very specific location. The way they decided to do this was, from what I can tell, one of the most complex ways to do it, but again, integrates very simple mechanisms. It was the ability to move the gear on 2 axes. It could move horizontally forward and backwards across the front of the robot. This was through funky electronics and software, which I do not understand all of, enabled them to control these 2 axes, these 2 linear axes, to allow the very precise positioning of the game object. And I believe there's a short clip here to demonstrate that. All of these videos are available on YouTube under the titles at the top of the video. Yeah, so that can be seen, and the gears dropped off by a simple rotary mechanism on the edge. Yeah, again, 2 very simple mechanisms integrated to create a very fluid motion thing. Again, the software behind it's quite complicated, but it's still quite impressive to see. And then, yeah, again, to push the time, as we have a lot more than I thought we will, I'll sort of go to the question of before of a mechanism on my team. Here's another photograph of the tube-in-tube that was on the linear mechanism slides. These tubes actually cost about $5 from Bunnings to make, and it's a very light, very durable way to do that with a pneumatic cylinder, because you only needed 2 position placement at the end of the day. But when it retracted, if it was jammed by something, it would stop and hold rather than go the full way because we limited the pressure. Yeah, very simple, very effective. And on the right here can be seen multiple stages of draw slides stacked onto each other. So we saw with the Crescent Robotics, they had a complicated tube-in-tube with bearings method of doing the extension of climber. Here can be seen a much cheaper method of getting the same extension ratio of 4:1. Rather than pull in internally with that tube, obviously don't have the option here, so just a winch was used. A very simple winch, just 2 motors with a gearbox on a shaft. Ended up working quite well if the machine didn't continue to power the winch and fall. Yeah, again, the draw slides, they seem very simple. They are very simple, and that's a great thing. If used correctly, you can do heaps with them. We end up using 13 draw slides on our robot made in 2020, 8 for the climber, 4 for the intake, and 1 for the color mechanism. Cannot recommend draw slides enough for someone trying to make a simple linear mechanism. They're cheap. If they're not working, you can toss them out and it's not that much of a break to the bank. Yeah. Have any questions come through since then?
None on the YouTube questions? No, not yet.
Good. Yeah, I'll just continue going through the extended presentation then. Right, yeah, what else has been taken out? So on that disk intake, as discussed before, this is an example from 2013 Frisbees with the game piece in question. You had to pick these Frisbees up from the ground. And so because they're already on the ground, you have to have a friction surface in play here. Deal with that friction surface, this team had a top roller, which enabled them to suck it up fairly quick. It's pretty hard to see the actual mechanism, but you can see the effects of it quite here. Because of the mechanism is quite wide, it was able to pick up in quite a wide area as well. You can see that top roller there in the gray. Just sucked it straight up into the machine with a small plow on the bottom. Again, very simple rotary mechanism powered by an electric motor that performed a task quite well. Right. I guess one thing not quite discussed that can be talked about here in regards to intakes. On the front of this machine, I imagine a lot of people will recognize mechanism wheels, in which the rollers are at an angle. What this enables, when the wheel spins, rather than having the forces imparted with the same plane as the rotation, those rollers enable it to be vectored at 45 degrees. This can be used on a mechanism machine to enable it to move in all directions, which is more on drivetrains, which I don't think is my topic for discussion. But in this case, it can be used to, rather than just pull in a cube object, it can be used to lift it or move in some other way. I'm not entirely sure what these people specifically intended for this team, but mechanism wheels can be used in a horizontal roller. Say you are picking up balls, to center the ball toward the middle of the intake. I know a lot of people watching this will likely be doing FRC, so that's a likely help for some people. This machine is also, I just think it's great, using drivetrain elements to launch a cube. This is 2018 with those big yellow milk crate cubes. Again, because of the cubes, they're never perfectly straight. They're not round like a ball, obviously. The wheels were quite compliant to enable to deal with that slight misalignment, which is the gray pneumatic tires, and the green wheels at the top were just to give it some extra velocity. It is worth noting those intake wheels on the front were deployed with a rotary mechanism on this shaft just there, because that's the way they wish to stow it. Right, what else did I take out of the first presentation? Here we go. So, example of both a linear actuator and a 4-bar mechanism is Team Miscar from 2018. Large heavy mechanism due to the 4-bar. So how does one deal with this? They also need high positional accuracy because of the height required and the varying heights of the tray in which those yellow cubes have to be placed on. Therefore, they want to keep things parallel, used a 4-bar. They wanted high power, that is with high precision. They used linear actuators. So this, as long as it's quiet, yep. Fairly short, but it's a good way to see it. And even though they only go to 2 positions here, that electric solution does permit effectively infinite resolution within that range of motion. And that intake was able to move up and down on the wrist fairly accurately due to the fact that the back of the machine and the mounting point for that intake was always parallel, no matter at what point in rotation it is. And then here we have another example of a offset 4-bar mechanism, like the one in that fighting robot. I was able to launch the other. This is used in a much simpler sense, again, for deploying an intake in FRC. One can see the potential uses of this in regards to attempting to stow a large mechanism. One can see it can fold up quite nicely there. Again, play it in because it's quite short. It can be done also in reverse, in which the mechanism starts up and they will deploy out at an angle. This is because all elements of that 4-bar are different lengths, and you get very funky geometries with that, and it's good fun to play with all that. Yeah, 2 more uses there. I think that's about all that's directly into the presentation. If any questions come through, that'll be quite helpful.
Yeah, we've got one question.
Yeah, great.
With so many different ways to achieve motion, how do you choose the best one?
That is a great point, and I can't believe I forgot to discuss that. There is absolutely no answer to this. And in a great thing about FRC, a great thing about FL, a great thing about all mechanical challenges is that there are a million ways to complete it. If there was only one good way, then all the machines would look the same. A good example of this is 2018. Because you had to place a fairly heavy object fairly high up on a scale, lots of people chose to use elevators. And I will get back to the question very shortly. A 2-stage elevator that would cascade, you had to move in a linear fashion, had to be fairly simple. Most teams couldn't make these funky 4-bars with electric power. A winch, elevator, that was the way it was commonly done. Other teams chose to use a 4-bar like this. I know Project Bucephalus used a 4-bar like this as well. Other teams shot the cubes. There is no, I'm sure, you could find some relation, but across all games, across all challenges in real life, across all machines in real life, there is no attribute. You can't really judge the correctness of a mechanism. It's how it is implemented far more than it is the mechanism chosen for the task. So this team, this car, is very, very capable. They used a 4-bar where everyone used to use an elevator because they took the time and effort to optimize it, to plan for it, to prototype, to test in the proper order and method by which to get a good result. Their 4-bar was just as capable as anyone else's elevator or anyone else's shooter. So quick answer to that is that there is absolutely no answer. Pick what, if you personally were going to pick a mechanism for something, have a few ideas, test them and see what you're able to implement the most effectively, and then choose and progress with that one. It is, again, far more about how you implement the mechanism rather than the choosing of the correct mechanism, as there is no such thing as the correct mechanism.
So could you give us some tips about how you would do it in a design process? Like, how would you come to the conclusion of a certain system that you would use?
Yeah, fair enough. So if you were, again, in the context of FRC, which I imagine is quite a number of people watching this are involved in that in some method, you're given a game challenge, you have to move a ball, you have to move a cube, understand what that is and what the potential methods to achieve this. While there is no perfect method, there are things that just won't work. And so make sure you know what you're doing in that regard. Then from there, like with, this presentation is a good example of a lot of different ways in which it can be achieved, and make sure you have a good idea of a bunch of them. From there, pick ones which are feasible and which you think will actually work. Test a couple. If you only think one will work, then only test one, or just go with one, but test a few if you can. Again, which one can you implement the best? Which one do you think will work the best? And then move on with that and progress with that as much as you can. If you're going to chop and change the idea, nothing will ever get developed. I'd say stick with one once you have a decent idea of what you're doing. Yeah, that will hopefully lead to a functional machine or whatever it is at the end of the day.
Yes. Thank you for your presentation. It was very informative. And I think we'll be ready for the next group in a bit. I don't have any more questions. So that would be it. Yes. Thank you again for giving the presentation, and we'll take a short intermission, and then yeah, we'll be back in a bit. So yeah.
Thank you for having me on.
Yes. So thank you everybody for coming to watch our stream. We'll be done for today, and we'll give the mic over to 503. So I wish you all a very nice stream for the rest, and yeah, you guys can take it away.
Thank you.
Yes. Goodbye. Have a nice day. For the
Bye.
rest.
Have a good day. Hi, everyone. Welcome to the next 3 hours of the 24 Hours of STEM conference. We're FRC Team 503 from Rockforce from Michigan. I'm Ashna, and I'll be your host for the next 3 hours. Please make sure if you have any questions to put them in the chat, and we'll be sure to pass them on to the presenters that way. So now we can get started with our first presentation. And it is about connecting Onshape and LEGO Spike Prime for virtual robotics. And we're with Owen Gervais from Tufts University. Hi, thank you so much for joining us today and presenting.
Yeah, absolutely. Thank you for having me.
So we're ready to start whenever you are. Just a reminder to everyone out there watching, put questions in the chat and we can ask them at the end. Thank you.
Great. Thank you. So, hello, my name's Owen. I'm a senior in mechanical engineering at Tufts University. So today I'm going to be talking about work I did over the summer and through the fall, connecting Onshape with the LEGO Spike Prime and trying to expand your virtual robotics design toolbox. So the big question we had at the beginning of the summer was, with virtual learning, how do we get everyone building and designing with LEGO robots? The LEGO education platform is awesome for getting people hands-on experience, getting introduction to coding, introduction to robotics design. But once we're all virtual, how do we actually step away and be able to build if we can't have access to the kits that are in the classroom? So by going through that, we decided that Onshape was a great platform to try to leverage. So with using the collaborative nature of Onshape, I like to think of it as the Google Docs of CAD, you can build a public document and then have it shared out to everyone on the Onshape user base and have copies made and make personal build spaces where different groups can start building virtually with the LEGO Spike Prime and developing. So here's a few models of our actual final pieces. The end up product was that we created a full kit. So we created every part in the full LEGO Spike Prime kit in Onshape in a single document. And that document is live right now. And I will share the link out or put it on the page at the end here. But we'll go through the whole process of downloading the document, playing around with it, just so we can get more copies and get it out there as much as possible. These are just a few of the sample LEGO builds that come with the kit, and then a few other little pieces. We have a little dog and a little differential drive robot. Yeah. So I think I'd start this out to really just show a video of how awesome Onshape is to use with this this platform. So with Onshape, I'm sure a bunch of you used it before, but you can actually go through and build and collaborate on the same document. So while it's awesome to be able to use Onshape in the fact that you can build in the same part studio, you guys can do sketches, you can add features, and you can all see it real time, updating while each of you are adding those features. It's also a really cool idea to use assemblies as the same thing as if you were in the classroom and you were working with a partner building a robot. You guys would each be adding piece on and piece on until you guys came up with a final product. We thought it would be a really cool idea to use Onshape's assemblies to leverage that fact. So you are actually able to put each Lego piece in, and you and your partner are able to put together a Lego robot. This is an early demo from the beginning of the summer when we started getting the pieces together, but my partner Teo and I, who did a lot of the work with me this summer and I'll be showing a lot of her work as well at the end of this presentation. This is a live stream or a time-lapse video of us putting together a full Lego robot at the same time. So I can talk through it. So as you can see, we have all the assets in and we're importing them all in. It's just a simple 4-wheel drive Lego robot. You can really see that we're both on the same document right now. We're placing the axle through. And when you're done, you get a full Lego robot in Onshape. I think one of the really cool things about this is that Legos really tailor well to using these pieces together. So you've got your pins and cylindrical mates, fastens. The mating system of Legos is very similar to the mating system that organically integrated with Onshape. So if you want to put a pin in a lift arm, it's easy to just fasten them together. I'm going to go through a live build a little bit later on how to actually go through this process and get your own document, but we will continue on from there. Pan around. You can see we have a little wheel animating down the bottom corner as well. This is an early start torch informations. So today, these are just the table of contents, what we're going to be doing. So I'm speaking about the document first, going through it. And then I'm also going to get everyone who has an Onshape account their own copy of the document. So I'm just going to walk through slowly how to get your own copy of the document, how to get to the document and access it if you haven't searched the public forums on Onshape before. And then I'm going to show off some cool Onshape API demos that we figured out over the summer, and then also my further research that I've used these Onshape assets for, if we have time. So I think I want to start with the fact that if people have used Onshape before, it's an awesome CAD-based platform or CAD platform for virtual collaboration. But they also have a really cool side to their program called Feature Scripts. Feature Script is Onshape's coding language. It's the in-house coding language that their developers use to create the features for Onshape. And that is open to the public. So you're able to go in and create your own custom features for Onshape documents and for the public. And you can publish those just as you were to create a public document with all your parts and your assemblies. You can create a public feature script that people can search up, download into their workspace, and it pops up in their toolbar, just like if it were a stock Onshape app. Our original idea with the Lego document was to create a bunch of different feature scripts. Say we had the Technic lift arm and the Spike Prime hub and the motors and the wheels. We were thinking that we could have it so that it would pop up in the toolbar and you could just click in the toolbar and the piece would generate in your assembly. Here, I just wanted to highlight some of the really cool features that you can get out of this. I think this is totally an awesome aspect of Onshape that I hadn't dived into a ton beforehand. I know the spur gear I use a ton and I used throughout my robotics course this fall. Super easy to quickly generate meshing gears. Yeah, it's awesome. And yeah, you guys should all check them out. I put the link down here, but it's really intuitive and awesome. So this is the first demo. This was a proof of concept to actually kind of take our models and do the idea of we're clicking in the touch bar up top and being able to generate Lego pieces. So if we go slowly here, we have the gray axle pin. These are, I'm sure you're familiar with all of these. These are just the stock Technic pieces that come in the EV3 kit, the Lego Spike Prime kit as well. But if you can see here, the top bar is cut out in that demo video. But once you click the icon on the touch bar, this Lego axle pin generator pops up, and it creates a feature in the Onshape feature tree. And then you're able to see a drop-down menu with different configurations. In the feature script, you're actually able to go through and select and create configurations as if you were creating them in an Onshape document, but you're just doing this in the backend code. So one of our initial proof of concepts was to create the axle pins, the axles, and the technical lift arms to try to get stuff generating into Onshape and try to start integrating this process. So one of my first goals was to get these axle pins working. So each of these pieces are generated in feature script. We went through and created each part. It's just a revolve and a cut through the body. And then it's configured for each type that it is. So here I'm selecting yellow axle pin, and the yellow axle pin gets generated into Onshape. These pop up like features, but they come in as separate parts. So you're able to easily select and choose which one you want to work on. One of the cool ones that Teo, my partner, worked on was that this expandable technical lift arm. So you're able to actually specify the number of horizontal and vertical studs you want. So you can make custom Lego pieces just by clicking the icon in the top corner. And by default, it defaults to a thinner lift arm, but you're able to select the standard thickness option and be able to import these into your work. We thought this would be a really cool application if you wanted to 3D print custom Lego lift arms that were just one bys if you have different dimensions that you want to reach. Yeah, these are all public documents. I'll show how to access all of these later. But as you can see, she's putting in different values. So we have 1, and she's specifying a 1x3, which gets automatically generated. It's all real-time updated. 5, and she'll select standard thickness, and we'll go to the normal thickness that you would suspect the Lego arm. The next stage is our Lego axles. We also worked with these. We thought there would be simple configurable parts that we could try to get generating in really quickly. The axle, we have a drop-down selection just like the yellow and gray pin connectors as before, but you're actually able to just select and generate the pieces, which is. So as you see here, there's a drop-down selection menu before, and you can just drop it in. If we look here quickly, these are just the initial models. You saw them originally in our build demo, but this was our starting phase. They're all originally modeled and they're all parametric. So they're all driven off of the distance between the holes and the diameter of the holes. So when going through this process, we realized that feature scripts were awesome for features. So if we go all the way back, which makes sense given the name, they work awesome if you want to generate a simple a part of a feature, a feature of a part. So if you have this, say for this extended surface, you're generating a feature in that part, but you're not creating a part with a feature script. Granted, this spur gear is a little bit of an exception, which works really well. We realized that the easier way to do it was create a public document that had a bunch of different part studios, and in each part studio, it was a configured format. By going through this method, we were able to not generate the parts within each part studio. We were actually able to just create one master document that when you went into an assembly mode, it would all show up and you would be able to just click through and select and drag and drop your Lego pieces into the document. So it's really awesome because it also increased the usability of the document a lot. As it had started beforehand, we were creating different part studios and clicking the top bar and generating Lego pieces into a part studio, and then going to an assembly and dragging pieces in. But now all you have to do is find your document in the work and drag and drop your pieces into it. So I'm going to show a quick demo of early configurations when we were testing them out. So right here, as you can see, we started to change the aspect of the sorry about that. We started to change the form of the document. So if you see to the right, we started to create a bunch of folders and started to separate out each Lego piece into each of their each of their configured formats. So in this case, we're creating a Lego Technic axle connector. But the only difference between the three that come in the set are the angle that the two axle connectors are apart. So as you can see, we're using a configuration of the part in the part studio and changing the property, the name, and the angle between them in order to generate each of the Lego pieces. So in this case right here, we have 180 degrees between each of the axle connectors, and we're actually just using a circular pattern that's configured to drive the dimensions of these pieces. So if you click into here, you can see us changing through. Super easy to select on this side. As you can see here, it's all parameterized over the variable L, which is the length of distance between pins. And you see we generated the 90 degree. It's just, and you're also able to update the color. You have the configurations, and you also have a configure properties tab. In the configured properties, you can change the color, the name, the mass, the material. It's a really awesome thing to dive into. You can make some really cool documents with. And this is 135 degrees, and they're all stored within the same document. So it's very easy to use. So once we've decided to settle on this format, we decided to jump into going in the route of making every single part studio a specific Lego type. So right here, I have just a simple Lego brick. And in the Spider Round kit, there's a ton of different colors. So for our use case, we decided, okay, we're going to make Lego bricks. We're going to make Lego circular bricks. We're going to make Lego lift arms. And in each of those pieces, we were going to create a configured document that had each of the one that fit in that category. I'll show this more when I walk around the document, but this is just a quick video of how we refactored the document to just get into a better form and more usable form for the user. So as you see, we're starting to build up some documents, but this is how it actually looks once you import, go into an assembly and you're starting to use the documents. So as you can see, it's classified by the type of block. So we have Lego bricks, angled, circular, shield. And if you click through that drop-down menu to the right, which I will do in a later section, you're actually able to select which one you want. Just like you were in the configuration as I was doing before, deciding on which angle I wanted. All I'm doing here is just actually using that configuration in the assembly to choose which piece I want. So here I'm grabbing an Azure plate piece, and I'm also grabbing a white tile. All these pieces are linked together because they're all circular Lego pieces. They're all one part studio, so it's really easy to just get everything together. And the usability of it is awesome. It's really been a good way of going about it. Another interesting way that we started to work through this is that we just wanted to try to use the bill of materials that Onshape has built in. If you create an assembly and you spec out your parts with the correct properties, you can start to actually print out a CSV of all of the bill of materials on your document. And from here, it's a little hard to see in this corner, but we actually in it specified the individual Lego part ID for each Lego piece, and then also connected the bricklink URL. If you, by say, build up a virtual Lego robot that you don't have all the pieces for, and you want to build, you want to buy the extra pieces you have, you can go click the bill of materials, print out your bill of materials. It will tell you how many Lego pieces of each individual type you have. And then you're able to go through with the part IDs. And actually, if you don't have enough pieces, you can click the bricklink URL right there, and it will bring you to the page to buy more or just look around with different colors and pieces that will work. So I think here you see the part numbers, and then we have our description, which is our bricklink URL. So I'm just copy and paste that into the tab, and as you can see, it brings you right to the Azure home. So what I thought would be a cool idea for today is just to go through the document and start to show off some of the ways of using it, and also try to live build something as well. Just take 5 minutes and go through how it all works. So this is the document itself. It's public. Everyone should be able to see it. I'll go through the process right now of actually downloading the document, or you can just honestly jot down this name and you'll be able to search it up later if you want to use it. So when you open it up, you're greeted with this main page. And then I always just said, just go from top to bottom. You'll be able to find everything you need. So this is the getting started building PDF, where if you go through, it just shows you how to find this document already. You're already at the document, so this doesn't really pertain. But you would just go to the public search page and be able to just type in Lego Spike Prime. This will pop up, and once you click into the document, you should see this tab. I don't know if everyone's used copying other people's documents on Onshape. Awesome way to get a bunch of assets really quickly if you don't want to go through GrabCAD or some other way. So just you click make a copy and name the copy of your file. That will show up in your documents. Once you click up here, you're able to go to your documents and you'll be able to start building. I recommend either building within the document. So once you make a copy, it's really awesome to just pop in and create an assembly within here, which I'm going to do in a few seconds, and then just start adding and building stuff in. So here just walks you through similar thing that I showed before, the different pieces. And then there's just some tips for building robots. Revolutes and cylindrical mates work awesome, but working with this document this fall, fasten mates are awesome. I will show those off. It just makes everything super intuitive. Yeah, so I'll show off some. These are the Lego robots, the stills I put in the beginning, but they're all built in this document. Play around with them. All the degrees of freedom are there in the piece, so you can actually move your pieces. Full rotations, everything fits and snaps together really nicely, which we were really happy about after building out this whole Lego kit library, that everything clicked and there were no collisions. And we have a little tiny dog robot. This was part of our, we had a competition at the CEO where I did research this spring of creating a small robot that was cute and could do one motion just to emote. So this was the little guy I came up with. And then this is a just a simple differential drive robot. I ended up using a similar variant of this for research this fall, just getting Onshape connected out of the page. And then if you can see here, there's parts tab. When we go through this whole thing, we have our parts, we have different motors. You can click through and select all of this. These are all the different part studios. So I think one of the more interesting ones, if you go down to beams, it shows up and you have different part studios. So once I jump in here, you're able to see that we have these pieces and the configurations tab pops up here. You can click through and see the different types of pieces and they pop up and generate. If you want to see how the configurations work a little more, you can dive in, you just click the button on the side. You're able to see that all of the pieces are generated in this fashion. You also, what I was talking about before, you can name and color and put the BrinkLink URL, the individual part number, so it's super searchable. And the material type too, which is super important if you want to take these parts out and start playing around in simulation with them. Just so they generate the right mass properties, so you can start playing around with those values. So I thought it'd be just a cool demo to just go through and add some parts in, connect the motor to a spike prime hub to show off. I'll take just a few minutes to do that. So going here, I've clicked the insert tab and that shows up and I'm able to see all the part studios and stuff I want to add in. The way we kind of organized it is that all the pieces are in the part studios and then the assemblies are all of the extraneous non Lego brick pieces or Lego tool pieces. So we have our large motors, the spike prime hub, the caster, the wheels, all of them in this section. So just to start, I'll take a spike prime hub and drop it in. I always say easiest way is just fixing it in space, just when you're building around so stuff doesn't fly around. I'll take a small motor, 2 of them, and let's grab some wheels. So when you click through here, you can see all the different pieces. We have different axle connectors, like I was showing off before. We actually took those generated parts and popped them into this section to get more of a easier form. So we'll go through here, the classic Technic pins. We'll grab some of those. We'll grab one of that type. If you click down here, there's the different blues and the that you figure out. So I'll grab a few of those. And I will also grab okay. So it's all really nice to use these documents. So all I'm going to do is I'm going to use a fasten mate. That just takes whatever ring you select or face you select and aligns the mate connectors, which are these in Onshape. And so right here, I've selected the inner bit of this face, and I can just select the inner face of this. And the piece is in spec prime. We thought this would also be a really cool way of introducing assemblies to students because they click together the same way that Lego bricks would. And so you're teaching them how to align pieces so that everything meets together nicely. And you're also teaching assemblies by doing this process. So what I'll do is just build a balancing bot. I did a little demo of this later in the presentation, but it's a quick and easy thing to put together. As you see here, I've selected the inner race again, and I'm selecting outer this time and everything. You can switch orientations of pieces and rotate them about secondary axes here. So as you see, got those pieces together. And one of the cool things I like to use a lot more is just taking different pieces. So I'm gonna grab that. Actually delete. You don't have to take all your Lego pieces and dump them all into your assemblies at once. So what I like to do is just take this and make a copy. And you have all your pieces connected. You're gonna have one not connected because it's not in space. But as you go through here, you can quickly build up your robot. Select these a few more faces. Awesome. So I have those two, and just a quick on this face. And just for animation's sake, we will do a revolute here, revolute here. Yeah. So you can see you can quickly build up Lego robots. It's really awesome use of this doc, and I think it has some really cool aspects to teaching and just like virtual collaboration using this. So if you want to use this document again, just jot down this name and search it in the public, and you should be able to totally find it. I'll stop sharing here, and we can talk about how once we built up these virtual robots, how do we get them connected with the Onshape API and start doing some cool interactions with a physical robot and a virtual robot, which is what the goal of research was. So the goal for this, the goal also for the spring, the summer, was to create a connection between the two. We wanted to create a virtual twin, so that the great goal was that we wanted to be able to create a robot. Say you want to create a robot arm in Onshape, and you create the same robot in real life and physical life. We wanted to be able to drag the robot around, move its arm locations, move joint locations, and be able to actually have a one-to-one representation of your physical robot. We weren't totally able to figure that out, but we got some really cool demos and different connections, the way of doing that. So the way we started was using the EV3. EV3 is awesome because you can just connect up Wi-Fi access by using a USB dongle. Spike Prime doesn't have a Wi-Fi card on it, but we've been playing around with different ways of connecting to it. So the EV3, we ended up going through System Link and LabVIEW in order to connect to Onshape. We also then realized that you can just use Python 3.5 and jump away from using LabVIEW and System Link in order to connect to it. And we're just publishing to Onshape's API using GET requests. One of the cool demos we put together was actually using the color sensor on the EV3. So what I'm doing in this demo is taking the color sensor and reading the color of a block, and then changing the color of an Onshape part by publishing the RGB values, true RGB values, to Onshape. The hues of these parts change, but the true value doesn't. If you look here, I've clicked block, there's a green block underneath, and you have a greenish tint to it. The color sensor without a lot of light isn't the most representative measurement. As you can see, changes this part to red. These are both real time, by the way. They're just stitched one on top of each other. Another interesting demo that we had was that we used a room mapper. So we wanted to leverage the fact that the Onshape, or that the EV3 also had an ultrasonic sensor on it. So what we wanted to do was, what if we put ultrasonic sensor on a Lego robot, had it spin in place, and use it as like a low density point cloud for a LiDAR. And then took those points that we generated and put them in Onshape to visualize the room that we created. So what I did with this is I created a small little turtle bot and had it rotate about its center axis, and was able to take a bunch of data points, use 2x4s, and tried to close in the gaps so you didn't have any extraneous points where the ultrasonic sensor would shoot out of it. But yeah, so it's also very harsh corner, so it should pop up nicely. So as you see here, it's collecting data points. And once it collected data points, just converted from spherical to XYZ. And we got this representation in Excel, which is really awesome. And from there, I wrote a Python script that converted all of those points into a feature script. And then we use that feature script to put into Onshape. So it creates a polyline. So you're able to click through. So imagine it creates a line between each of these points designated by the XY coordinates and plots that into Onshape. There's a threshold to clear out any bad data points, which is this stuff right here. So as you see, it's a lot of points. We just had a simple Python script running all this. So, but once the final product, you're actually able to put this in and you extrude it up and you have a rough estimate of your room in Onshape, which I think is a really cool method. There was actually a student that was doing research this fall trying to put a LiDAR onto an EV3 and use a similar method to this and try to map a room using a LiDAR on the EV3. This is our foray into transforms. This was all my partner's work. This was her focus for the whole summer. So I can't speak too much to the full technical aspect of it, but I think some of the demos are really awesome. So I wanted to show some of this off. So first we wanted to transform a motor. So let's try to turn just the axle of the motor. So in this demo, she's using Postman and sending direct HTTP requests to Onshape's API in order to rotate the motor. Soon she's just the motor will flip and you should see a rotation. So as you see right there, it's very fast because it's a one-to-one. There's no way of animating it to that point, but it just switches to that section. This is another cool demo I found. So if you keep an eye on this gray block right here, she's transforming its position in the assembly. So we click through. The Onshape API takes a little bit to load up and set through. She wrote an awesome transformation script where you're actually able to set the different points to send around. And as you can see, the block just jumped over there. In this demo, we were able to, she was able to connect the Spike Prime to her computer and actually read out the different acceleration and IMU data points so that she was able to coordinate a position of the Spike Prime with the side of the dice. So by rotating the Spike Prime, it changes the side of the dice and does a rotation. So as you see here, connecting up over Bluetooth serial, one of the best ways to interface with the Spike Prime. So it's getting primed up, started up, and by moving it to the side, you're able to change the side of the dice. As a final transformation demo, we wanted to try to mimic that goal of getting a robot arm to drag in Onshape and then a real physical one doing it as well. But we weren't able to get that direction going, so we decided to flip the direction and have a physical robot move and have the position of the Onshape model update. So in this demo, we have a color selector. There's just 4 colors, a quick handle. We're using the small motor as a basic potentiometer. And when we start up this code, by dragging the arm, it publishes the current position of the Spike Prime motor to Onshape, and this is both real time as well. So as you can see, there's a lot of really cool aspects of using Onshape with the Lego Spike Prime. These are just a few sections we dived into, but there's a lot of work going into doing more with this. I know a lot of people that did research this fall are working at PTC doing some work on it further. But so I'm going to touch briefly on this topic because we still have a few more minutes. But this fall, I decided to try to use these Onshape assets in order to start integrating with different softwares and try to get a virtual twin working. So because their transformation endpoints aren't published, we weren't able to see, and you're not able to get those direct transformation translation matrices. We decided, going through the process, I found that there was a awesome URDF exporter that actually allows you to take your Lego robots, pull them out, put them in URDF format, and then put them into ROS and Gazebo in order to start simulating and training and using these Lego assets as a virtual twin, and then deploying these values to physical twins. So the way I went about that is just ask the overall research question: how do we use our Onshape robots in simulation? So what I did was I built a virtual twin in Onshape. I created a ROS2 package that was built around the virtual twin, contained the SDF, the different meshes around it, and then simulated it in Gazebo, and then deployed the game parameters that I generated in Gazebo to the physical robot. So in this first demo, it's more of a communication protocol demo. So I created a differential drive robot, similar to the one I showed earlier in the demo of the document, and commanded the velocity of the wheels in Gazebo using a ROS2 package, and then created a Raspberry Pi hat that communicates with the Spike Prime over UART, and am able to, in real time, connect and send the same velocity commands to the virtual and the Lego robot. So you'll see here that we've exported the Onshape differential drive robot out of the screen, and now I've run a ROS to just spawn the robot into Gazebo. I'm using a differential drive plugin that's built in Gazebo. Later use some ROS control work as well. Right now I'm sending a velocity, just a linear velocity command to the differential drive robot. And this is happening synchronously. So as you can see, the virtual robot starts moving, and so does the physical. There's a Raspberry Pi hat on top, and the cool thing is you can actually take the front off of the ultrasonic sensor, and it gives you access to the LPF2 side of the Spike Prime, so you can actually just interface over UART. It's really, really quick and easy, and it's definitely opened up a lot of cool demos this fall. So as you see here, I'm just commanding it and then also telling it to stop, which both do. This one, I'm just commanding pure angular movement, so it should just spin about its central axis, just similar to the turtle bot demo that I had before. So yeah, both of those same time. And then for the last demo that I have today, this was the culmination of my research this fall. So I really wanted to create a balancing robot, but I wanted to make a balancing robot that you weren't creating and training by having it fall over constantly. So by creating a physical robot and then making it, training it in real life, I wanted to pull it into Gazebo and do training on a simulation, and then deploy those gains and see how that matched up. So the way I went about that is creating the virtual twin in Onshape using the Lego assets that we created, and taking those points and bringing that into Gazebo and putting actually I just used the same differential drive controller because it's just 2 wheels and you can disregard the caster wheel. And I wrote a simple PID balance loop and trained the robot in Gazebo. I meticulously measured out each of these Lego pieces, weighed the masses of them, so that it was tried to be 1-to-1 as much as possible. I also characterized the motors, so they worked to the stage. But as you see, we've got the robot balancing in Gazebo on the bottom left right here. And then if you switch your direction over, this is a representation of the physical robot balancing. These are the same gains that were generated in Gazebo. And I thought it was a really cool combination of and I'm using a low-level Python class, their hub class, which is really cool because you can just command PWM to the Spike Prime motors. You're not usually able to do that through their main Spike class. but yeah. I have all my research and any of the CEO, any of the demo code, if you want to look at like how I interface with the Onshape API, if you want to dive into this more, my GitHub is right here. This is the one for all the research I did this fall with Ross and Spike, but I also have a CEO page. You can check it out. I have a ton of demos. There should be pretty well documented, but if you have any questions, about it, just totally feel free to reach out to me. My email is right here. And thank you for having me today.
Thank you so much for presenting. It was really interesting, especially to see the different bots and things that you made throughout the demos and things like that. We do have a couple questions in the chat, so we can go through those. The first one is, how would you compare Onshape to other CAD softwares like Fusion or Inventor? Are there any notable similarities or differences?
So I never really used, I've never used Inventor before. I used a little bit of Fusion. I use it for renders a lot. Awesome toolbox, and then also just machining as well. But I think the ease of access to, I was able to get into Onshape pretty quickly as a SolidWorks user. I use SolidWorks a lot. But I think key bindings and like just using it, the usability of it is pretty great. I really don't think the intro, we actually ended up switching from SolidWorks to Onshape this fall. So because we're all virtual learning, my advanced robotics course this fall, we weren't actually able to be meeting in person. So it's harder to be working on CAD when you're doing that. So when we're all in our dorms or in our off-campus programs, we're able to actually just use Onshape and just collab virtually, which is awesome. Just all get on the same Zoom call, and then I'll be working in the same doc, which I think is just such a huge strength of that platform.
Okay, and then the next question is, quite a few of the first LEGO League teams are elementary school students. How difficult do you think it would be for them to pick up Onshape?
I don't think it would be, I don't think it'd be that hard. I think the way that we've formed the document, I think if you put them in the environment of the assembly, I think if you just said that if you want to put pieces in, you can click the insert button and drag and drop pieces in, and you only use one mate. If you just use the fasten, you say that these are the edges you want to touch, I think it could work well. We haven't done a lot of introductions with the claying. We've run a few classes, but not full work yet.
Okay, and then the next question is, which demos have you made so far that are your favorites and why?
I really like the room mapper demo. I think that was a really cool way of like visualizing your data. I think like LiDAR is awesome because you can see it, like looking at the 2D view of it, it's really cool, but it's really awesome to see that like just pulling it out into the 3D space and actually getting a visualization of your room, I think is a really cool and awesome way of using Onshape. I think of the way we've been talking about it a lot is that Onshape is really good for data visualization, which you wouldn't think of as a use of it, but because it's a 3D platform and it's a CAD platform that has the API access to it, you're able to visualize data in just a whole new way, which is a really interesting also way of like learning and teaching the way of usage. But yeah, I think definitely that. And then the balancing bot, I really enjoyed doing that with Ross and Gazebo, and having this thing you created virtually actually translate to the thing physically. I think that was a really cool learning thing.
And then the next question we have are, what are some limitations for using the document right now?
I think one of the largest limitations is the transformation. So I think it's really good for doing some design and doing some like basic teaching about APIs, like connecting stuff and sending requests and having things move. But I think as of right now, the current limitation is like actually using the document or using your robots once you built them. But I know there's a ton of work going into actually doing that, like actually being able to do it. So hopefully within the next year or half year, we'll see some interesting stuff on that front. But I think that's the only limitation I think as of right now.
And then our last question for today is, what are some future applications for classrooms that would use these new assets?
Yeah, I think when I think of future applications, I think that the most interesting use would be if you were still in this hybrid format where you have half your students online, half of them in person. Like, how do you get that connection between them? Because you're basically separating the class into two in that aspect. So how do you get partners to talk and communicate between, so it still feels like the whole class, but you're getting this communication? So having a partner virtual and having a partner in person, but that partner virtual is also helping build the robot. You're building the same one at the same time, but that person's able to control and code and move around the robot in the virtual, or the person physically is able to move around the robot as well, and they'll be able to see the updates and be able to interact together and learn. I think that's a really cool use of that in future classrooms. Yeah.
Thank you so much for giving your presentation today. I definitely learned a lot, especially this is something that you can use given everything that's going on right now, like virtually, and it really like interacts with a lot of people and how they want to use it in robotics in general. So thank you so much for your time and presentation.
Great, thank you for having me.
Okay guys, so we have a couple minutes until the next presentation. So we're going to be playing a couple videos about Spin Art Robot and Lego EV3 Mindstorms. So that's going to be coming up right now.
Welcome to 5 Minute Classroom. I'm Bill Church, your host. Behind the camera is Pete Rogers.
Hello.
All right, Pete. What color do you like that goes with yellow?
Gotta pick blue.
All right, so pick blue. The project we're gonna do today, Pete, is a spin art project with a Lego motor, the construction paper, your color blue, and cardboard. The stuff we're gonna need for this project, so the paper, the cardboard, a Lego axle, gear, some black pegs here, and then, although not essential, but always fun to use, the brass fasteners. Well, we have the Lego gear already attached to the cardboard. If you need a little more detail on how we did that, go check out our video about attaching Lego to cardboard. Okay, so we've got our canvas. Let me put my axle here, and I'm gonna put it into the motor here. We're gonna use our trick of one motor connected to another motor to do that, but I've got to attach my beautiful piece of yellow construction paper, and that's where the brass fasteners come in. You could use tape, you could use glue, other things, but we're gonna use the brass fasteners because it's fun. And we're gonna poke this through. Boy, this is the toughest cardboard I've ever used, Pete. Okay, one there, and they just look cool, so that's always fun. We've got our canvas here. Are you ready to do some art?
I'm ready.
Okay, Pete, I need your help.
Now I get to effortlessly
Zoom in.
slide into camera.
All right, excellent. Go ahead and turn that motor. This motor is the generator for this motor. Really cool. Now let's use that for our spin art extravaganza.
All right.
Okay, you ready? Go
Ready.
ahead. Go ahead. And voila. Super cool spiral.
Super cool spiral.
But we've got other colors here. What's our next color, Pete?
Red.
Okay, take out some red. Should we add a splash of red?
A drip.
A drip of red. Okay, ready?
Yes.
Go ahead. 1 drip, 2 drips, 3 drips, 4 drips, 5 drips, 6 drips, 7 drips. Okay, we got some drips of red. What's our next color?
Green.
Okay. So, Pete, I did the spiral by coming in. I did the drips by poking up and down. What should I do next?
Let's do squiggly lines.
All right. So, squiggly lines. Right, go
There
ahead.
you go.
So I got some squiggles out there. Squiggle, 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 squiggle. And, oh, voila, that is beautiful.
It is a true work of art.
Okay.
Yes.
Yes. Good. So we've got the spin art here. There's more we can do with this idea. Let's go to the whiteboard and talk through a few other next steps. In this episode of 5 Minute Classroom, we did a super cool spin art project. Where can we go next with this? Because we're connected to the Lego brick, the Lego brains, we can immediately turn this into a coding project and challenge our students to write the program to move the motor at different speeds or with different patterns and see what the resulting effect is in your artwork. Making this deck spin faster, also really fun and cool to do. So how we do that with gears is a neat challenge for our students. We ask them, can you gear this up to move at a faster speed? And again, what's the resulting artwork that we can create with that? Finally, this is a neat science platform. If you made this deck out of a sturdier material, and if you reference the video we created on how to add Lego to a thin wooden plywood, perhaps that's the ticket. But now we've got a rotating science platform for exploring the science of rotation. Best thing at the end is that the students can take away their own artwork and bring it home for their refrigerator. Thanks for watching 5 Minute Classroom. Look forward to seeing you next time.
And we're back with our next presentation. Also, that video was really cool. I definitely want to try that spin art project. So our next presentation is actually with a fellow Frogforce member of mine, Sanjith, and he's going to be talking about LiDAR and field awareness through that. Hey Sanjith, how are you doing?
Hi, I'm good. How are you?
I'm doing pretty good. So we're ready to start whenever you are. So just take it away.
Okay, thank you. So yeah, as Ashna said, I'm also a member of Frogforce, and I'm going to be discussing how FRC teams can attempt a method of field awareness without using the typical solution of odometry. And we're actually going to be talking about using a LiDAR sensor for that. So just a bit of an overview of what we're going to be covering. We're going to first talk about some existing methods, like the common methods. Then we'll talk about what we might want in like an ideal method. Then we'll kind of dive into how we could adapt the LiDAR sensor for that and how we could use that. So before we get into that, I want to just talk about that first term in the title, right? Field awareness. So field awareness the definition is kind of in the name. It's like being aware of the state of the field or the state of the robot on the field. So like the simplest definition of that could be something like, I know my robot's position on the field. And that's one of the important problems to solve when you're writing programs for the robot, especially in autonomous. So one of the existing solutions, and it's very popular, is called odometry. So it's popular in both FTC and FRC. And what it does is it essentially uses wheel encoders to calculate the robot's positions. So if you look at this diagram here on the right, you can see how as the robot moved, it's able to figure out how much each wheel moved, and therefore it's able to generate this offset. And the way it works is it figures out its offset in each iteration and adds it to its previous location. And we'll see what that means in a second. And it actually works well. Like, since it's been used so much, right? People have been able to optimize it a lot. And there's several implementations and libraries available for all teams to try. It's a pretty easy thing to get started with if you just use one of those libraries. However, that being said, odometry does have some drawbacks. Like what I was just describing about how it actually works with the offsets and adding it to the offsets, it's not absolute, and the readings are based off of the last position. So the common methods, what they do is they just add the change to the previous position. And what that means is that it's very prone to drift. So what drift means is, let's say that in every loop iteration, my robot was off by 2 inches. So then, or it would be some sort of random number. It wouldn't be exactly 2 inches every time, but for hypothetically, let's say it was 2 inches, then we'd drive once, and at first our estimate is off by 2 inches. That's not too bad. We have a 2 foot by 2 foot robot. It's not that, that's not as major of a concern. But then we drive again, 4 inches. Then we drive again, 6 inches. So it just starts to compound, and that's where we start to see problems. And we'll see this type of issue more prevalent in FRC, especially in fast moving matches where your robot's driving really fast, maybe doing a lot of different maneuvers. This drift starts to really compound and starts to hurt against you. And it also, this is not as major of a concern as the drift, but odometry can often vary a lot based on drivetrain. For example, swerve odometry is different than tank odometry, and therefore it's not always as smooth of a transition between the two drivetrains. So if we think about what other options we have, right? What would the ideal solution be? Like, if you look at this image, right, we want to be able to just track our robot's position the entire time. So our ideal system would first of all have some sort of absolute measurement. The measurement isn't based off of your last position. It's just constant. It's just always figuring out in general, not really depending on your last position. That doesn't mean that it can't utilize the last position for some sort of efficiency boost, but it shouldn't be solely dependent on it. Next, it should have a minimal difference between the drivetrain types, and this kind of goes with the next few points, is that it should be drive-based independent, where let's say that this year my team decides we want to use a swerve drive because we feel it best fits the game, but then next year we think, okay, a tank drive might be better for that game, we should be able to pretty easily transition between them. It should be reusable and can operate as a separate sensor where you can easily get the estimate from the code. So we think about our potential options, right? If we think just on a high level, right? a tool that we use pretty much every day is GPS. So if you think about it, this would give us everything we need, apart from the fact that it doesn't work in FRC and it's not like allowed. It gives us everything we need, but on a much larger scale. Because GPS is tracking the entire world, it can afford to be a couple feet off. Meanwhile, on our gym-sized field, we can't afford to have that kind of variance in our estimate. It's not accurate enough, but the idea is still that it's an absolute measurement system. It's not based off the last. It's easily transferable between the different vehicles, things like that. Next, another option could be beacons. And basically what beacons are is there is either points somewhere on the field or on your driver station, which we would have a camera tracking. So then the camera would be just looking for the beacons and performing some calculation based off of what it sees in the beacons. And there are like perfected implementations of this where it can get down to be very accurate. The issue comes when you start to think about in different positions. Like let's say on this image over here, the beacons were on this wall and this wall. But now if we're over here and faced in front, we're not going to be able to see any of the beacons. So there's going to be times on the field where you'll have kind of like dead zones where the beacons won't be able to see anything, and you'll have to adjust. And you'll have to adjust with some other method, which would end up being some sort of sensor fusion method. You would have to use something like a particle filter or something of the sorts to basically figure out, okay, on these parts of the field, my odometry is more accurate. I should trust the odometry more. And then on these parts of the field, my beacons are going to be more accurate. I should trust the beacons more. So you figure out those types of things, but then you realize it's just not independent. Our whole goal is to get away from odometry. We don't want to be dependent on it, and even on some parts of the field. So with that being said, I'm going to bring over to something called the LiDAR. So the LiDAR is a sensor that, and LiDAR itself, the acronym stands for light detection and ranging. You can think of it as a measurement tool. And basically it measures distance, and it measures distance from a point to a point using the sensor. So the idea is the sensor itself just gives you one single reading, but it starts to get interesting when you start to rotate the sensor. So like if you're facing forward, you get a reading, you have one distance. You face 90 degrees, you have another distance. But if you have every intermittent point in between, then you have 360 degrees. If you plot them out on a piece of paper and go and connect the dots, you'll have a map of the room that you're in. So LiDARs are not just used in our sense, it's also used in industrial settings. Like for example, world mapping. If you think about Google Earth or Google Earth, or just typically any other mapping thing. But if you look at Google Earth and you like zoom into some mountainous area or cities, you see how they have that intricate data of how high each thing is, the slopes and everything like that. That is all collected through some means similar to LiDAR. And probably more prevalent to what we're talking about, it's used a lot in autonomous cars. So for their advanced navigation and localization systems, they use LiDARs for seeing the world around them. And if you're thinking of this in a graphical sense, you can think of it as like a field of view of your surroundings. So if I have a stream of LiDAR, a stream of measurements across one single area, I have now like, it's kind of like a field of view if you're thinking of computer graphics. So how does this apply to us? Well, we've already talked about that the concept is already in use in autonomous cars and vehicles, but we should be able to reapply this to FRC. They're similar to us, just on a much larger scale with different problems and challenges. So we need to look at these existing techniques and figure out what they use and how we can reapply it. So we need to see how those cars see their surroundings and how can we simplify it to work on our robot without all the extra overhead that comes with what the cars are doing. So we can think about what the cars use. First of all, they use three-dimensional LiDARs and they use something called SLAMs. So let's dive a little bit deeper into what both of these are. So 3D LiDARs are pretty self-explanatory. Like the rotating LiDAR that I've talked about is called a two-dimensional LiDAR, where it can give you it gives you distance and angle, or it gives you an X and Y directions. Meanwhile, three-dimensional LiDARs are just kind of the same thing. but in 3 dimensions. So if you look at this image here, you can see how the car is able to see all of that information. So that's simply because the details are really important for the cars, because they need to be able to recognize the other objects. And the next thing that they use is something called SLAM, which is simultaneous location and mapping. So let's dive a bit deeper into this and see what SLAM is and what it entails. So SLAM stands for simultaneous location and mapping, and it was introduced in 1986, but has been improved since then. It was meant to be used indoors with mobile robots. And the idea of what it does is it creates a map of the environment around the robot, which is sometimes referred to as the agent in these types of things. And what it does is it creates a map, and it also determines the location of the robot. So pretty standard. But then you start to think, then you realize that the first term in this, right? Simultaneous location and mapping. The location we see is figuring out where the robot's location is. The mapping is creating the map, but simultaneous means that it does it at the same time. So if you look at this image over here, you can see that as the robot is driving, it's able to figure out its location as well as create the map of the field, and you can see how the map gets refined as it's going. So usual application of this are found in self-driving cars. It's adapted, of course, and mobile robotics. So mobile robotics is like the robots that move around like an FRC. So how can we use it on our robot, right? Theoretically, we have everything we need for SLAM, but there's an issue. We haven't talked about what they need, but let's go into that, right? SLAM is dependent on odometry, not entirely. It uses the LiDAR sensors for a lot of it, but the way it's able to actually figure out its location and map and piece everything together is by using partially odometry for its location getting, which is an issue for us because, again, like I'll reiterate that our goal is to try to get away from the odometry. So then second, we don't need to make a map while we're localizing. Like we might think, okay, it's cool and all and it works, but our map is relatively constant. Our field isn't going to be changing during one competition time that much to the point where it'll require us to remake it every single time. We would just need to make it once, theoretically. So we don't need to make the map while we're localizing. So how can we simplify this, right? First of all, we don't have the need for the height information, the extra detail that those other cars, the autonomous cars had. They have the real implementations, but processing all that data could also be harmful for us because it's just so much more information to process. So we just don't even need that. Then next, we can introduce something called LAM. So introducing LAM, it sounds like it's a brand new thing, but in reality, it's just a subset of SLAM, where the idea is it's the same concept of SLAM. Obviously, the implementation is a little bit different. The same concept of SLAM, but it's separated. The idea is we just do the mapping first and the localization. So if you want an idea of what's going on, right? This is like SLAM as a bubble, but under the hood, SLAM is really just mapping and localization combined at the same time. But what we're saying is don't do them at the same time, rather separate them and say SLAM and say we want to do the mapping only once at the beginning of each competition, because from competition to competition, the field could change a little bit with different placements and stuff. But the idea is in one competition, it's not going to change all that much. So at the first time we go onto the real field to measure, because all the teams are allowed to go onto the real field and measure, we should be able to run some sort of mapping routine on our robot where we're basically doing that same measuring, but it's all automated. And we would essentially save that map to some sort of file that during the real matches, our autonomous and teleop period, we can read that file, load it into our tracking algorithm, and basically compare our LiDAR readings to the map to figure out our location. So the idea is starting to come together, right? You create the map once and you do this all the time afterwards. And we're somehow comparing to our previous map. But let's actually dive in a much deeper into how that exactly works, with starting off with the mapping phase. So mapping is just simply creating a map of the FRC field. So this is where we're going to actually figure out the map. Before we go into that first, I want to talk a little bit about how maps are stored. So if you think about back to what we were talking about earlier, odometry, and just in general, the way we represent our robot's position is in X and Y. And the way the X and Y goes is it's usually, or at least the way we do it on our team, is through inches, where we divide up the field by inches. We're doing the exact same thing here, except we're representing the square as just that grid. Instead of being as individual points that you remember, you're remembering the whole grid, where each square is 1 square inch on the field. So the grid squares are the values of the grid squares are Booleans. They're either true or false, and they represent whether the space is filled or not. So if you take a look here at this image, all of these gray squares are not filled, which means that there's basically air here. But if you visualize this as being like what the wall is, this would be where the wall in real life is, and the robot's able to detect, okay, there's an obstacle here. So in our digital representation of the field, we set those values to true. So true for there's something here, false for there's nothing here. So we can use this for a couple of different types of things. First of all, just checking if any object is there, just like this. And not as important or not as relevant to this problem is pattern detection, which you could use to figure out to improve some other programs that you have. So what's so what we've talked through has an actual technical term. It's called an occupancy grid, and the way we store it is in a binary 2-dimensional array, where basically each square is occupied or not, and that's where the term occupancy grid comes from. Now, again, before we go into actually how our mapping algorithm works, we need to talk about what our LiDAR is telling us, because we need to have some sort of way to process the input from the LiDAR. So if I talk about hardware, I'm just using a generic RP LiDAR, but it'll be very similar for other sensors. But the idea is when we get it, we get a lot of data. Like there's a lot of data coming. This is a pretty long animation, so I'll just cut through. But and the issue is the sensor is really fast. Like all this data that just flew on the screen, that's not even one full 360-degree reading from it. It's giving us a lot of the data, and we need to figure out how we can receive that data at a reasonable limit. Secondly, it's sometimes spotty, which means like if I have 259 degrees and then 260 degrees and then 262 degrees. Sometimes they will skip out on 261, but it's not giving us indices for those values. So it's not telling us that this reading is at 0 degrees. So we have to be able to somehow correct for those types of things, or have some sort of system that'll allow for those sorts of inconsistencies. So what's our solution to this? We can't be reading from the LiDAR and then processing the input, then reading from the LiDAR and processing the input. That's just simply not going to work. So what we do is we write 2 different programs, one for processing it, and we write a second program for reading from the LiDAR. And we have to find some sort of fast way of IPC, or inter-process communication, to transfer it to our program. And the next thing I want to talk about is simulating the LiDAR output, because at home, it's something that really is going to be a little bit of a struggle to do with the real sensor. So yeah, how do we do this at home? Because without the actual sensor, is there any way to test this? And I think this image kind of gives the answer away. But yes, you can use simulation. So 2 of my other teammates, Joshua and Cameron, they actually gave a presentation yesterday about how you can use it was called Simple 2D Robotic Simulation and Robot Simulation Applications, is on the Energy Stream. So if you guys want to check that out, it was a great presentation. It talked through, basically our team has been working during the summer so that we don't have to stop programming. We can keep working on robot code, but we've created simulations to simulate how the real robot is, so that it'll be easy to transfer over. But just a general overview of what we've done, for this LiDAR simulation, is we wrote it in Java and Swing. So it's a relatively simple project. But what we did was we simulated the LiDAR using the same technique that you use in computer graphics for these types of things, which is called ray casting. The idea is you just shoot a line, and then you have a list of all the other lines that make up the field. And you just check for collisions with those other parts on the field. So then we obviously included parts for the robot to move around and re-render so that it's as likely as possible. So I'll go into more detail about how the actual simulation works with the LiDAR, but you can take a look at how everything is kind of fitting together with the drawing stuff. Then finally, we have to make it one thing that you need to make sure that you do is make sure that it's more realistic, because simulation, when I'm drawing out the line, the computer's going to give me one answer every single time. If I give it the same calculation 30 times, it's going to give me the same answer for at least this type of line distance calculation. But the thing is, on our robot, there's particles in the air, there's inconsistencies in the measurements, there's other real world factors that'll make it so that we're not going to get the same number every single time. We're going to have some sort of offset. So what I did was I implemented noise so that our readings would be more like the real ones, because we don't want to be dependent on this perfect world that we're getting in our simulation. Then finally, for the beams that didn't hit anything, because obviously you can't just say this beam is null, because in the real LiDAR, it's going to get a distance. Whether if it goes through like the glass wall, it'll hit someone in the stands or hit something in the stands afterwards and eventually give us our reading back. So we need to assign some random high number value that we can later try to filter out through. Then finally, another point that I want to talk about, and I believe they covered it in their presentation, is that simulation is not everything. You should build your code to be as separate from the simulation as possible so you can easily transition onto a physical robot. You don't want to be dependent on the stuff that comes in simulation. And you need to be able to simulate those real world inconsistencies I was talking about. So I'll skip the video. Okay, so with that, before the last thing I want to talk about, and this is just going to be very quick before we get into the actual mapping, is polar coordinates and the Cartesian plane. So our LiDAR is shooting at every angle, is shooting out a beam with a distance, and all we're getting back is a distance, and we can kind of figure out the angle from it because we're getting it in a list. So we can try to say, okay, maybe the first one is at angle 0, the next one is at angle 1. So we're able to figure out an angle and a distance, but how do we actually get that in an offset for our grid? We just use the simple equation, because if you think about it, right, the angle and the distance is actually just a polar coordinate, which can be very easily converted to our typical rectangular coordinates that our grid will be dependent on because it's a 2D grid. So with that, let's talk about the actual mapping phase. So now we get to actually put our data together to form our map. But I think before we actually go into how this works, I want to talk you through our thought process, because understanding how we came up with this is a major part of understanding how to use it and how to adapt it. So the way we always think about when we have a problem like this is we think about our goal, our inputs, and our outputs. And this is pretty similar to what most people do. We basically say our goal is to generate this 2-dimensional binary array of our occupancy grid map, like right there. But what does that actually entail? What is our input and our output? Our inputs, what do we have? We have the robot's current position at any time, because we're saying during our mapping period, we're using odometry, because during our mapping period, the drift hasn't gotten severe enough and we need to depend on it, because we're not going to be able to get it without some sort of position estimate. So you can kind of say that the mapping is dependent on the odometry, but at that point, the drift isn't an issue because we're not having the full match at that time. Then we also have the LiDAR readings, like where the LiDAR is hitting. Then our outputs, or what we want, is the actual occupancy grid map of the field. So let's talk about the procedure that we could probably go through for this map. Essentially, what we say is for each position, we'll do a LiDAR sweep of the field. So a sweep is just like spin the LiDAR around once. Now, and obviously, we're not commanding it to spin around once. It's going to be spinning around continuously, but we're just going to say get the current values that is just seen. So we get a sweep around the room or the field, and then what we do is we say we have each of these scans. Now I'm only going to be talking about the corner ones, but in reality we would, because of the drawing capability, but the idea is in reality we'll be converting for every single scan. So what we take is we take each scan, and like obviously it would be like a row of dots here, and we convert it to the offset points. And what I mean by offset points is, if we talked about the polar coordinates and the Cartesian coordinates, these are the XY coordinates that we got from that conversion. So then what we do is we add those offset points to the current robot position. So if we say our current robot position is at 40, 30, then we say that this offset point is at -10, -10. Then we know that this offset point in world coordinates is on -20, 20, 30. or 30 comma 20. But the idea still stands that it's like converting from local coordinates to world coordinates. So this is basically determining the absolute position of the scans, and we add those absolute positions to the map, where we can eventually connect them all together with our other scans. Now, why did I put this asterisk? It's because what we're going to do is we're going to not exactly add it directly to the map. I'll talk about that in a second. But the idea is we're not going to just automatically add them to the map. But we'll cover that one in about a minute. So before we go any further, before we talk about more advanced, because we need to think. In the last slide, we talked about just one scan, right? We talked about going through one scan and adding it to the map, but we need to, if you think about it, just doing one scan is not going to be enough to map the entire field, because in one point of the field, you're not going to be able to see the entire field. You need to be able to drive across the field and see the rest of the field in that sense. So what we need to do is we need to have some sort of mapping routine that basically combines together several scans and is able to use that input of the location. So we need to drive across the field, and I'll show you what it looks like in the simulation. Note that this is not the refined version. The refined version I'm going to show in the next slide, but the idea is that what we're doing is we're driving across the field, and I'll just point out for a second that there's 3 windows in here. The center window is called the navigator. This is through the main screen where you can see the robot running through the mapping phase. The left side window is the navigator visualizer, where this is saying these are all the beams that hit, and this is where the robot's position is. And the console is kind of like saying at 141 degrees, it was 164 point this. This is like the distance. So this is combining together all the values. So this is how it's going. I can skip ahead. But the idea is it's going through all of these positions, taking the scan that it took at that position, projecting it onto the map based on the robot's position. So putting it into world coordinates, then just adding it to our map list. So now if I go to the end, you'll see another window pops up with our map. So again, this is not the refined version of the mapping, which I'll talk about in a second, but this is kind of showing you how you can piece together the different puzzle pieces from the different places on the field to make this one singular map. So how can we actually improve this though? Because what we can do is we can add something called probabilistic mapping or probability-based mapping. Basically what this says is it asks the question, how likely is it that this square is filled? And you're going to see this pattern come up a lot with the way we use the LiDAR. We don't really just say yes or no. We're going to say, how likely is this going to be true? Then at the end, we come to a conclusion. So we say, how likely is it that any square on the field? How likely is it that any of the square on the field? Because, for example, when we go into the field, we're not going to be alone. Like when we're testing on the field to measure out the distance and run our mapping routine, we're not going to be alone because there's other people using the field. And it's their right to use the field too. Just like how we're allowed to use the field, they're allowed to use it too. So we can't infringe on that and ask them to get off, because that's just not how it works. You have to be able to adjust for that kind of thing. So the idea is saying, in one scan, we might have this other robot here or this other person here, other object, and we're scanning and our scans interfere with that. Then in the next loop iteration, maybe our scans go through it because they're gone. They might have moved or they might have got off the field, something like that. So now we're going away. But if you consider it to how we used to be, what happened is as soon as we hit something like this, as soon as we hit it, we're saying, okay, there's an object here. Yes, a done deal, 100%. No need to check it again. Meanwhile, when we hit it again, when we hit this other one, now we're saying, okay, there's an object here. So our final output of the map will have these random points, this random line here from where we intersected with that other robot, which is just not what we want. So we need to somehow say, okay, sometimes we're going to hit other places on the field, but how often did we hit it? So what we're saying is we're going to assign a score to each square. So now, rather than saying each square is an array of Booleans, we're going to say each square is an array of numbers. And this is only temporary because, remember, our final output is going to be that Boolean array, that binary array. But that doesn't say that that doesn't mean that we have to stay with that while we're creating the map. While we're creating the map, we can do whatever we want. So each square is now a number. So what we say is for each hit on a square, we increase the score, and for each for each like not hit on a square. So every time we see, okay, this square was not hit by anything, subtracting the score. So what I'm saying is like this. Now we've added to the score of these two squares, but then we've added to the score of these two squares. But now on this time it sees, okay, there's nothing actually on these two squares. So now it's safe to say, let's subtract from this score. So even though this might have had a small bump up in the beginning because it saw that, at the end, it'll still get subtracted so much from not being there. It'll only be really tracking the permanent objects. Then finally at the end, we convert it back to Booleans by basically saying, we say like squares with scores above a certain threshold. So if it's above a certain number, we say, okay, that means that we've hit it enough times to say we're fairly certain this is like a real object, a solid stationary object. Meanwhile, if it's below that, we're saying, okay, we might have accidentally hit it sometimes, but this is not part of our field. So what this actually ends up outputting is each cell has a weight, or we call it a score earlier, and you can kind of view these as 3D maps. So these aren't images from me, but the idea still stands. Where maps go from this type of binary occupancy grid while we're creating this. I mean, they go from this type of thing where you're just seeing either yes or no. You hit it once, it's true forever, even if it was just an accident that you hit it. But it goes from something like this to something like this, where you might see small bumps in different places. But the idea is that in the places that are most solid, that you've scanned the most amount of times, they've got a higher score. They're higher up. Meanwhile, these types of places, they're lower. Like you can kind of see how that comes. And what that really starts to describe is how we can create these really accurate and solid looking maps. Like remember our first map from that video I showed was a little bit off in some places, but now look at this with our probabilistic mapping. You can see how much cleaner the map is actually come out because we're able to refine all those unnecessary parts, and that's how you're able to actually put together a strong mapping solution like this, where you're not accounting for unnecessary obstacles. So we've seen that the mapping actually works, right? We're able to, and then obviously we serialize the map at the end to store it in a file, but we've seen that the mapping works and we're able to generate this map of the field. But what is a map without a person to look at it? What is a map without a person to say, okay, I'm here, now I need to go somewhere else? The map is only useful to someone that's actually using it. We need to actually use it for our localization. So our localization is the next step of this process, where now we finally get to compare our readings to the map and figure out where we are. So when you think about it, right, this is a pretty hard problem to solve, right? How do we even approach this? First of all, SLAM uses odometry, so this isn't really something that we could kind of pull directly from SLAM. The mapping was similar to the SLAM mapping. It still wasn't exactly the same, but we could pull a lot of details from there and figure out from that. But this type of problem is not as well documented as SLAM, so maybe we could try to see what SLAM does at a high level, but still that is like, it's not really giving the exact thing. So we know our goal is to find the robot position. So let's think about this the same way we thought about the mapping, the same way we think about all of these types of hard problems. We think inputs and outputs. Our inputs are what we have, or what we have are the map we created before and our current LiDAR readings at any point. Like we're shooting out a beam, we get it back, we have our readings. Our output, or what we want, is our robot's current position. So if you'll actually think back to our mapping inputs and outputs, these are the same components as the mapping equation, but just rearranged. And what that means is, obviously, theoretically, it is possible, because the idea is we just need to figure out a way to manipulate our existing variables to basically rearrange the equation. Because theoretically, we have everything we need to get this. We just need to take a closer look at how the mapping worked and see. So let's actually, now I get to show you something that's that I like to call graphical equations. I don't know if they're actually called that, but the idea is that it's like an equation but with images. So you can think of it as pseudocode too, like visual pseudocode. So we have the robot's position, and this is so if we think about the mapping, right? The first thing we have is the robot's position from the odometry. Then we also have our LiDAR scans. So if we add those two components together, we can now get a robot with all those individual beams coming out of it. But these aren't things that we can use yet. We have to convert these to rectangular coordinates like these. So this is also known as a point cloud. So what the point cloud is saying, and this is a pretty common term in the field, it's basically like saying these are all the points with their local offsets around me. So my position is X. So it's just like a delta X, delta Y from the robot, not an absolute position just yet. But we know the robot's position, so then we can actually use this, add it to each of these individual offsets, and get these map points. So these map points are places on the field, like physical places on the field that we add to the map. So we would add these to the map. But then remember, we talked, one scan is simply not enough in most cases. It's just in general, we're going to say one scan is not enough to generate the entire map. We need to do multiple scans. So the idea is before each scan, we need to be able to move the robot and repeat this in multiple positions. So we can think of this as kind of being one larger operation, for each position, and we just have to repeat this multiple times. And then what ends up happening is as soon as we get this with these map points, we take them and we add them to the map each time. Now, obviously, again, this is not accounting for our probabilistic mapping, but this is the general gist of it, right? The idea, however, what we're saying now is we don't have the robot position. We don't know where the robot is, so we need to somehow rearrange this and say, we have our map points. Could we somehow take these original map points, compare them to our current map and say, this is, or we have this point cloud and we need to convert the point cloud to our original map, or we have to compare the point cloud to our original map to say, this is where our robot position is. So instead of adding to the map, we have to realize that this robot position can be anything. So this so simulated, right? What does so simulated mean? Let's think about, so what we're saying is the robot position can literally be anything. Let's try everything. Let's try every single position and see how likely is it in that position. So what we're saying is rearrange the equation, and from a conceptual level, we have everything we need from that one equation. But on a more practical level, how would we do it? We say rather than adding the scans to the map, we just compare it to our existing one. So we have our point cloud. What we can say is we can say, let's say that our robot position is at 0, 0. Figure out all the absolute points, then see how many of those absolute points that we just calculate match up with the real map. Then test the next position. Check 1, 0. Convert those to all absolute points, check each of those absolute points and see how many of them match up with the map. So we do is we iterate to the map and we check the likelihood of the robot being there. This comes up our concept of the score again. So let's say that this is our map and this is just a basic map and this is our robot scan. So we know, and the reason I put this red dot in the center, this is our robot and these points are all just offsets from the robot. So what we're going to say is let's iterate through the map. Let's start at the top left of the map and check, okay, or just anywhere on the map and check how likely, and then say, okay, I'm saying my robot position is 0, 0. Now, knowing that, where is this point going to be? This point might be at like -10, -20, which is not going to be possible. But so we're going to say, okay, that's not real. But this one, it might be at 40, 20 away in offset. So then we check, then we go on a lookup and we say on the real map, is it filled in is it occupied at point 40, 20? And if it is occupied, we add 1 to the score. If it's not occupied, we subtract 1 from the score. So it's like that. So what we do is we basically cycle through every point on the map until eventually we kind of center on this kind of point. We don't exactly center on it, and I'll explain what we do instead. But the idea is we end up finding this point and we say this is where our robot position is. And we find that most of these match up. And from that, we're able to say, okay, this is where our robot is in relation to the rest of the field, in relation to the world. So, but as humans, right, with eyes and like, we're able to see, okay, yeah, this is pretty well matched up. We're able to see, okay, this is pretty much the most likely position that this robot could be in. But how's the robot supposed to judge one position over the other? I was kind of hinting to it before with the likelihood and the score, but how do we score each point is very similar to what we did with the mapping. What we say is we say for each tested position, we have a score. So each point position on the field, we have a score. And I'll say, let's test out this first position for a second, right? This position, we check, okay, this first point, let's say that's hitting. The second point, we'll say that's hitting. So now we have 2 for the score. But this one's, when we check this point, we go and look up on the table for our real map table, and we check, okay, this point is not there. So we subtract 1 from the score, because incorrect results are all we have to subtract from. So we have 1, 2, then we go back down to 1. Now we're going to 0 because we're subtracting 1 again. Go to -1. Oh, now we hit 1 more. So we go up to 0. Then we subtract 1 again, -1, -2. So this overall point score would be -2. And since as of now, this is the first one we've done, what we do is we remember this position and the score. So we say this is our high score so far is -2, and the high score's position was this. Then we'll check this guy. We'll say, okay, this one's already off, so -1, but then we get 0, 1, 2, 3, 4, 5, 6. So even with a few off positions, as long as most of them are matching up, it's fine. So now this one has a score of 6. We check 6 is greater than -2, which we know is true. So then we just replace the high score with -2 with 6, and we replace our high score position with this guy's position. Then we check this one. All of them are off. This would give me a score of -7. So this one's already less than the high score, so we don't even have to take count of it. So then after we've iterated through every single point, now we can just check, okay, what point had our highest score? What did we register as our best position estimate? And we spit that back out. So it's pretty simple when you think about it. It's just the same type of method, but saying, let's do our mapping routine, but act as if we were on every single point on the field and see which one matches up best with our real map. So, but with that being said, right, it works, but it's not optimized. We need to somehow improve it so that it can work on a very fast time scale. So we're testing, first of all, we're testing every single point on the field. And I'll just say it out front. We're on the field, right? It's a really big field. If we're in the corner of the field, in one loop iteration, we're not going to be able to jump from one corner of the field to the next corner just like that. Like coming from a team of frogs, myself, we're all frogs. Even we know that we can't jump that far and robots can't jump that far. So you should be able to take it from us that robots can't jump that far in one loop like that. So we don't need to test every point on the field. And then another problem before we talk about the solution, because both of these get solved the same way, is something that I call similar objects. And basically it's essentially like this. Similar objects are hard to differentiate. So let's say that my robot was around here and it did a scan of the field. So we're saying, okay, this is our robot scan, but we only have these readings, this offset. So now we're going to cycle through the whole field and check everything. But oh no, now our algorithm is spitting out, okay, these two positions are very similar, and it's going to vary based from time to time. Whichever one has the very better, like has just like, it'll be a very small difference between the two. So it'll be hard to tell whether it's this one or this one. So how's the robot supposed to be able to tell if we're here or here if we're using just these points to determine? So the way we solve both of these problems is by establishing something called a search radius. So a search radius is not technically as a radius because we're just using a square, but the idea of it works. So what we say is we use our last known position of the robot. So if in the last loop iteration, we were right here, we don't need to check the whole field because in reality, there's only a certain amount of distance the robot could have traveled during that time. And obviously we could do even more interpolation using like the velocity and things like that. But the idea is you only need to check around where the robot was because there's no way the robot's going to be out of there. So then if we're only checking in this box, automatically our efficiency is a lot faster. And the other problem, the similar objects, now we're only checking in here. And in the only position in this square that's actually matching up well enough with this bottom with these LiDAR readings is this position. So we ignore that type of thing. So now we've talked about all of this, right? It's finally starting to come together how all of it worked, right? And it actually does work. Like it's a feasible solution. But let's talk about it, right? how did it work, like accuracy and efficiency wise, right? Because if it's not efficient, it's not accurate, it's not going to be a timely solution. So let's talk about how it worked, right? First of all, I want to again cover the importance of using a realistic simulation and noise and constantly sending data to test. Because remember, our LiDAR we talked about at the beginning is like spitting out data really fast at us. We should be able to process all that data in a timely manner. So we were also testing with sending all the data right back to us. And also this noise to simulate those real world inconsistencies that you just wouldn't get in simulation. So for thinking about accuracy, what actually came to be, so actually let me show you the video first, because that's what comes up first in the click sequence. But if you look at this, it's pretty fast as the robot's moving. I'm using the mouse to control it, and this failed. I'll just show you how it looks. Like the navigator visualizer, there's an orange point and there's a green point. So the orange point is the physical position of the mouse, because that's like saying this is where the robot really is. And this green point is saying this is where my algorithm has expected the robot to be. So as I'm moving it around, you can see that the green point is very strongly sticking with the orange point. And even when I'm moving it fast, it's sticking right with it. Even in fast movements like that, it sticks with it. So it's pretty fast in that sense. Along with that, it's very accurate. Look at this reading. 151, 124 is the real position. It's outputting 150, 123. So it's off by just 1 inch. So if our accuracy, our test run error was only off by 1 to 3 inches at max. So the minimum was 1 inches, or the amount it was ever off by was 1 to 3 inches, and oftentimes it's also perfectly accurate. So it's very accurate, and that means that it could be a viable option. Now, obviously, the things with the real world are going to be a bit more different, so we need to test more there. But in just coming from simulation with noise, having 1 to 3 inches offset is a pretty good outlook for the rest of how this will work in real competition. Next is speed, right? It's pretty fast. It was 7 to 15 milliseconds per calculation. So it's low latency, even with the testing with the overloading data. So that having to split up the data was also a little bit of an issue. But this speed shows that it's actually viable for a robot loop too. We can figure out positions about 2 times per loop, which means it's going to be very accurate for us. So that means that overall, this is a viable option, and it could be a great solution for localization, even as like a replacement for odometry. So just to recap what we've talked about today, we talked about how odometry works, and it works great, but it does have some flaws. For example, we want an absolute measurement system. So we could look at something like SLAM, which is simultaneous location and mapping. But again, we found the issue that it's kind of dependent on odometry, and we don't need to do mapping and localization at the same time. So then we introduced the concept of LAM, right? Our concept where we say, take SLAM, but just split it in half, but just split it up and don't do them at the same time. You do the mapping phase, which we run only once during the tournament. And basically what we do is we drive around the field and we add relative points to the robot's position and we add them to the map. Then what we say is we could improve this mapping by using probabilistic mapping, which basically it's basically asking the question, how likely is it that each point on the field on this occupancy grid is filled, rather than saying, yes, it's filled, no, it's filled. Say, how likely is it that it's filled? Then at the end, come to a conclusion for every point. Then we finally got to the localization phase. This is what we run constantly during the matches, right? So what we came up with is not explicitly there in SLAM, but we found that just by rearranging what we do with the mapping and adjusting it, what we can do is we can actually compare our point cloud to the map, say, like our same way that we get real world coordinates. Like on the map, we know our robot's position, we have our point cloud, now we're able to get field coordinates. On the localization, we don't know our robot's position, but we do have the field cloud. So we say, let's say our robot position was 0, 0. Now we have field coordinates, and we compare that to the map. Let's say our robot position was 1, 0. We now have world coordinates, and we compare that to the map. So then what we can do is we can use a score to compare the different positions. It's very similar to the mapping, and say, this is my best position estimate that matches up the best. And finally, our results were that our accuracy was within 1 to 3 inches of the real position, and it was fast because its update time was 7 to 15 milliseconds. So now what's next, right? What we want to do is like, where can we take it with this? Because like, this is cool and all, but we need to expand it more. So firstly, we want to expand this and make it into some sort of singular submodule where we can use it to as a separate system that's just easily able to give us the inputs to our code whenever we need it, either publishing it through network table or something like that. But figuring out some solution to access this in the code is an important step. Then obviously increasing the accuracy and the efficiency. So we implemented like rearranging of the mapping algorithm, and while that worked, there might be potential for more mathematically efficient algorithms out there. So if we can research more into finding those type of things that could increase our accuracy and efficiency, that would again make this more competitive, or make this more powerful, and then therefore competitive. So finally, and then next, we also want to share it with other teams, right? Sharing knowledge helps foster growth. That's the reason why that this conference is happening, right? To have everyone learn about STEM, because it's just a great thing to learn. So more teams can take advantage and start learning about how LiDARs work. Then finally, we want to actually use this in competition. Whenever that starts to happen, our goal is to use this in matches as a replacement or a support to odometry. So with that, I want to say thank you to everyone. I'll answer any questions that you have. And if you have any other questions afterwards, feel free to email frogforest@frogforest503.org and just ask for Sanjit, or just ask for the programming team in general, and we can direct you with some if you have any questions or just want to contact us. So yeah, I'm open to questions now.
That was a really, really good presentation, Sanjay. Definitely some things I was like, wow, you know a lot of stuff about it, and it was really interesting. And there are a couple of questions we have. So the first one is, how do you decide the threshold for the scores during mapping?
So deciding the thresholds for the score during the mapping, it's not, I guess there is like an actual number. I just can't remember it off the top of my head. I'll get back to you on that. Sorry. But it's not, I guess I might have described it a little bit differently. It's not like a dynamic threshold or based on what the highest score is and the lowest score and just taking 50%. It's not like that. We just have like a set number, but I'll try to get back to you on that with the actual number in the code.
Thank you. And the next question is, in the process of mapping, at what point are you most likely to stumble upon inaccuracies?
So in the process of mapping, when you're stumbling on inaccuracies, during the process of mapping, when you're stumbling on the inaccuracies, probably the most likely place you'll see that type of thing happening would be when you're driving and you see other robots on the field, because a lot of times you'll have people measuring the field or setting their robots down and trying to calibrate something. So while they're doing that type of thing, we would run into more inconsistencies because our LiDAR isn't seeing the whole field. Now it's seeing other robots. So that's the reason why we tried to implement the probabilistic mapping. But obviously, if there's like a robot standing there for the whole time, we would have to adjust something afterwards. But yes, the mapping phase, you would see the most inconsistencies when there is other robots on the field.
Okay, and then the next question is, what is the advantage one would gain from using an absolute localization method versus a relative one?
So the absolute localization method versus the relative one is actually a pretty good question. The idea is, you're saying with relative location, it's like what relative location, I'm assuming what you're saying is like odometry, where your last position was based off of where your current position is saying, in the last loop iteration, my X distance has changed by 5 inches and my Y distance has changed by 10 inches, but we don't know our overall position. We just add our changed position to our last position. So the issue that you could see with that is if there's some inconsistencies or inaccuracies, let's say you're off by only a couple inches, in one round or in one loop, then all of your scans are going to be off afterwards. And let's say you have a consistent offset, like a consistent error, like 2 to 3 inches off every time. First time you're going to be perfect, right? The next time you're going to be 2 inches off. The next time after that, not only are you already 2 inches off, you're again 2 more inches off. So the error just starts to compound. With the absolute system, you kind of ignore your previous position, and it's like a fresh position every time. So if you have one small inconsistency or offset in one reading, it'll be like, it doesn't matter for the next one because it'll be fixed afterwards.
And then the next question is, do you see your team using this solution as a full replacement for odometry and encoders, or with a combination?
So I see in our competition, we still have a lot more work to do when it comes to actually putting this on our robot and testing it out, simply because we're not able to be with our robot right now. But I think we're going to start off trying to use it in conjunction with odometry, just as a means of saying this is still in trials. But our final goal, and hopefully we can do it by the end of this year, is to have the odometry be our LiDAR. Our LiDAR being our one and all solution for the localization.
And then another question is, how do you compensate for other robots on the field potentially blocking the LiDAR sensor?
Yeah, so this is also another problem that is kind of interacted with the probabilistic mapping. So if you're thinking about the mapping phase, it's kind of what I talked about at the beginning, or with the first question about the mapping and checking the positions on the field, or with the mapping and using the probabilistic mapping. But it's very similar with our localization method too, because the way we're scoring each point is just by saying how many points hit and we're actually there. So if we're saying that we have 3 extra points here, we might miss those, but every other point has hit the real field. So this is still going to give us a higher score than the other points. And another thing I want to point out about the localization, this kind of reminded me to explain, but you don't need to see every point on the field. Like, these points on the field are behind the field of view of the robot, so the robot's obviously not going to see it. But because these other points were giving it so much of a boost with the score, it's already good enough to say this is the highest score of the positions on the field.
And we have one more question, and that is, are there any flaws that LAM has that other localization methods don't have?
Yeah, so, well, I guess one of the major flaws I would say with LAM, compared just simply because of the nature of LiDARs, is that you're getting a lot of data. You're just getting a lot of data. So that could be one of the flaws, because you have to process all that data. So it could be a little bit more expensive than some of the other solutions. But that would be one of the only things that I can think of right now off the top of my head.
And those are all the questions. So thank you so much, Sanjit, for giving your presentation. And just in general, like he said, if you guys have any more questions, make sure to just ask the email that is on the slide. And yeah, thank you so much, Sanjit.
Thank you. Bye.
Audio check here.
Hello?
Can anyone hear me?
I can hear you, Alan.
I hear you.
I hear you.
All right, good. I hear all you guys. Fantastic.
Yep.
I can't see everyone that's joined, but I assume Cindy's on as well. I see Ayla, Sarah. I see Al. Let's see, I got a pull down window here. I see other people. There's Chuck, Sarah, Cindy.
Everybody hear me okay?
I can hear you, Chuck. Can you hear us, Chuck?
Absolutely.
All right.
There's Cindy.
Yep. Alan, if you count, there should be 8 of us total.
I see some folks from 503. Stand by.
Yes, I meant us.
Yep.
Not our hosts.
I understand. You're giving me a big task counting to 8. Let's see. 1, 2,
Just
3.
remember that everything you say right now is streaming live to the internet.
All right, I can count to 8, everybody. Yeah, we have 8.
Okay, just making sure.
Check that box. All right, we got to do a little shuffling here, I think. All right. Cindy just took over my whole screen. How'd you do that?
Thank you guys so much for joining us. We are back with our last presentation for this 3-hour block with Meet the Chiefs. So if you guys all want to go through and introduce yourselves, that would also be great. And then you guys can start whenever you're ready.
All right, I couldn't hear you completely, but I think you turned it over to us.
Yes.
All right, great. All right, well, thank you. Certainly we want to start off by thanking 24 Hours of STEM and our host, FRC 503 Frog Force. Thank you very much for that. This segment is all about our field, Meet the Chiefs from the FRC side. My name is Alan Bancroft. I'll be your moderator for the next 50 minutes. And up front, there are some chiefs that are not on the call, but we'll make sure we put a shout out to them a little bit later on today. But we're going to go around. We're going to introduce our chiefs that are on the call today. The things that you're going to learn from us today well, I guess what I should say is what you're not going to learn from us today is how to pass inspection, how to win a competition, how to win awards. But we're certainly going to give you some guidance on how to do really well in all those categories. So we're going to go ahead. Once again, my name is Alan Bancroft. I've been with FIRST for about 22 years now. My day job, shameless plug, I work at RE Squared Robotics. We make robotic manipulators that we ship around the world. I got into FIRST because we want to hire people just like you. So when you graduate, I want to make sure you reach out to us and we'll get you building robots that we ship around the world. So with that, I'm going to shoot it over to Cindy Stong for her to introduce herself. Cindy?
Thank you, Alan. So Cindy Stong, I live in Tularosa, New Mexico. I've been involved with FIRST a long time, about 20 years. I think Alan has me beat by a little bit. I do FRC judging mostly. And the reason I'm in FIRST and the impact to my life is working with the kids and seeing that this program works over and over again. Every time I think I want to go camping instead of judging robots, some kid comes with the impact and it just makes me want to do it more. So who's next on the list, Alan? I don't have it in front of me.
Oh, we're going to shoot it over to Al.
Morning, everybody. Morning for us, evening for you guys. I started in FIRST in 1996 when my son joined the Wild Stang team in their first year. My day job had been working in television. I have over 50 years of experience. I started in high school. When I started working with Wild Stang, I did video, and in the very first Midwest regional, the first regional outside of Manchester, the Wild Stang robot was having problems, and my son asked me to come over because all of the other engineers were scratching their heads trying to figure out what had happened. And I looked down in the robot and saw that the mechanical team had drilled through a tube that had wiring in it. And they never let me leave the pit after that. I became responsible for ensuring that our robot would pass inspection at events, and that eventually led to me being a robot inspector in 2003, and I've been inspecting robots ever since.
Fantastic. Thank you, Al. We're going to go ahead and shoot it over to Chuck.
Hey, everyone. I'm Chuck Dickerson. I'm a civilian research computer scientist with the U.S. Army. I work at the Engineer Research and Development Center in Vicksburg, Mississippi. I've been mentoring in FIRST since 2003, 2004, so I guess 17 or so years there. I'm the lead mentor for FRC Team 456. And, for my day job, I have a really great, really fantastic job that I get to carry over into the FIRST mentoring in the evenings.
I work in what's called the sensor integration branch. So I obviously do a lot of sensor work, a lot of different sensor modalities, development, integration of that. Some of the cool things I get to do is, instrument blast effects. I develop reconnaissance systems that are used, around the world by our military right now. And of course, I'd also get to do a lot of different robotics work for both civilian and military applications. Like I said, I've been doing FIRST now for maybe 17, 18 years. And sometime around 2010, I think it was, I started inspecting and have been a lead robot inspector at Bayou Regional since, I guess, around 2010 or so. A division championship LRI for a long time, and work with Al on the chief robot inspector roles now across FIRST. So with that, I'm going to turn it over to Scott, I think.
Morning, Scott Gehring. I'm one of the chief field supervisors. I live in the Kansas City area. I got started in FIRST in 2001 when I joined Team 935 as a freshman in high school. Participated in FRC for all 4 years, and then after going to college, decided that probably the best way to continue helping out with a program that did a lot for me was to start volunteering at events. So I started volunteering in, I think, 2006 or 2007. Worked my way up to the FTA role in 2014. So I also have about 20 years of experience. My FIRST did a lot for me, especially as a nerdy young high school student. We had to do a lot of our fundraising on our own, so we had to go out and do presentations to big groups, big corporations. That taught me a lot about how to do public speaking, how to interact with people that have a lot more power than you do, and that's played a big role in my my professional life. And I'm a enterprise data architect for a company called PRA Health Sciences. We run clinical trials for the medical industry, so we're doing a lot with COVID and the coronavirus these days. So with that, I'd like to introduce Ayla.
Hello, I am Ayla Delott. I'm from the Seattle area, even though right now I am in the Hawaii time zone. So I got started with FIRST in 2007. I joined Team 1258 in high school, and I worked with them for 3 years of high school, and it really was a great experience. I actually met my college advisor at a competition. So he helped me all the way through college, and it just rocketed me with lots of experience towards a professional career, which now I am a manufacturing engineer at a laser company in the Seattle area. And yeah, FIRST it's been a great experience over the past 13 or so years to be involved with teams, to be involved at competitions, and yeah, I'm not sure what else to say, but I think I will pass it off to Lori.
Hi, good morning. I'm Lori Shimizu. I am one of the two chief volunteer coordinators. I'm in Edina, Minnesota. I started with FIRST because it started in my living room with my older son, and it was kind of hard to avoid it when a team is meeting in your living room. It's kind of hard to avoid being involved with FIRST. But I became a volunteer coordinator in 2008 and stepped into the chief VC role in 2016. And the impact has been just immense. I just can't say enough about how this program truly invites all to participate and really lifts them to a different point where you can go out into the world and make a huge difference. And I'm a journalist by background and experience. And I'm just enjoying the fact that we're invited onto 24 Hours of STEM to talk about what we do. And with that, I'd like to hand it off to my co-chief, Sarah Plemons, down in Florida.
And I'm hoping you guys can hear me because Lori was kind of freezing on me there. I'm Sarah Plemons, and I am down in Orlando, Florida, where, it was really nice this morning, nice clear blue sky, and we watched the last SpaceX launch of the year. And 10 minutes later, the booster landed right back at the Cape where it took off from, which is kind of awesome as far as STEM goes. I've been with FIRST. This is my 16th year. And kind of like Lori, I got involved with FIRST when my son was a sophomore in high school and Exploding Bacon formed. And he got involved and I got involved, and he is now, raising his two sons, and, I'm still involved in FIRST. I currently am a member of the Orlando Regional Planning Committee and help plan the competition side of the event. And then at Championship, starting in 2009, I think is when I joined Championship as a volunteer, as a volunteer coordinator for the pit, and then moved on to volunteer coordinator for Curie and other fields. And then in 2017, I became one of the chief volunteer coordinators. My daytime job is I am an operation analyst at Lockheed Martin, where I have worked for 41 years. So at that, I'm going to pass it back over to Alan.
Oh, that's fantastic. I appreciate everyone introducing themselves. And I'll do a quick go back real quick. I am the co-chief judge advisor with Cindy, who we met a minute ago. Cindy and I head up and work with FRC on the judging side. So we work with headquarters, putting some of the materials together that we use in the judging process. And I just want to give a big shout out to my cohorts that are on the phone today. I know we don't have all of the volunteers in the chief category on the call today, but thank you all for all of your contributions. Collectively, there's lots of years of experience here, so I'm encouraging the audience to start streaming those questions into this group, and we'll try to get them addressed the best we can. But I want to sort of segue into, why was the chief role created for FIRST? The chiefs, we also are known as the lead key volunteers. We're a combination of FIRST staff based in Manchester, New Hampshire, as well as volunteers like us that you've met on the phone here. That are more based in the field and scattered around the country. And I forgot to tell everyone I'm in Pittsburgh, so I'm glad to be here representing sort of the Midwest area a little bit. We're also US based, we're mainly everyone on this call except for Ayla, who's in Hawaii, but we're all based in the United States generally. We're responsible for training, documentation, and on-the-spot guidance and support throughout the season. And we work very, very closely, with FIRST headquarters to help steer the programs and support the programs that are happening around the world throughout the season. Some of the responsibilities that we do, as many of you know, it takes a large number of volunteers at an event, usually well over 120. We're not talking about the championships, would take a whole lot more than that, to run each FIRST robotics event. For the past several years, we've had chief volunteers help lead some of the key volunteer training, who we also go and help at the local events. So I know Lori and Sarah do a lot of the key volunteer roles to get folks to help at these events. So a big shout out to their efforts. And the events are growing each year. So, the volunteer pool is really, really important. And the chiefs sort of step in to help sort of coordinate some of those efforts. So recently, to help lighten the burden, we've asked our chiefs to sort of split. There used to be just a single chief in each of these categories that got introduced today. Now we're all co-chiefs, so we absolutely support each other. There's a lot of work. So if, for example, I can't be on a call or an event, Cindy will, and same thing, with Chuck and Al and Sarah and Lori and, everyone on the call here. So we really divide and conquer. There's a lot of work that happens behind the scenes. So, please, when you're out at these events and you see some of the chiefs and some of the folks working those events, please put a big shout out to them. So I'm going to move on here, because the important thing is we want to start putting some examples out of some of the roles that each of us do. I'm going to start off, I'm going to pick on Cindy. And Cindy, why were you picked as a chief or a co-judge advisor?
So I was trying to think when I started with FIRST, and what I remember is Stack Attack. So I think that was 2003, I'm not sure. And I got asked to be a judge at one of those events. I was working at the Boeing Company in Seattle, and a fellow partner from the American Society of Mechanical Engineers asked me to judge, and I got hooked. So I continued to judge. Then I learned the role of judge advisor, which that person's trained to run the judges in the room. And then a few years later, I got that call from First Headquarters asking if I'd like to co-lead in the chief judge role. And the difference there is that we end up, instead of just training a room full of judges, Alan and I train judge advisors all across the world who then train judges. So it just luck of the draw, I guess, Alan, by being
you got so lucky. We get to work together. No, I'm thoroughly
I enjoy it.
No, that's wonderful. All right, I'm going to pick on one more person to maybe share how you were picked, and then we're going to get into some Q&A of each of the groups. So I'm going to pick on Al. How did you get picked as a chief?
In 2009, I had been acting as chief for quite a while, even though it didn't have a title. And Frank and several other people at headquarters sat us down at lunch at the championship in Atlanta and said, you know, guys, we understand that you operate as a group and that you're really good at operating a group, but we really need to have somebody that that we can ask just one person and get all the answers that we need. And I happened to mention, oh, you guys are just looking for somebody to point a finger at, and everybody at the table pointed their finger at me. So that's basically how I got this job. In 2012, I had to have a short stay in the hospital, and I recognized, and that happened right in the middle of the season. And I recognized at that point in time that we needed to have somebody that could step in and take over for me if something happened. And so I talked to Frank, and we came to the conclusion we needed to have co-leads. And it took me a while asking around for people who were willing to step up and do this job the way I did. And I was looking for people not living in the upper Midwest because I have a lot of volunteers up there. And I approached Chuck because we had worked together at a number of championships, and he said he was willing to do the job. I hope he hasn't regretted that decision, but we work really, really well together. Each January, just after kickoff, the week after kickoff, we have been meeting in Manchester and training all of the LRIs, or a majority of the LRIs, so that they can go out and do their job and train robot inspectors. And what we'd really like to tell you guys is, I know it's kind of a fear when an inspector shows up, but we train all of our robot inspectors to be there for you. We want you guys to be successful. We especially want the rookies at an event to be successful, because we know how important this program is to students, and we just want to keep seeing it go on and on and on in order to help everybody.
That's great, Al. Thank you very much. And it truly is an honor. I'm sure I'm speaking for everyone on this call and some of our chiefs that aren't on the call right now. It truly is an honor to serve in this position, to really, help work closely with headquarters. And once I said earlier, there are some chiefs that are directly volunteering from headquarters as well to do some of these tasks. So just huge appreciation for all the work everyone's doing. I'm going to turn it over to Sarah and Lori. I want to start learning a little bit more about what you guys do. So what's the best way to get a role at an event? We know it takes a tremendous amount of volunteers to run these events. How do you guys do it?
Sarah?
So the best way to get in a role at an event. So there is really no one best way to get a role at an event. But for starters, the first thing you need to do is apply and apply and apply. And of course, you do that through your volunteer dashboard. It's good to get to know your local event volunteer coordinator and let them get to know you. That's an important piece. Not that you just know their name and you kind of reach out to them and say, hey, I want to volunteer, but it's good to let them know what your skills are, what your interests are. Even if you're a first alumni and you're familiar with events, you've been on one side of the event, but you haven't been on the other side of the event, and there's a lot going on in the background, and there may be a role that is a really good fit for you that you just aren't even familiar with. Because it's always been in the background, not on the field where you can see it. Let's see. I guess the skills part is important. It's not just your technical skills, it's your leadership skills, it's your background, your personality, your ability to handle situations when they come up and to keep a calm head. It's your ability to do all those things. And we may not find the right role the first time. It may take a couple of tries to find, the really good fit for you that you're good in and excites you and brings you back to the event, time after time. So that'd be my answer.
I like that answer. Anything to add, Lori?
You have to think about it as a journey. You are launching yourself on a journey, and there's no one way, there's no one pathway. We work with a lot of volunteers who all say zig and zag. They try one role at an event, and then they'll come back to the volunteer court and say, I don't know if that was really a good fit for me. So you really are launching a conversation with the volunteer coordinator. I'd like to say you're never one and done, Alan, and there's always room for another pathway to develop. I don't know. I don't know. Scott's giving me the smile that maybe the technical route may not quite be what you want to fill up all of your volunteer time, but it's really a conversation that you're launching. And just because it doesn't work for you at one event, don't think you're stuck. I think that's the biggest message overall, is you're never stuck in a volunteer role. There's always an opportunity to grow and try something different.
That's great advice. And I know we've seen volunteers do different things, even if they weren't stuck, they just wanted to learn different aspects of the organization. So lots of opportunities there. Get involved, right? And then from there, your journey will take its course. I want to switch up a little bit, and I'm going to turn over to Scott and Ayla, from a field supervisor perspective. What is the difference between an FTA and a field supervisor? There's a lot of confusion. Please educate us.
I would love to educate you, Alan.
We don't have a lot of time to educate me.
For this very one specific question. So the field supervisor has sort of three main responsibilities. One is field setup, field teardown is the second one, and then making sure that the field is ready and the event runs on time. The FTA has those same responsibilities, so we help a lot with setup and teardown, and obviously making sure that matches start on time. We also are the primary technical point of contact for the event, so all the field software, the field, the robot connectivity is all part of our responsibility, and then we also work a lot with the other key volunteers for that event. So we're working very closely with field supervisors, the FTAAs, the scorekeepers, queuers, LRIs, etc. Really just to make sure that the event as a whole runs as smoothly as possible. So I think those are the primary differences there. I don't know, Ayla, if you have anything you'd want to add to that.
I was just going to quickly add also the field supervisor is working directly with all the rest of the field reset staff to help make sure that the field gets reset as quickly as possible. And also to make sure that if things break on the field, that they get fixed in a timely manner so that matches can continue and that everything works the same for every team that comes onto the field. So yeah, that's all I had to add to that.
No, that's fantastic. I mean, I think we've all seen, the sprinting in action when things are happening on the field to make sure that the show goes on. So, real important job that you guys are carrying out there. Thank you very much. And I guess, sort of a segue into that, you see all these people running around at the high school, the FRC events, running around in these blue shirts. Maybe Cindy can talk to about what are they doing?
Are you referring to judges, Alan?
Oh, judges. Is that what they're called? Yes, we're talking about the judges. Yeah, so tell us about judges.
So it's a role I'm kind of addicted to. And the main reason is you get to go out and talk to the teams and the students, which is the fantastic part about doing that job. The judges are a group of folks that are usually sequestered away unless they're talking to you and asking questions about awards. It's a group of professionals, and we go across the gamut of different professions that we choose from. We need technical as well as business folks. even writers like Lori for writing scripts at the end. So it's a fabulous job that's led by the judge advisor. We're very careful about training our judges ahead of time. They need to be up to speed on all the awards, know what the criteria are for each of the awards, so they can ask carefully crafted questions of you when they're talking to the team. And then they also have to be able to work together to discuss pluses and minuses of what they've learned out there with talking to the teams, and then decide what awards are appropriate where. You want to add anything, Alan?
Yeah, no, that's great. And thank you, Cindy. Yeah, as being Cindy's co-judge advisor, I guess what I would add, and I always like to coin what I learned from Dean Kamen early on is, judging is all about judgment. We do have a group of judges. They're trying to get the stories the best they can while they're interviewing all the students in the pits. Sometimes, to Cindy's point, some of these interviews are happening sort of behind closed doors. And it's taking all that information and trying to get, the best deserving teams to win the awards. The challenge is everyone out there is deserving, and we don't have awards for everybody. So it's a very, very difficult task. The folks that are doing the judging they take that role very seriously, and they're very committed, as all the volunteers are within the FIRST organization. But yeah, there's a lot of work behind the scenes, I guess I would say, on that some of the students may not be aware of. So Cindy, that was great. Thank you. Just maybe a real quick follow-up. Where do these judges come from? Where do we find them?
So well, Sarah and Lori help us a lot. Also, our planning committee helps us, and sponsors sometimes will ask some of their employees to be judges, which is great for both of us. So it's from anywhere, from folks that qualify. There's an age limit, of course. You are trained, so you don't have to have done it previously. We also look to maybe societies like American Society of Mechanical Engineer. It's just a great way to get your foot in the door, see what goes on behind the scenes, and talk to students.
Okay, that's fantastic. Well, I guess we've learned about how we get volunteers. We've learned about how some of the operations happen on the field. We've learned about how we get some judges to judge some of the events, but I guess none of this is going to happen if we don't end up with any robots. So I'm going to shoot this over to Alan, Chuck, and I've got a couple of questions for them. But why should somebody volunteer at an event to help with robot inspectors? Why is that role critical?
Why don't you start, Chuck?
Sure. When I first started inspecting robots a decade or more ago, I was nervous. I had spent all my time with my own team, and I was very technically competent, and I knew the robot rules in and out and that kind of stuff. But I felt like I could give back more to the community. I thought FIRST was the greatest thing since sliced bread. And I was very comfortable working with my team and my students and, 20 people sort of thing. But I felt like I could give back and share that knowledge with all the other teams at competition, particularly some of the younger teams and the rookie teams that I would see struggling. And so I volunteered to step away from my team and be that robot inspector that first year. And it was the most rewarding and wonderful experience I had right out of the gate. I really found that I could help so many more, and it was good for me. The things I learned from other teams. There's nothing like stepping into a pit wearing that yellow hat, and other teams are eager to talk to you and tell you about your robot and enthusiastic about it. And you get to stick your head in every robot there and share ideas and collaborate. And yes, there's some problems occasionally. And that's what robot inspectors' mission is to help teams, solve those problems and come up with the solutions on the fly and connect teams to each other out there. But as far as volunteering, I think that being a robot inspector is one of the great jobs in the volunteer community there in FIRST, because of the in the pits collaboration you get to see and be involved in. Al, you want to chime in on that?
Well, I basically do this job because I'm a little selfish. I want to see what other people's ideas are, how they've managed to accomplish something on their robots so that I can bring ideas back to my team. But like Chuck said, our biggest fulfillment in this job is being able to help other teams become successful. As you know, when you get to an event, you're very nervous. You're wondering whether your robot's going to function properly or not. You're worried about the inspectors. You're worried about everything. And my job and the staff that is holding down inspections at your event are there to make you feel better and to take away any worries that you have about your robot. We're not only there to inspect, but the reason that we have inspectors is because Dean and Woody first took a look at the competition and realized that there were organizations like NASCAR that had inspections so that everybody was playing on this semi-flat field. And inspectors are there to, first off, make sure that your robot is safe. It's not going to hurt anybody. It's not going to hurt any other robots, but also it's not going to set itself on fire. Venues kind of frown on things setting themselves on fire. And so we're helping maintain the integrity of the competition so that we can come back next year in the same venue. But we really get a lot of satisfaction about walking into a pit where the entire team is scratching their heads because they have a problem and they can't figure out what it is that they need to do. And we, being the cool heads, because we're not a member of the team, walk in and go, oh, guys, you need to move that from there over to there, and most of your problems will go away. And Chuck and I both sit on Slack and on phone basically 24 hours a day for every event weekend. We're available because we now have 180 events worldwide. Those events are going to take place at non-traditional times here in the United States, but we're available if any one of those robot inspectors has a problem to give us a call, contact us on Slack and ask for guidance. So we're in effect on every single team in FRC.
That's great, Alan. Chuck, thank you very much. And I've got so much more I want to learn from all of our lead folks here, but I really want to reach out and see if we have any questions coming in. So Ashna, do we have anything coming from the field that we should address?
We have had a couple. Can you guys hear me now?
It's very soft, but I can hear you.
Okay, I don't know if my network is kind of going nuts right now, but the first question was, what is like some of the most interesting things that you guys have seen at competitions from students?
Can you repeat that one last time?
What are some of the most interesting things you guys have seen at competitions from students?
All right. Well, man, I don't even know who to start to turn that over to. I'm just going to pick on somebody. So Ayla, let's start with you.
Actually, I'm going to revert back to my judging days of interesting things I saw. So for the first probably 6 or 7 years of volunteering, I did a lot of judging with Alan and Cindy, and definitely saw some interesting things. I remember specifically there was one team from Canada that they had a student on their team that they needed prosthetics for their shoes, and they worked to 3D print these prosthetics for the students' shoes, and that's how they learned how to do it for their entire community. And so using their STEM knowledge to help their fellow student, and then to move into using that to help their community. And I just remember they were so passionate about learning how to make it the best they could. And they had just books and books and books of their tests and their research behind how prosthetics work and how to make it the best they can. And I will never forget that. So that was one of the most interesting things I think I've seen.
No, that's great, Ayla. And we certainly be remiss if I said we don't miss you as one of the judges, but I'm glad you're still playing a very important role. Maybe just I'll reach out to one more. Maybe Lori, any Maybe you can share with us an interesting thing you've seen at an event.
So at one of our events up in Duluth, Minnesota, we had a team that decided that all of them could fit on a glass elevator. And we've all learned what happens when you overstuff a glass elevator. I think that we counted upwards of 25 people on this elevator. They literally were going up one floor. But as you know, an elevator has a capacity and will only go so far before it says, no, we're not going anywhere. So we got to watch them, all of them. They were crammed in there like sardines. And in the middle, there was a robot inspector wearing a yellow hat who very feebly, when we finally released them and we got the fire department, we got everybody involved, he came out and he looked at me, he said, I really tried to tell them. And I said, next time it's like you push them out of the elevator. But yes, that has provided some memorable moments for us, and it remains a teaching moment at the event, because we really do remind teams that you cannot overload an elevator, because you will enjoy quality time with each other in that elevator.
I seem to remember that was 32 people, Lori, and the windows
I stopped counting.
But the windows did get pretty steamed up.
Yes.
Yeah,
Took about a good hour to get them out.
I'm sure that was very scary. All right, so we're gonna hold on that question. I'm gonna go back to Ashna. Any other questions coming in that we can talk about?
We have another question that is saying, how many hours on average do you end up putting in during the season, and what about during off season?
Wow, that's a great question.
That's a hard question for us to answer, primarily because we're also involved in other competitions. So I act as a judge in FLL. I am the chief robot inspector for the state of Illinois for FTC, and I'm the chief robot inspector in FRC. I don't know how many events Chuck gets to. Chuck does pretty much the same thing I do in those three divisions. I counted up one year, and when I exceeded 1,000 hours for the year, I decided to stop counting.
I used to actually keep a spreadsheet, and because my boss wanted to put me in for some kind of a DoD STEM award or something at one point in time, and they kept asking me this, and so for several years I kept a spreadsheet of the hours I would put into FIRST, and that included volunteering and mentoring my team and everything. But for like 3 years, I kept that spreadsheet, and every year it was well in excess of 1,500 hours, closer to 1,600 to 1,800 hours a year. And I just quit doing the spreadsheet because, it's a second job. It's a second full-time job basically for all of us. And, I think we all do it because we love it. We love the kids. We believe in the program. I see, everybody shaking their head. Yes. If it's not a job in that aspect of, I don't want to go do this. It's something that we truly are passionate about. I think everybody on this call is passionate about FIRST because we've seen the impacts. Personally, I don't have children of my own. My wife and I don't have kids, but I have hundreds, thousands of kids out there. I'm writing letters of recommendation for students in other states because I've gotten to know them. I wrote one yesterday for college applications because we see the impact that FIRST has on everyone's life, students, adults. It's truly impactful. I think it's truly changing the world for the better. I think that this pandemic has shown that we can all still come together virtually and do great work and do great things and collaborate together. So it's hard to put an actual number on how many hours we see, but it's year round, off seasons. Al and I know the others on this call are involved in their aspects of working with FIRST to develop, the rules and changes and documentation and trainings and things like that for the upcoming season, year round. We do a lot.
Well, I just want to add to that, Chuck, because At any given time, all of us are available. I know we're always looking at contacts from teams, from volunteers, and it is pretty much year round. A day for us without robots is unusual, even during shutdown. When we were all in shutdown in the spring, FIRST was still going. It's still going now. And we are all in contact with each other as chief volunteers, but we're also in contact with the people that we work with in the field and at headquarters. So there is no question too small or no question too great for us to answer. So we truly are available to the FIRST community throughout the year, pretty much all the time.
No, that's great. Maybe, something I would add, for people that may not know, FIRST is a nonprofit organization. So, the folks that work at headquarters, they don't have thousands and thousands and thousands of resources to pull off all these events and all the work and all the things that happen to hold these events. And FIRST headquarters really does work and lean on the volunteer community to do that. For me, I think I agree with Al and Chuck. Back in the day, I used to sort of keep track of my volunteer time. And it wasn't really because I'm only going to volunteer 2 hours a year. It's because I really wanted to sort of have a life balance of things that I wanted to do as well. But clearly there's no exit strategy and just the passion. I don't even know how many hours I think at this point in my life I volunteer to FIRST. I wish I could volunteer more and more time. I probably take more out of the FIRST program than I'm giving back, which isn't my intent. I'm hoping I'm actually really giving back, but I very much enjoy the program. I've started teams. I brought my kids up through Lego right through high school, and it's been very fulfilling for me. So I think right now I'm gonna jump back to some other questions that I'm really burning to ask this group, and this is a perfect segue, back to Lori and Sarah, when we're sort of talking about how, all these hours that all these volunteers do. And it's not just the ones on the call here. I mean, there's volunteers around the world that are putting in if not more equal, if not more hours than we are. But how can I become a volunteer, right? We need more and more of them. It seems like, I don't think I've ever been to an event and says, wait, we got too many volunteers, just go home, right? I don't think I've ever been to an event in 22 years that's happened. So how does one become a volunteer?
It's actually pretty easy.
Apply.
It goes back to apply. There are event planning groups and regional planning committees for all of the FIRST events around the world. And it can be as simple as sending truly an email to volunteer@firstinspires.org. And the happy people who read those emails are very happy to refer volunteers on to the volunteer coordinator in that area, in that district, in that territory. And truly, especially this year, because we've reorganized how we're looking at what we're calling events this year, you may want to contact headquarters through that email and they will get you started. After that, it truly is as simple as setting up a volunteer account through your dashboard with FIRST Inspires. There is a button there called Event Volunteer. You click on Event Volunteer. You clear your filters, you click on FIRST Robotics Competition, you actually click on Apply Filters, and there will be somewhere in the neighborhood of 36 events that will pop up on your screen and you get to pick from them this year. And I'll put in a plug, you can either be a judge this year if you're age 23 and over, to volunteer for one of what we're calling the online challenges, the Innovation Challenge presented by Qualcomm, Infinite Recharge at Home, which is the Skills Challenge, and of course, some of our favorites, the Game Design Challenge, where your game might be picked for future FRC competitions. But there are also 33 events that are currently live that you can apply for. And what these are the local awards, if you will. These are the submitted awards for the Chairman's Award. Please apply. And mentors, please write up your students for the Dean's List. So there are quite a number of volunteer positions that thankfully will just pop up now when you go into volunteer registration. And it truly is as simple as that. And then from there, you are launching a conversation with a volunteer coordinator and a judge advisor. And it just flows from there. The fun begins. Sarah.
I was gonna say, I think you covered that one.
All right, great. Well, I love the plug, volunteering for judges. I didn't realize you could volunteer for something else. No, I'm just kidding. There's lots of opportunities to volunteer across the board. But real quick, I know we have a hard stop coming up. I want to make sure I put a shout out to some of our other colleagues that are not on the call today. We have Chief Referees John Zolak. And Aiden Brown, sorry they couldn't join us today. Blair I know these people. Blair Hundermark, who actually does most of the MC work, so I'm a rookie. I'm training. I'm Blair 2.0 for today. I'm sorry we didn't have Blair on the call. Danny Diaz is one of our scorekeepers. Kevin O'Connor, who works with the Control Systems Advising Group.
Okay, so Alan, I'll help you. It's Naomi.
Help me.
Naomi Mancuso, who's our PID admin supervisor.
All right, good. Good. Then the rest I can get. Derek Foster, FTAs and field supervisors. Krista Pratt, LRIs and robot inspectors, and Fiona Hanlon, who really works with Cindy and I. And a huge shout out to Fiona and all the work she does with us throughout the year. She does a lot of work behind the scenes that probably isn't transparent to everybody. So big shout out to Fiona. I guess also I want to do a big shout out to the folks on STEM who have hosted this call. So thank you once again for FRC 503 Frog Force for hosting us. And if there's other questions that you have after this call, please don't hesitate to send an email to volunteer@firstinspires.org. Those will certainly come into us, and we'll make sure we get those addressed. But with that, we have a few more minutes, and I'm going to reach back out to Aishna to see if anyone else has come in with questions.
As of right now, there haven't been any in the chat, but there are just a couple in general. Like, what are some of the minimum ages for key volunteer positions for people that can volunteer?
Laura, Sarah, you want to take that one?
Sarah, I can speak to some of them. There are minimum age requirements for most of our volunteers, especially as you work more in the technical areas. I know for judging, 23 and up is really the minimum age requirement, but to be a robot inspector, we really do prefer, and this is where Alan Chuck will correct me if I'm wrong, but 18 and not on your high school team. We'd like to see that you've at least graduated and you've started your college career or your technical career, whatever your step is after high school. But all of the minimum age requirements and the listing of responsibilities and what we're looking for in a volunteer, those are all listed on the First Inspires website under volunteer. And it's really so that we put a little bit of distance between you as a student on a first team, and now as you're stepping into what it means to be an adult and to work with other professionals in the field, we really are trying to set you up for success. And I think that's probably the biggest aspect of this. We're not going to deny you a volunteer role, but we are trying to set you up for success. And over the years, this is where we've developed some minimum requirements. Sarah.
I think that everything you said is true. I don't know all the ages for all the different positions either, but I think the question was geared towards key roles. But even in the non-key roles, there are some age requirements, and they start, I think, at the for a regular district event and a regular regional event, I think it's like age 13 is the minimum. It can be changed by the local planning committee, but the guidance is age 13. And at championship, it is 15. So that often we have to address that at championship, because people will volunteer at their local event and then want to come to volunteer at championship, and the requirements for championship are a little bit different. It's 16, I believe, for championship. Yep.
Okay.
So.
Well,
hey, Alan.
I want to jump in here.
Jump on in, Al.
I do not have enough women inspectors. Since we're the visible people, the visible volunteers in the pit, it's important for girls on teams to see that there are women in technical positions, and so it has become my personal goal to try and get more women into volunteering and inspection. So do not think that that is a volunteer position that's not open to you. It's open to women as well.
Al, that is exactly what I was fixing to say. And in addition to that, I know that a lot of people may be hesitant to jump into a robot inspector's role. Don't think we're going to throw you to the wolves. We train all the LRIs to work with the new inspectors, people that are volunteering, and you may be partnered up for half a day, a whole day, whatever it takes to shadow a veteran, experienced robot inspector until you feel comfortable to solo. So, and I think that's true in all the positions here. So if you're interested in volunteering for a role, don't be hesitant. We're not going to throw you to the wolves. We're absolutely going to make sure that you're trained, you're ready, and feel comfortable in that position before we turn you loose out there. But like I said earlier, please volunteer. It is so rewarding. Whatever the role is, robot inspector, field reset, referees, judges, whatever. There's so many different roles. We have something for everyone. Volunteer. You will have the time of your life. Step away from a team and see the other side.
That's great. And just maybe building on that, Chuck, and we do have volunteers that are on teams, just to point that out. We generally don't like to have volunteers that are working with the team and working as a volunteer at that event. But if you come in with your team and your team's well taken care of with the other mentors and so forth, please volunteer. To everyone's point, we definitely that's how this program is going to continue to grow. Were there any other comments on that question before I wrap up?
Just a real quick one. So look at those volunteer roles carefully, because, for example, in the judge room, we can have a judge assistant, and I think that age is 19. So there's lots of ways to get involved.
That's fantastic. Well, in closings, I know there's other speakers coming on. A huge shout out to 24 Hours of STEM. Thank you very much for inviting us once again to be part of this this call. I know you guys have done a tremendous amount of work getting all this organized. So big shout out to everyone in that group. So thank you, Cindy, Al, Chuck, Scott, Ayla, Lori, and Sarah. Huge shout out to you for taking time this morning or afternoon or evening, depending on Ayla's in Hawaii, for taking your time to help educate some of our folks that are dialed in today. With that, all of us are very excited about kickoff, which is January 9th, and the start of another great season. So looking forward to seeing you there. And once again, Dean's List candidates, submit. Every team that's listening right now should absolutely be submitting your 2 candidates. And looking forward to seeing all those teams submitting for the awards. So with that, thank you, Frog Force, once again, 503 for all of your work, and stay safe, everybody. Happy holidays.
Thank you guys so much for
Thanks
coming.
all.
And I think behalf of
everyone.
the entire First Students community, thank you guys for putting
Thank
so much
you.
time.
Bye.
Bye. Thank you.
Bye-bye.
On that note, we are going to be going and watching a video, which is going to be introducing Python programming using Lego Spike Prime. So this is kind of funny because the time for this is 5 minutes and 3 seconds, which is our team number 503. So kind of cool. And it's going to start now.
Let's finish this off with a couple of activities called Hello World. So my Can You challenge is, can you go STEM? Go STEM. With Lego, cardboard, and Python. Now in FIRST Robotics, coding of robots is essential, and there's many different languages to use. At Whimsy, when we're introducing students to computer science, we'll use tools such as Scratch, and we'll use tools such as Python, which is very readable as you go through. Forgive the Minecraft noises in the background. Hold on, I gotta fix this. Because I'm, all right, oh dear. Well, the cat's out of the bag on that one. Let me quit that. That was gonna be a demo. Let's see if we can pull that one off. I spawned a bunch of dogs with Python in Minecraft. Okay, so Python. So we're gonna program with Python. The first place we'll go, and let me share my screen, is, did that work there? Can we see this? Do I have confirmation that we can see this? I'm hoping we can. Amanda, can we see this? No. Stop share. Let me try one more time. I got all this time. You know, I'm getting a little lackadaisical here. So, oh, you could see it. Oh, let's try again. Share again. Oh, we're good. Okay. Whew. All right. So we're gonna go into a program on the computer itself, and let's make this bigger, 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 bigger. Go big. And so on any computer you have, you can get Python on that computer. And on my computer, I just go into the terminal program and I type Python. And I say print go stem. And it says go stem. Let's have it print go stem 10 times. This is cool. It's going to use a for loop for x in range 10. I think I said 10. I hope I said 10. We're going to tab over and we're going to say print go stem 10 times. Okay, so hello world tasks in any programming language is find the programming language you need, load the resources, and write your first program. And in this case, we wrote our first program, go stem. Well, Python as a program can be used to work with other devices. So we've got here a Spike Prime kit. So Lego Robot, Mindstorms, long history there. Working with FIRST and other groups in education. And if I do, actually, let me do a new activity, and I'm going to do Python here, and I'm going to say test. I'm going to spell it correctly. Well, I got 2 minutes. I think I can pull this off. So they already built their hello world into this, and if I press run, I get a smile. Well, let me try my go stem. So I'm going to say hub light matrix right go stem, and let me run that there. Well, I think I got time. And go stem. Now in this one, I'm going to go back to my pre-baked program here, and we're going to try to end in the last minute here with our 15th activity. And I'm going to put this go stem here, and we're going to run this program, which has the loop in it. And so first, whoops, there's the go stem, and then my motor says go stem 5 times. Awesome. Well, this has been a super pleasure and honor to work with everybody on this 24 hours of STEM. And I think we did it. Congratulations, Whimsy team, fitting 15 5-minute STEM activities into 1 hour. Well done.
On that note, that was our last presentation and video during our shift by FRC Team 503 Frog Force from Michigan. So thank you guys to everyone who tuned in, and thank you to all of our presenters. It was really great to hear all of those different presentations. Just another thing, make sure to check out 24hoursofstem.org for more information on the challenge, which will be open up until 6 p.m. Eastern Time today. So make sure to go check out the website there. You can also head over to Mass Stream 4 for more presentations, or you can check out Mentors Without Borders Stream because they have a lot of cool things going on there too. Thank you to everyone.